I think it wasn't this session selected or something like that. Does that make sense? Yeah. Like the room was right, but the session or something like that. Sorry. I think in the next video,
Well, there used to be, some of them had a clicker just hanging out here, but I don't, oh, I think it's right here.
Okay, perfect. That's 3 people, I don't know who wants to smoke first.
We'll see what happens. Almost as good as landed on native. The optimized stack, lectures on the optimized.
Yeah.
Game and all.
Yes. I was there.
Yeah, whatever they do is
I wanted to study that, but I think it's also having good courses. Like, create this slide. I went and they said, if you don't, they were weird about it. Buying that is they were like stuck up, like, you should know who made this chair years ago. If you don't know that person, then what are you doing here? Go away. Yeah, that would be idea. So, like, he asked some kids, so like, who's your favorite artist? And then he gave it, he was like, so like, why can't you do the same like your favorite designer? Like, no, I think the focus was different away than maybe interesting, which was fine, but also that didn't help. And the other thing was using glass. I don't want to be in glass. I don't know.
That's very interesting.
It's okay. It's like something. In my opinion. Yeah. That's what's happening to me. So now, the problem is, but hopefully, I always have like ideas and things I want to do. You know, I don't put enough effort in. Typically, I hope that something pops off. I have 1 or 2 things right now. If it don't work out, then I'm going to work out. That's always the idea. Very best in what? Exactly. Not investing. I have an idea for a camera which doesn't exist, and it should exist. And I'll leave that out. Yeah, it's fortunate. That's not the it's optics, and I do not know optics. I'm working with a friend, and he's currently making a program that basically real-time renders images. Like let's say you're trying to design a lens, and like the lens is let's say 3 elements, and you want to make that lens. If you're a professional optics optical engineer, then you basically do it in like 2 graphs and use the maths, and then it gives you numbers, and based on the numbers, you understand the numbers and can interpret those into like what will it look like. But as someone who didn't study this, that's really hard. So what he's doing is really different. What he's trying to do is he's making a program that basically has the same input, but instead of giving you numbers, it gives you like a visual, like actual image. So you can tweak the lens and have these movements and actually see what's happening. So like it's more like intuitive. You still understand what you're doing. You don't need to like do precise mathematical formulas to get yeah, but you also have to do what, but it's for someone who doesn't know how to design, like the science or something, it's not. So I'm waiting for this and I'll be up to date. I went through all the patterns, everything, and no one's done it. Like, it's like, it feels like, what's the right way? Like, let's say, but it's the kind of thing where you have to do the work to get it done. And that's the only way, like, it stops when it stops.
What do you say?
Big mixing.
Yes, 24 channels it seems, but I'm not audio guy. Seems kinda excessive for this. Well, no. 1, 2, 3, 4. And the info channels. Oh, well, yeah. I guess it's not excessive. I guess the video is expensive.
In this particular one? Yeah. Okay. I haven't heard of this.
I don't know. I haven't heard any talking about the next possible. Which is L2, right? I'm seriously, I don't know. I'm a good camera.
Yeah, it's only telling you that they're I can bring someone over to.
It seems like our schedule is a bit behind, so
I think everyone's scheduled behind.
yeah.
There's some sort of problems now.
That's how it is with Linux. Problems everywhere.
Isn't that what the Linux people complain about Windows?
Yes, they do.
When we saw those business solutions, it's like rewatching the
Yes. Yes.
Some of the masters, they probably have 10 people employed that do Linux.
No, they just over it. Just giving money.
No, they need their names.
Because it's very
You actually have public drivers in Linux. You actually can do that. If they put their name there and they just don't do public drivers for Linux, that would be kind of complicated. So I don't use Linux, I don't know. But I can imagine that it just don't be popular. Or like, it's like people like backwards and forwards.
it would be very stupid if you don't use drivers for Linux. So it would be very stupid, so I don't think that we have to miss the part of it. No,
Not getting treated like
it was 10 years ago. Yes, Linux is a proper operating system that is just like
Okay, hello everybody.
but don't say that.
Hey, I will be your point person for today. Sorry, so sorry. Let me give a little bit of a rundown of what's happening. This setup is really complicated. which are these guys. This one's off right now. And then these guys are the remotes for the camera. So part of what you guys are going to do is change these guys out in the catch boxes. Their battery lasts about an hour or so. So whenever there's a break in a session, like I think they do like 10-minute coffee breaks every like 2 or 3 sessions or something like that. They're pretty short sessions. We have two or four of these at each table. You guys are going to change it out with a new one. So to put it in the catch box, there's magnetic down to the base of it. So it's going to reach in there, grab it.
Hallo.
Put it in and snap.
Willkommen meine Damen und Herren, willkommen beim Linux-Kongress, willkommen in der Lounge 2.3. Heute an diesem wunderschönen Mittwoch, den, keine Ahnung,
Just so you know, the back switch
20.
has to be
18. September. Ich hoffe, ich bin laut genug, ich nehme schon an. Ich höre mich auch, draußen ist super laut, also es wird schon passen, Leute. Beide Mikros funktionieren. Solange du beide nicht gleichzeitig komplett gleich hast, passt. Also eins immer lauter als das andere, weil sonst haben wir wieder Phasing.
WhatsApp group, yeah. With it. Then you can let us know if there's any issues in your room, or like, hey, Mike is dead in whatever room you're in, just tell us the room name and we'll get help sent to you guys. Either I'll come or one of the house audio people will come, depending on what it is. So if it's an audio issue, say, hey, L3 audio's not working, and then we'll get some help on the way.
So we posted in the WhatsApp group. You are in our WhatsApp.
I'm going to be, at least if I'm not already. Yes, I will be. And there's a lot of things going on for us today. It's super busy. So if you guys have multiple issues, or if a couple of you have issues in the group, I will try to get to you as soon as I can. I know it's super awkward when the client's looking back at you and you're like, I don't know what to do. I'll try my best to be here fast. Anyway, so this remote will go right here. Let's put it, this is the power button. You hold it for a few seconds and it turns it off. A few seconds turns it on. Then the light will be green and blink every once in a while. That's good. We'll put it, power button up, kind of tucked in right there like that. This is kind of how it goes. So, power button up, tucked in like that. Close the Velcro, stick it in, then in theory, that camera should follow the catch box, which is working right now. Yay. So they will have this, they'll toss it back and forth the room, the camera will follow it as best as it can.
So the speaker is going to carry the catch box around?
The speaker will be up there at the podium.
Yeah.
This conference is very like, they'll talk, someone will talk. It's kind of like anything goes. It's very, they call it fluid and dynamic. It's kind of a free-for-all, really is what it is. And they're supposed to wait for the mic to be thrown to them. They almost never do. But yes. For Steve? Yeah.
The one room over there, which one was it? Is still set to chat. You just need to switch it to.
Okay, perfect. I will be over there in just a few minutes. Yeah, thanks.
We have 4 times copies.
What was I saying? So they'll have this, they'll be somewhere in the room, and the camera will try to follow it. If the camera wigs out, which it probably will, you can let us know. We may do something about it, we may not. I'm sorry, I'm not giving you very much confidence in this. It'll be great, guys. It really is a fun system.
So how do you know if the remote battery is going to die? Or do you...
Exactly. This is not our normal system. We do this once a year only for this event, so...
But we just generally make the change of the batteries every break.
Change the batteries as often as you can. Yeah, so...
Do you have a means to recharge them?
Yeah. So come back here, or look over the side or whatever. These are the batteries. These are the called watches. Pixel calls them watches, so they're watches. Is what we call them. So the watches, those go on like that, and then they're supposed to charge. If they're fully charged, they don't. They only charge wirelessly. Correct.
Do you have to turn them off to charge?
In theory, no, but I would, because the less sensors that are going on, the camera seems to follow better.
Right, I understand.
It actually does. So you'll have this iPad back here as well. It's just on okay. This is the Pixel Remote app. It's only semi-helpful. I think when the watch is about to die, there might be like there might flash a little battery symbol on it. I don't remember. But what you might have to do is if you turn a new remote on before taking over and out, hit follow, and now it'll follow this remote. So last event we had 2 catch boxes in each room. So then you had to sit here and switch them from things. Only one this time. So you might have to hop in here and do it. In theory, if you take the one out of the catch box, turn it off, and then turn this one on, the camera should auto-connect to the new one. Double check it on that.
And the electronics, the 2 switches inside the cube, they're on all time.
They should be on all the time, and then our helpful audio people will also check it out.
Alright, how do we know when the camera doesn't follow?
You'll tell. It'll start like, it won't be where the catch box is. So sometimes it's hard to tell where the catch box is in the room until they throw it. And sometimes the camera will follow it and then go back. Start to find it. Yeah.
Is it also a microphone in there?
There is, yeah. So that's what that is. Yeah, so the soft can come off. Don't worry about it, it can stay on. Just pull it out. And it has, so yeah, the microphone is right there. It'll stay on. And then this part back here is battery, that'll stay on. And it has some software and a circuit board in it, so it's supposed to turn the mic off when it's being thrown, so you don't hear like the whooshing of the wind and the bang and stuff. It mostly works. That's that. So you guys will mostly be doing that is kind of the most problematic thing. If the front camera starts to really freak out, we've had them a few times where they'll just lose their mind basically and start spinning to a certain extent. If that does happen, if you guys could run up there and just pull the power, because we just don't want to break the SDI cable and stuff that's hooked up to the camera. I'll walk up there with you guys in a second and show you how to do that. We've only had it happen like once, but if it does happen, doing something about it would be amazing. That's cameras. Any questions on the camera? I'm sure
Yeah. Is there any situation where we have to do the camera manually?
No. So there's 3 cameras hooked into it. So you can tell on screen, there's that. I was thinking about out there. That's on now. This back one is always on. It just stays, and then that follow camera. So there's 3 cameras. They might ask you to do some stuff on the computer as far as like software that's up. You can tell them you have to wait for one of us. We're not supposed to do it, but we can. But anyway, so for the computer back here, is hopefully you won't really have to do anything with it. If you guys were to pan shuffle around the back, so this is our little setup. Emix is a recording software. It's also how we're sending stuff to the front of the house. this screen is just a copy. We're copying this screen and sending it to the house. So just so you know, if you move your mouse over here and do anything, they can see this up there. Which is why we most likely won't have to do anything here. Shared notes is supposed to be up. They'll switch through the slides up there.
They do that.
They do that up there, we don't do that. These are the camera feeds. So you can kind of keep an eye on these. They will most likely lag. And that's not our fault, it's this software that they built. So this is what it is. If they go like gray or black or cut out, you can let us know and we can try to re-input them.
Paying attention to
So we can try to do that. So hopefully you guys won't have to do anything here. This should be running. It'll run all day. They'll control the slides. Hopefully that'll be good. They'll put notes and stuff in here because it's all linked to their online software. On vMix, streaming is already going. It's streaming to YouTube as well. It'll stay streaming all day. So you don't have to worry about that. You don't have to worry about switching anything here. What's on this side is being recorded. If you guys hit the space bar, and will switch to this one, don't do that. We just want to record something here. So, if we can, for this conference it's really difficult, but if we can, two presenters on the box, stop the record, so you'll hit it, you'll give a confirmation, you can say yes, and then just hit the record again. That makes it much easier for us editing.
Trying to make it a half
to get this a break in between the presenters, so we can find what presenter is where. Yeah. Oh, sorry, yeah. Yeah, so for between presenters, if you can stop recording, but then just restart it again right away.
Restart it immediately.
Change next to 131 to results instead of a chat. Yeah, so if you just click it, it'll give you a little confirmation, stop record, hit yes, and then just hit record again, and it'll start. If it ever asks you, there's an error window that pops up sometimes that's like file location is this or whatever. Just hit confirm. You just confirm everything. It's just letting you know that it's being recorded to the documents folder or whatever. But if you can do that between presenters, great. Sometimes the presenters are like, they'll kind of start talking as the other one's getting off and that kind of case, so then don't worry about it. It is what it is. Can, that'd be great. Remix. Pretty good. Yeah, record, stream all day. This is how we're getting audio in and out. As long as you see levels on there, you're great. If this thing shuts down, let us know immediately. It shouldn't, we've never had that. But just so you guys. For now? Okay. Yeah, it's not unmuted.
Keep the camera focused there then. I'll put it in the middle seat. I'll put it in the middle seat by the speaker.
Put it on the far edge because they don't like to get really close to the camera.
Oh, okay.
Because then it starts. I don't know
Can
why.
I put it on?
Yeah, you can put it on.
Okay.
Yeah.
Do I have to move my seat over to here? That's what you're just telling me? Okay, we can do this. We can do this. I'm front over there by Joe right now, but that's okay. Okay, I'll go across the aisle. I'll go across the aisle and hang out on that side. I like that side. We keep it.
I'll wait for you to start.
I'm sure morning.
Lemon, your microphone, and we have these microphones here.
Okay, just having the microphones and them speaking back and forth. But if not, we'll go to the back and ask.
Perfect. And for the catch box.
We've got the catch box. Yes. What?
Is that a portable microphone?
Yeah, it's portable microphone. Yes. You haven't played the catch box before? So Tim says they want to go to the remember that.
Well, it's not like I've done this for 7 years. My issue is launching using the system.
On the script. That's real though. Oh, you can ask her. Well, it isn't yesterday. Well, not the same. Right. Oh man, that big change around. Yeah, that was what I got.
I did all the fly because they had it was like 18 cents.
Yeah. Don't worry about the microphone.
Okay. Just wanted to say welcome, everyone. It's top of the hour, so we're going to get started. Want to first off start by thanking our sponsors. We would not be here without them. And so once again, thank you to all of our sponsors. And then let me just move this forward. Hold on. Is it going to move it? Nope, it's not. Okay. Then, should this be moving forward here?
You need to make present.
Oh, take the presenter? Yeah, okay.
Yeah, go to the plus and
Make it the presenter? Fine.
yeah, LPC speaker.
Just a second here. While we're doing that, for that, I'll just go forward on this one, since I'm there. So I just want to remind everyone, we do have an anti-harassment policy. It's the same as you've seen before. If anyone has any questions, feel free to come up and speak to me or to any of the organizers. And then, oops, we're not on a break, we're about to start. Thank you very much. So let me just go and move the presentations over, and then I'll give the speaker over to Joseph. And so with that, we will be starting. And for those who are coming in virtually, if you want to ask a question or comment, please turn your camera on during the thing, and that is a signal for us to see that you want to ask a question. You can try raising your hand, but those signals get lost. We also have the chat, and you can put comments into the chat here, and we should be able to see them as well. And so with that, I will, let's see if I can make this a presenter. Okay. How come this isn't taking? You may be doing this on my laptop, you know. Tim, can you see if you can? I'm having troubles making this one a presenter with this laptop here. Ah, there it goes. Take presenter. There we go. Okay, it's sticky. So, hopefully now. Yeah. Yep, you got it. Thank you.
And just right and left arrow. Okay. Hi everybody, my name is Joe Salisbury. I'm a kernel engineer with Oracle. I'll be talking to you today about the maintenance that's involved with maintaining the 5.15 real-time patch set. I've been maintainer for the real-time patch set for about 2 years now. And real-time itself has been in development for, I don't know, 2 decades, 20 years now, so it's been going on for a while. But I'm fairly new, so they asked me to give a talk on what I did to learn to get up to speed and what the type of tools we use and processes we use to maintain the patch set. Okay, so here's a brief agenda of what I'll be talking about today, basically just to, why do we need a patch set? The different types of versions, how often we produce a new patch set. Give us some examples, because there's a lot of talk about the real-time patches, but many people don't even know what a real-time patch might look like or what it does. The various tools that we use to create the patches, and the types of testing and how the patches are distributed to the various vendors. Okay, so this is a quote from the Linux Foundation page, basically saying the goal of the project. So it was a collaborative project that was started to allow multiple companies to all work together to maintain the patch set going forward and perform development, stable releases while the patches were not in mainline as of yet, while they were still trying to get accepted into mainline. Several companies participate in the maintenance and the development of the patch set. There's a large community that participates by fixing patches, opening bug reports, the email list, an IRC channel. Okay. So why do we need a patch set? So the real-time patch set provides the logic that's needed to turn Linux into a real-time operating system. And that could be whatever distribution you're using, it turns that distribution into a real-time operating system. Minimizes the amount of kernel code that's not preemptive, and that's a quote from Paul McKinney from way back when, 2004, 2005, somewhere around there when the patches were first started to go into development. So real-time is partially available in mainline, and that's kind of a lie as of yesterday. So up until 6.12, the real-time logic has only partially been in mainline. Move back in case that's me. So merging of the patches in mainline started in about 2021 with the 5.15 iteration of the patches and that long-term stable release. And I posted a little link there, or the commit, the SHA one of the first patch that made it into mainline to get things moving. The last hurdle to date has been the print K logic, making that real-time compatible. So we have several versions. I guess I'll just talk through the static. It's not.
Sorry about that. You've got someone looking for it.
Adds a little bit of flair. Can you bring it back now? So there's a few versions of the patch set. Basically, there's a version of the patch set for every long-term stable release. So there's one going all the way back to 4.19, all the way through 6.6 right now. 6.11 until 6.11 was merged into mainline. That was the current development release. But as I mentioned not too long ago, and I won't steal all the thunder from Stephen Ron said, but 6.12 real time should be fully available in the kernel. And I'll leave those details to the other talks that are happening. So basically if there's a long-term stable release, there's a real-time patch set that can be used. So how often do we create a new patch set? So there's a new patch set. There's a new patch set every time there's a long-term stable release. But when I say a new version frequency, that is a new version of the main release. So a new version of 5.15, say, so 5.15 165. How often do we have like 5.15 156 or 157? The primary trigger is the upstream stable updates. So those that come down from whatever LTS kernel that the patch set's using. So a maintainer of the patch set monitors what the upstream updates regularly, and then the maintainer themselves decides how often they want to perform the update. A simple criteria is, at a minimum, we try to create a new version of the patches with the latest updates at least once a month. That way we don't get too far behind, because if anybody who's maintained stable releases, if you wait too long to apply stable updates, you end up having conflicts. And then if there's a lot of stable releases that are happening per month, we try to create a new patch set at least every 4 stable kernel releases that happen. Some other criteria outside of stable releases is if there's a critical CVE or a specific bug that's happening with the real-time patches themselves. So those are the two main criteria that we use. Okay, so like I mentioned earlier, so there's a lot of talk of the real-time patch set, but unless you've actually looked at the patches themselves, it may just be a blob that you apply and turns things real-time. So I just randomly picked a few of the patches. So the patches themselves, they affect many different areas of the kernel. So the scheduler, drivers, tools, things like that. And that's what will make it difficult to when real-time is maintained in the actual mainline kernel. Finding a maintainer will be a little different than the usual maintainers, because maintainers usually maintain specific subsystems or subsystems or specific files or chunks of code. But with real-time, it's really all over the kernel in many areas. So that might be something that's talked about this week is figuring out how to find a maintainer in mainline. So this first patch I showed as an example. It's actually patch 2. So these patches are from the 5.15 patch set. In that patch set, there's 180 patches. And that number generally goes up. It doesn't usually go down. What would make it go down is if the code that comprises of patches accepted into mainline, that would make it go down. But because this is a stable release, we don't really pull back any development code into the patches. We basically just apply the stable updates. And the patch count will go up specifically if there's a fix to one of the existing patches or a new patch that's created to fix a specific real-time bug, or like I mentioned, maybe a CVE fix or something of that nature. But the count usually stays pretty steady. This first patch is for the scheduler, and it's introduces a helper function migratable. And the reason for that patch is to allow the kernel to keep preemption enabled and to use migrate tasks instead. The second example is patch 20 out of the 180, and that's an EFI specific patch. And what that patch does is it disables the EFI runtime when you have real-time enabled, because there was some testing done with the EFI variables enabled, and it caused a very large amount of latency. It was in the order of like 10 microseconds, which in real time is pretty high. You want to keep things in the microseconds, not the milliseconds, in the millisecond range. So, 10 milliseconds, even 1 millisecond is pretty high. So, because the EFI functions were causing such a high latency, decision was made to disable them by default. And then some distributions might find that these functions are indeed needed, so they have the option to turn them back on. This third example is for a tool LockDep. And basically the patch goes through and it makes LockDep itself RT aware, so it changes the type of locking. So it introduces, with real time, there's a new type of spin lock in the standard kernel. So spin locks can't be put to sleep, but in real time you need to put spin locks to sleep. And so when you apply the real time patches, it turns the spin lock into a raw spin lock, and then the traditional spin lock is turned into a spin lock that can be put to sleep. And then this fourth example is just a driver patch. It's for the fiber channel over Ethernet, and it just goes through and it makes all of the driver functions and such aware of real time. So you can go through, you can download the patches and look and see. But this is basically a rough example of what they do in different areas of the kernel. And if anybody has any questions while I'm talking, feel free to just jump in, raise your hand, or ask the question. I tried to make the presentation a half hour, so to give 15 minutes at the end to ask questions. But a lot of times the talk can be guided directly from questions. So, all right, now we'll talk about there's two primary tools that are used by the upstream maintainers for the real-time patches. The first tool's a tool called the kernel uploader tool, or CUP, however, if you want to call it by its short name. It's a utility for accessing the kernel.org website. It's designed basically to only accept GPG signed uploads. So you have to have an account on kernel.org. You have to give kernel.org your public key. And then they go ahead and they give you access to various sections of kernel.org. So myself, I only have access to the location where the 5.15 patches are kept. So it prevents, it's just a way of locking down the website a little more. So it's a pretty easy tool to install. And there's a public Git repo. You can use, it's a Python tool, so you can just use the pip tool to install it. Some distributions actually have the kernel uploader packaged already, so you can use whatever the distribution's package tool is to install it. And like I was mentioning, so the kernel uploader can be used for many things other than just uploading new files and signing packages and such. So it's so as a kernel maintainer, you upload your packages and your files to kernel.org, but you really don't have SSH access to kernel.org to log in and perform any type of file operation. So the kernel uploader allows you to perform file operations like ls, move, remove, things like that. So once you upload a file, let's say you upload a file with by mistake, or you upload a file that needs to be removed, you use the kernel uploader to delete the file or remove the file. So yeah, so it basically gives you access to the kernel.org website to perform any type of administrative type tasks for your specific area and your specific files. The next tool is the SRT tool, I think. Oh, I skipped a slide by mistake, so kernel uploader. So the second tool is the SRT tool, stable RT tool. It was created by Daniel Wagner, and it's what we use primarily to do all of our patch creation, patch manipulation, things like that. It's also a Python tool. It's located hosted in GitHub, so you can get the source code if you want to look around at what it does, or it's pretty well documented. And then the last page of these slides, there's a references document that I created that has links to all of the GitHub documentation and the tools, the GitHub source and all of the various tool documentation. So SRT is pretty well documented, so you can go in if you'd like, and you can install SRT and try creating the patches yourself if you want. Pretty easy to install. You just clone the repo, and you use the pip tool again to install the Python tools. It does have one it has multiple it has Python as a dependency, but it has one outside dependency, the kernel uploader, because it uses, when you perform the various actions with SRT, it uses the kernel uploader to do the actual uploads and the file signing. Okay, so the SRT tool uses a configuration file, uses a couple of configuration files, but this is the primary user configuration file. And this is located in your, well, I guess it could vary based on distro, but in your .config srt.conf file. There's also one that's located in etc srt config. And I think that's more system-wide. I just use the local user copy, so I'm not sure if you have one in etc what that controls, if it's for every user on the system or not. So the configuration file is made up of multiple key value pairs. There's for example, there's a mail to, so when you create a new patch set, you send out an announcement saying that the patches are created, and you give locations to where the patches can be downloaded from, and et cetera. What you specify in this for this mail to key is where your email is going to go. Your sender is who the email comes from, and then your name. These other three chunks of key value pairs are the three real-time branches that exist in the real-time repository. So that's some of the things you provide in the file is your GPG key ID, the location of the Git tree on kernel.org, and then whatever local directory where you have your tree checked out for the work that's being done. And this is the other configuration file. It's basically a template. So this is when you create your patch set and you want to announce that a new patch set exists. You send an email, and it uses this template to generate the email that you send out. And if you look at it, basically substitutes the keys that come from your configuration file into this template file. And it just says, hello, I'm pleased to announce, blah, 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 and then it gives you your location. It substitutes all of the new versions you created for the actual email yourself. And when I run this, I just redirect it to a file, and then you can use MUT or whatever mail tool you use to send text type of files. Okay, so I'll go through a little bit of how SRT is run to create the actual patches. The first step is to identify if you need to create a new set of patches. And like I mentioned earlier, one of the primary triggers is the stable updates that come down from the upstream stable kernels. So this is for a 5.15 example. Basically, you go to where you have the real-time tree checked out. You do I do a git fetch all to get all of the tags and everything that's associated with that repo. And I specifically grep for, or list out the 515 tags. So in this little example, you can see it lists out the tags for the stable releases, and then you'll see a couple of tags that have a -RT77, a -RT78. So those are the tags that I created with the SRT tool previously that are in that tree. And you can see that there's a 515.164 and a 515.165 that don't have RT tags. What that tells me is that those stable releases are available, but there's not a patch set in my tree for those stable releases yet. So I at least need to either wait a little longer for another stable release or two to come through, or create a patch set for 515.165, for example. Okay, so the repository that you can clone for real time, it's basically two primary operations that are done to the repository when we're creating the patch set. There's a merge and a rebase, and the repository, each repository, so for every major version, so 5.15, 6.1, etc., they have 3 branches. So there's a branch that we use to merge the RT code into, and the merge branch could be used for things like, get bisect. So it basically keeps the patches in the commit order when they were applied. So this branch is used for things like, bisects, or if you want to create a custom kernel, things like that. The second branch is the rebase branch, and what a rebase is, when you do a rebase of the patches, it goes back to the last common commit of the branch you're rebase into and your current branch, and then it strips off the RT patches and then reapplies them later. So what it does is it makes it so the real-time patches are on the tip of that specific branch. And that allows it, then the SRT tool, it gives a way for the SRT tool to take those patches off and have them in order. And so after you do the rebase to a specific stable release, you'll see that the top, for 5.15 for example, you'll see the top 180 patches will be the real-time patches reapplied after the stable updates are rebased. And then there's a third branch called the next branch, and that's used primarily for not for stable updates, but for whenever there's a new real-time patch added to the tree. We use -next in our workflow to basically create the new patch, a real-time patch or patches, and then perform an announcement and allow the community and the various distributions to test out the release candidate to, because we're changing the real-time patches themselves, we want to give them a little leeway to make sure nothing's going wrong, which there's a higher probability with an update to the real-time patches themselves versus a stable update. So we usually we apply the updates to the next tree, we perform an announcement, and we usually wait a week or two till we hear back from the community to make sure there's no problems that are happening, no new bugs or things like that. So we know, do we have to roll this back, or can we use this release candidate? Yeah.
So how does the testing from the community, so you're waiting back from the community, who actually does the testing in the community for you?
I have a few slides forward. I have the kernelci.org does the test. I want to touch that. Kernelci.org does the testing, but the various community members, whether they be distributions or end users, they do whatever type of local testing that they see fit for themselves. So there might be specific types of testing that they perform based on their hardware or their implementation of real-time itself.
Okay, thanks.
Yeah. Okay, so that's the next tree. So this is just an example of how the stable updates are merged into the merge tree. So we identified what stable updates need to be merged in. So in this case, 515.165. And it's as simple as doing a git merge. And 99.9% of the time, well, no, I'm not going to say any statistics, because statistics can be wrong. Most of the time that the merge of the stable updates are clean. Sometimes there'll be conflicts, and if there is a conflict, then you resolve that conflict for whatever reason. I think I was the one making that buzzing noise now that I realize that there's every time my hand touches it. So yeah, so for the back people, now you know, if it's buzzing again, it's the person up here. Whoops. Okay, so after the stable updates are merged in, you use the SRT tool to perform, it takes various arguments, so SRT, and you put the after you install the SRT tool, you put it in your path or whatever. You do an SRT commit, and behind the scenes, the SRT tool is basically just doing a git add and a git commit in the appropriate branch. Then you do an SRT tag after you do the commit, and the tag is signed using your GPG key, and the tag creates, so in this case, it'll be V515.165-RT, whatever it is, 78, 79, or whatever the next release is that you're releasing, next specific version number that you're releasing. Okay, and the rebase is similar. It's just a different branch in the same repo. I generally do an interactive rebase. So I do a git rebase-I to whatever the stable release is going to be. Interactive rebase allows you to see the patches that are going to be applied, so you can make sure that you're not dropping one, or they're not getting placed out of order, which they generally shouldn't be. And similar to the merge, the rebase is generally clean. Sometimes there'd be conflicts. Usually, if there's going to be a conflict, you'll see it first in the merge. If you're running the merge step first, if you see a conflict in rebase and you didn't see the merge, then you know something's wrong, because they should be identical. Or they are identical, just the order of the time where the commits were applied. And similar to the merge, so after the rebase is done, an SRT commit's done. It does a git add, git commit, and then you perform an SRT tag, which signs your tag. Okay, so. Next step is, now that you're done with your git merge and your SRT merge and your rebase, you need to compare the two branches to make sure that they're identical. It's just an example of a command I run to make sure that there's no differences. If there is differences between the two branches, then you did something wrong, and you got to go back and look at things to see what you might have messed up. Okay, and now that we have two new branches, the next step is to create the actual patches. Now, the actual patch creation is done via the rebase branch, and the SRT tool is used again. So it's basically SRT create, and then you provide the previous real-time patch set version that currently exists on kernel.org in your tree, and then you provide the second argument is the actual version that you're creating now. So in my example, we created 165-RT79, and then under the covers, SRT tool is basically just doing a git format patch. So it's looking at the top 180 commits of your rebase branch and just doing a format patch on them and putting them in a local directory on your system. And then under that directory, after you do the SRT create, there will be a directory with all of the actual patches. So the patches directory with the 180 real-time patches. There'll be a compressed file of one super patch. So it's one patch that has all of the patch logic in one file. Some people need that for things. And then there'll be a tar file that contains all the individual patches. And this is what you end up uploading to kernel.org. Okay, so the next thing I do after the patches are created, I do some local testing before I do the upload. I do the first thing you always do when you change anything in the kernel is do a compile, a kernel build. It depends on what distribution you use, and I like to test at least Debian Ubuntu builds and the RHEL derivative type builds, since those are the main types of distros that are out there that are consuming the patches. After I ensure that the new kernel compiles, I do a boot test, and then I run some local tests on the same hardware every released. I usually run cyclic tests and compare it to the baseline for the previous release that I had. And this is all manual steps at this point before the upload, just to make sure that nothing major's changed since the last release. Okay, and then once all of my local testing's done and I'm pretty confident in the patches, the next step is to sign everything and upload everything to kernel.org. And this again is all done from the rebase tree. Use SRT to sign your files. So you provide the arguments of the last release that's on kernel.org, and then the next argument, the new version that you're creating. Once things are signed, you can use SRT to upload, and again, same arguments, repeating story. And then this is where the kernel uploader tool comes in. So it's used to actually pull all the new files from your local directory and then upload them to kernel.org. And then on kernel.org, if you've ever looked to where the patches are downloaded from, there's like a link for the latest and greatest patches, and I have the links in the references page, but there's a link for the latest and greatest patches, and then there's an older link which has all of the previous versions that were ever created. So the kernel uploader goes and it moves files around to put everything in the proper location for the new release. Okay, and then after the patches are uploaded, we just do a push of the merge tree. Just uploads the upstream repository that can be cloned. And then the push uses that configuration file that I showed earlier. It looks at the keys in there to know where it's going to upload, where it's going to push to, what your GPG key is, and the project Git tree. Okay, now that everything is uploaded and pushed, it's time to announce the new release. SRT uses the template I showed earlier to generate the email format, body of the email. It's the same example I'm using as before, but I got the version numbers different. But it's the same concept. SRT announce, and then the last old release that's on kernel.org, the new release you're creating, redirect it to a file, and then use an email tool to send the email to. Your configuration file will say where the email is going to. Okay, and I kind of already covered this. So the next branch is when there's updates to the real-time patches themselves, not the stable updates. It's similar to when there's a stable update, but we like to announce at least a week or two to the community to make sure that they can do some testing of the release candidates, that there's no new issues. And then once we find out that there's new issues and we can move forward, it's basically just do a fast forward of the next branch into your merge branch. And then you go through the other steps that I mentioned earlier. Okay, so there is some testing. This is to answer your question, Kate, that you asked earlier. So there's some manual testings that we do on the local side. Like I mentioned, there's a compile, a boot test, run cyclic test. Then there's some benchmark suites that are out there. There's RT test, there's RT eval. RT test is what contains the cyclic test, and it has a whole other bunch of tests in there. RT eval is, but with cyclic test, it runs without a load, so it's basically just checking latency on an idle system. So it's checking the latency on your code paths, things like that, schedule latency. The RT eval tool basically puts a load on the system while cyclic test is running, so you can have a loaded system measurement as well. In addition to whatever testing the maintainer and community does, there's automated testing that's done by kernelci.org. And I just put a little quote in there what their mission is. Their code's also hosted on GitHub. They have a dashboard that you can look at to monitor all of the tests of the new release that you just put out. And the advantage to kernelci.org is they have a variety of hardware and thousands and thousands of tests that are run against your new release. So when you upload a new release, it's picked up by kernelci.org and all of the tests are started. And as time goes on, I generally monitor these tests to make sure that there's always going to be failures in there, but as anybody who does testing knows, that there's test failures that is going to be a test failure, and if the test failure doesn't happen, then maybe there's a failure with my test failure. So monitor these tests, and usually if you see that there's something bad that's going on, you can check with the other maintainers to see if they're having a similar issue. And if, worst case scenario, we can always roll back to the previous real-time stable release, real-time patch release. But that very, very rarely happens. And then once the patches are uploaded and pushed, the way they're distributed is by this link right here. So like I mentioned, there's a link for the current version of the patches, and then there's an older link that has all of the previous version of the patches. There's also a Git repo that I recloned if you want to build your own custom kernel or tinker around with it or do some debugging at bisect or what have you. Okay, so conclusion, we've got like 10 minutes, almost 10 minutes left. So the real benefit of the real-time patch set collaboration was it showed that multiple companies can work together to maintain common code base until it gets merged into mainline, and it was really with the help of the Linux Foundation hosting and coordinating all of the activity. So like I mentioned earlier, so there was here's an example email. So this email was sent out by Sebastian probably about 2 weeks ago, and it was exciting because it sounded like, maybe real-time's going to get into mainline soon. And then as of yesterday, if you search LKML or whatever various mailing lists, you'll see that real-time is going to be in mainline, should be in mainline as of 6.12. And this is the various end-of-life dates for the stable releases, so there won't be any new stable patch sets coming out after 6.6 because, real-time will be a mainline, and 6.6 is last LTS, and most will, 4.19 is EOL this year, and then 5.4 is EOL next year, and then the rest will all EOL in 2026. And then that's it, and then real-time will be a mainline consideration and not require a patch set. And so that's it. Yeah, go ahead. I have a question. I know there's a spongy cube somewhere.
Hi. So the 100, less than 100 microsecond cyclic test thing, now how are we planning to measure that performance every time? Now that pre-imperative patches are into the mainline, now mainline is going to move forward with the configs and other things, like even if you change it.
Yes, right, yeah.
The cyclic tests are going to break the 100 millisecond rule that you have.
Yeah, that's a good point. Yeah, I don't know. Well, since it was just really accepted yesterday, you're right on top of it, right? So there's going to be there's more real-time talks and meetings this week. So that's definitely something we should bring up. So, yes, definitely the latency will change with it being in mainline, and that's probably something that will have to be measured moving forward. But yeah, I'm not sure as of yet. I don't think that's been really.
If there is any particular test that we can look in CI/CD that can ensure that the numbers are not changing drastically.
Yes, the CI/CD does run cyclic tests. They run out the whole real-time test suite. So Yeah, that's definitely somewhere where you could look.
And we are dropping ARC like old SOCs from RT, and we like in the recent discussions that has come out, things are all moved to mainline now. There are no separate branches for ARM32 and 32-bit ARM. So how are we supposed to maintain those patches ourselves? Like if we have SOCs based on ARM32-bit thing, and the workflow that you described, will that be helpful? Like there are some 3 to 4 major patches which are not being considered for mainline merging.
Yeah, I mean after real-times in mainline, the SRT tool is not going to go away, so that could be used for maintaining patches outside of mainline still. I don't think there's no group or project assigned yet to maintain any new patches post 612. But yeah,
If you have the interest, you get to maintain it.
We're looking for a new project now that real-time's coming to an end, right? Linux Foundation can definitely help.
It's more along the lines of Thomas was looking for volunteers to be testing things so that things could go upstream, and there wasn't anyone volunteering.
Okay.
Okay? So.
Hi, one of the things you said right at the beginning was that the real-time patches affect places all over the kernel. So as part of the testing, do you actually do any kind of, I guess, interference testing to see whether behavior in particular subsystems in the kernel has an impact on the real-time behavior?
Yeah, I don't do anything, or I'm not sure the maintainers do anything specifically for like interfering type testing, but CI/CD, at kernelci.org, they may do something of that sort. But the way to look at it is if you're applying the real-time patch set, there's going to be, if there's interference, that it's, due to the real-time patches, and, you have to investigate that. But
I was more thinking the other way around, whether, changes in particular subsystems
might
have an impact on the real-time behavior.
That's true too, yeah. Other than, I guess those changes would come in. So with these patches, we only apply stable updates, so we don't apply any new features and things like that. So usually you'll see the difference, from going from 5.15.168 to 5.15.169, for example, and then okay, that the change in latency is happened due to a commit that's between those two versions, and you could do something like a bisect or something like that. But basically, cyclic test is the core test that's run to. And the thing with real-time is you have to make sure that you consistently use the same hardware and the same environment and same setup every single time you do testing, or the latency can change. Something simple as like a BIOS version change can affect your latency. So.
Well, I guess now it's in mainline, then you could do that kind of testing and see whether each change has an impact.
Yeah. And that's another opportunity for a new project, right? Yeah.
Is there any specific project or team working on power management and real time?
Power management?
Yeah, like we generally disable power management when we want to do RT.
Right.
But looking at the product segments today, they both needs to coexist. Like RT is solving different problem of latency and things, but power management is also important, right?
Right. Yeah.
We want RT and power to coexist, but in general, we used to always disable power management in RT.
Yeah, there's no real team or project that I know of that's assigned to that. Maybe something individual companies are doing that on their own, but nobody upstream is really specifically. There's no real project that's specifically looking at that I know of.
Okay.
So about the power management, I think one of the things happening for the upstream was to allow the preampt RT, but then you lose the cluster idle states in the ARM64 if you speak about the ARM platform. And this is being worked by Wolf, I think now, and such restriction is being removed. So when you have the preampt RT on the upstream kernel, you will have the ability to go to the deep CPU cluster states. But I think the work is still not finished because the power management uses spin locks, and we all know that there's a clash here. but there are people working on it.
Okay, yeah, I think we're eating into Julia's time. Okay, thanks everybody. Just feel free to, email me, reach out, whatever, if you have any additional questions, and look at the references slide to follow up.
Thank you.
Thanks.
Okay. Hello? Do you hear me? Hello? Do you hear me like that? Okay. Is it okay like that? Yes? Not great? Okay, is it better like that? Okay, great. Okay, so I'm going to talk about program verification for the Linux kernel, potential costs and benefits. What's going on now? Oh, I'm touching that thing.
Don't touch that. Apparently that is the problem.
No, not like it.
Not
Just
there.
okay.
Yep.
Okay. So the Linux kernel, so it's a big system, we're all familiar with it. It seems reliable. Many of you may have servers that have been running for the last 5 years or something like that. But actually, at the same time, it's kind of a contradiction. Actually, it's full of bugs. You look at any part of the kernel, someone was mentioning this earlier this morning at the developer keynote, you look at any part of the kernel and you can find a bug with a little bit of study. So some of these bugs fit well-known patterns, so things like buffer overflows, dereference of null, and so on. And these are today all rather well covered by various kinds of tools, SMATch, CoxNL, specific compiler options, and so on. On the other hand, sorry, I'm not really getting the concept of how you switch from one slide to the next.
It's a bit sticky, that keyboard, so just press firmly for a minute.
Okay. On the other hand, some kinds of bugs are, yeah. I want to go to the next one.
Oh, you want back? Okay.
No, I want to, okay. Sorry. On the other hand, some kinds of bugs depend on the algorithm. So you have some function, it's supposed to do something, it actually just does something else, and none of these generic tools are going to help you find that issue. So what we are interested in is considering whether formal verification can be useful to help to address this problem. So what is formal verification? So the basic idea is that the developer or somebody can write specifications, some kind of formal notation that describes what the function is supposed to do, and then tools can be used to check that the specification actually matches what the source code does. And then one can scale up. You may have several functions. They may have each their own specifications. You can check that they're all consistent with each other, and then get some kind of complete description of how your software is actually behaving. So basically, you can think of specifications as sort of a form of tool of documentation, but it's not documentation written in the English language, it's documentation written in some formal language, and the benefit is that you have some kind of tool support to understand check things, understand the relationship between things. So the positive aspects, one of the positive aspects is just, I mean, I've emphasized already the tool support aspect, but also just the idea of forcing you to think about your code in a different way and thinking about what you want it to do and seeing if it actually is doing that. And then once you have these specifications, then they are also, in contrast to the documentation you write using English language, they're also completely unambiguous, and other people who are not familiar with the code base can study them later on and understand what's going on. On the other hand, there's a downside. If anyone has ever tried to do formal verification of any code at all, you know quickly writing these specifications is very hard. And actually, we're kind of targeting the space where we are not exactly sure what the function is doing. And so writing a specification of what the function does when you're not completely sure to understand everything is even more complicated. Another issue is that in the case of the Linux kernel, it's a live piece of software. It's going to change all the time. We have worked really hard to get our specifications to be in the perfect way, and then some foolish person has realized that actually your function can be called in some other context, and then you need to update the code in some way, and then you have to update your specifications, because the specifications, again, they're describing exactly what the code does. When the code changes, you might have to change everything. And this maintenance, like who is going to do this maintenance? So we might hire a verification engineer to write the original specification. If we make a one-line change, are we going to call him up and ask him to update the specifications? Maybe is there any hope that developers can do that themselves? I don't know. We can think about that. And there's no magic bullet. If you write a specification that describes the wrong thing, then you can verify that your code does what the specification does, but it won't necessarily be actually what you had in your head that the function was supposed to be doing. So it kind of formalizes things, makes things precisely defined, but it's not a perfect assurance that your code is perfectly correct. So in this talk is intended to be not a order that you should go out and follow this methodology that I'm going to describe. It's more of a thought experiment. So I don't want you to say, oh, you know, this is like a real nuisance. I don't want to go out and, now that I've been working on my code, I don't want to have to go out and write formulas. So just don't think so much about the burden that this is going to add to the developer. The point at this point is just to think about what kind of benefits could we get from it. If we feel like we could get some benefits from it, then maybe we can make some tools afterwards that will greatly reduce the burden on the developer, maybe. So here's a simple example. This is inspired by a talk from last year at Linux Lund, a very nice small Linux conference in Sweden. Some of people in the audience would enjoy if you come and attend that. So this is a swap function. Swap takes two arguments. They're both pointers, and it is going to dereference those arguments, and it is going to take the value from one and put it into the other, and vice versa. So very simple function. There's some things we might like to verify. We might like to verify that our incoming pointers are actually valid pointers. They're not null pointers, for example, that they are actually pointing in memory that's can be written. They're not pointing into some constant space. And then we would also like to verify that if we get these kind of pointers that we expect, that the values will actually end up being swapped in the end. So we're going to do this verification using a tool called Pharmacy. And Pharmacy is an automatic tool for doing verification. Basically, the developer or the user has to write the specifications, and then Pharmacy is going to take care of the issues of figuring out what the C code does. So the specifications basically describe the state on the way in and describe the state that should be achieved at the end. And the specific statements in your function are going to determine the conditions under which you actually achieve your goal. So Pharmacy takes care of analyzing all those statements and figuring out what conditions have to be checked. And then it relies on SNP solvers to do all of the checking. So except for writing the specifications, everything should be automatic. So in some sense, that's good news. So here is the pre and post conditions, the specifications that we want to write. First, we have our preconditions. What are the situations in which we can call this function? One of them, as I mentioned, we have our pointers. You have to ensure that our pointers are readable and writable. So that's what we see here. Requires is the Pharmacy notation for specifying this is a precondition. This is a property that is required to hold on when we call the function. And we just want that to be ensured that these two pointers are valid pointers, meaning that they can be both read and written. And then the other issue is to actually ensure that we have the right behavior, that we're swapping the values. Now we say ensures. Ensures is the keyword. This is a post condition. This is describing the state as we should have it as we want to reach the end of the function. And we want to ensure, a nice thing about this whole verification process is this is something that's done statically. It's not done at the execution. And so you can actually refer to the values of variables at different points in time. So we want to say the value that P is storing at the end is equivalent to the value that Q was storing at the beginning. So we have this old keyword. It says, give us the old value. And you can actually refer to the values at any point in the function definition. So we have this ensures for the post condition for P, and we have another one here for Q. So now we're all done, or almost all done. Pharmacy also wants to know about the side effects, so we have side effects to P and Q also. Here is our complete specification for the swap function. We just push the button, drop this into Pharmacy, and basically 1 second later it will tell us everything is good. So now we know that our swap function satisfies the specifications that we provided for it. Okay, so we want to do something a bit more interesting, so we targeted some functions in the Linux task scheduler. We're just going to focus on one function in this talk. It's called should we balance. Basically, what we're going to do is we will focus on a particular function, but that function might be referring to other functions, macros, data structures, and stuff like that. We have to go around and collect all of that information. Those other functions, they might be kind of somehow lower in the abstraction hierarchy of the Linux kernel. When you look at some of these called functions, unfold them a bit, eventually you get to assembly language, you get to some strange bit operations that you might not want to have to think about in your verification process. So we're just thinking about our particular function. For those other functions, we can just put their prototypes and put what we expect that their behavior will be. If we'd like, we can verify that at some time in the future, but that's not the point of this particular experiment. And as I said, we use Pharmacy for proving. We are also, again, just focusing on the algorithm. We are not focusing on concurrency issues. We're not focusing on strange pointer dereferences. Those are definitely important problems, but that's kind of the unique thing about what we're doing here is that we can actually focus on what the function is doing, what its algorithm is trying to implement. So we leave those other things to other tools. Okay, so the function we're interested in is called should we balance. This is a function which is part of the load balancer of the Linux kernel. Basically, different CPUs will be invoking the load balancer. Many of them may be invoking the load balancer basically at the same time, and it's not really desirable for multiple CPUs be trying to steal work from other CPUs at the same time, because they will all have access to the same information, and they will thus all likely try to steal the same tasks. So what should we balance does is basically just, it's like a gatekeeper. It sees if this current CPU is currently allowed to do load balancing. It's just going to return true or false in the end. So the history of this function, it was first proposed in August 2013. It was actually just a function that was refactored out of code in other functions. And a kind of interesting thing is in doing this refactoring process is basically some copy-paste of some scattered lines. People introduced a bug. So it's whenever you introduce something new, have a new change of algorithm, something like that, that's where bugs are likely to appear. And these kind of semantic bugs, not necessarily the kinds of bugs that null pointer dereferences and so on. The patch was, the function was first appeared in a release in Linux 3.12, and actually the bug that is in the initial version was found very quickly, and so the initial release version was not containing the bug. And then the function has changed a bit over time. It doesn't change like every day, but there have been basically 10 different variants of the function over the last 10 years. Okay, so I'm just going to first start with an overview of the code in words. It's not that complicated of a function, but it's written in a bit strange way, so it's a bit easier to understand it from words. Basically, we have our inputs, which is the CPU, which is trying to steal, and we have some other information about the other, basically the state of the machine, the set of CPUs that we're allowed to steal from, for example. And the action, it's a two-stage process. Basically, what the should we balance function is going to do, it's going to try to elect the CPU which is allowed to do the balancing, and then after we have elected that one, then we see if the CPU that's calling the function is actually the one that won the election. So basically the idea of this election process is deterministic. If we have a bunch of CPUs that are calling this function, they will be doing that concurrently with no interaction between them, but they will all elect the same one, and so we will only get one out the other side. Basically, we would like to elect one that is idle, because if you steal and you put work on an idle CPU, then that work will get to run immediately, so that's desirable. But if we don't find an idle one, then we just allow another one that's chosen in a deterministic way to be able to do the stealing. So here's the actual code. It's not a huge function, but it does have a bunch of ifs, it has a bunch of loops, it has some strange breaks and continues. It's not completely easy to see what it's doing. So it has various parts. We have our inputs, which are the environment, which is a CPU that is asking for load balancing, what are the CPUs it can steal from. Then it has a condition. This special condition is if the CPU is newly idle, if it was like working along doing something, but that process has ended, then it is always allowed to steal. If you keep your CPU active, then it will be able to stay at a high frequency with DVFS, so it's desirable to get some work there immediately. Otherwise, we go into this election process that I described. So again, we have the two parts. The first part is the loop. In the loop, we iterate over the cores from core number 0 up to the maximum one, and we see if a core is somehow a desirable one based on some masks. But the idea is basically we iterate from 0 up to the maximum, and we search, do we find an idle one? And then as soon as we find an idle one, then we store that in the variable balance CPU, who's the winner of the election, and we exit from the loop. And if we never find an idle one, then we get to the bottom of the loop, and this variable is still -1, and then we just return, we elect some random value in a deterministic way. And then the last step is to check if the elected relationship between the elected one and the CPU that's trying to run the function. And here you can see the problem. It returns true when the elected one is different from the CPU that's running the function. So actually, all of the CPUs on the machine would decide to do load balancing at the same time, except the one that we chose for load balancing. So that was not very good, but the fix is quite simple. We just changed not equals to equals. So we have pre and post conditions. So first, there's a bunch of things that I don't show up here at the top. These are checking the validity of the various pointer arguments. Those are actually in practice quite hard to do, but they are not super interesting to look at. So what I'm going to show instead are the pre and post conditions. So we have another construct of Framecy, which is illustrated here, which is a behavior. So basically the idea is when I describe the algorithm, there's different situations in which we can call this function, and the function is going to behave different ways in those different situations, and each one of them corresponds to a different behavior. So the first behavior is when the invoking CPU is newly idle. The second behavior is when there is some idle CPU and we are able to elect one, and the third behavior is when there is no idle CPU and we have to use the default definition. So these are the pre and post conditions for the function. Unfortunately, there's a small detail of program verification, which is it's not very good at working on loops. So as I mentioned, FRAMAC is going to go through, it's going to look at our specifications, and it's going to go through the statements in the function one by one and see what's the relationship between the execution of those statements and the formula that we're trying to figure out. But if we have a loop, we don't know what is the actual sequence of statements that will be executed, because you do the top part and then you might go around the loop 25 times or 150 times, so we don't know. There's no way the FRAMAC can figure that out. And so what we do instead is, instead of having to figure out how many times we go around the loop, the user has to write what's called a loop invariant, and so that describes some property that's true every time we go around the loop. And so then we can just kind of jump over the loop and use that invariant information to figure out how to continue. So here the loop invariant is not that complicated. Basically, we have the idea that we have this loop index. It's going to move through the list of possible CPUs, and all of the CPUs that have been checked so far are not idle. If they had been idle, we would have left a loop. So by definition, all of the ones we've seen so far are not idle. And so that's just this line here. The other information is some information that's necessary. We need to know about the side effects of the loop, and we also need to ensure that the loop is going to terminate. But the interesting part is how we get around each iteration. So now we have our loop invariants. We have our pre and post conditions. We have our loop invariants. We are completely done with everything we need to write for our specifications, and we can run FRAMAC, and it says yes in about 1 minute. And so when I did this initial experiment, I had not very much experience with FRAMAC, and this took maybe a couple days to get it right. So it's not completely trivial. It's not completely difficult. With some experience now, I could probably have gotten through that more quickly. The problem, of course, is that that's just the initial version of the function, and as I mentioned, there have been lots of other variants of the function since then. You can see that they do different things. Some of them are quite simple, replacing not equals by equals. That's one character that changes, but it's actually converts from buggy version to correct version. Some things are like replacing function names. Those are quite simple to deal with. And we'll see some of them actually get a bit more complicated. So I'll go through some of these changes, and we can see what are the impact on these specifications. So the question is, as the code changes, how much work basically is it going to be to update these specifications? We do have one point which is in our favor, and that is that if we don't have any loops, at least the pre and post conditions are describing the situation at the beginning of the function, the situation at the end of the function, and so if our input-output behavior stays the same, if we just do some refactoring or some optimization along the way, then if the input and output values stay the same, then our pre and post conditions should stay the same, and FRAMAC will take care of adapting to the new structure of the code. So there's some hope that we have no work to do at all, but as we saw, there can be some changes that happen, for example, to fix the bug that was in the initial version, and there's no magic bullet. If you're going to fix a bug, obviously you're going to change the input-output behavior, you're going to have to change the specifications. So I'll go through kind of for the good cases and moving on to the less good cases. There are some changes that have actually no impact at all. So one of the changes is somebody cleaned up all the comments. They turned lowercase CPU into uppercase CPU, and some other similar readability fixes. So obviously that has no impact on the verification, so you feel very productive. You get through your variant without any work at all. But something a bit more interesting here, somebody actually does an interesting refactoring of the code, but this has no impact on the input and output behavior. So basically the idea is, I mentioned that there's two parts to the election. If we succeed here in the initial loop, if we find something, then some developer realized we don't have to store it in a balanced CPU variable and test that variable afterwards. We already have enough information, we can just leave the loop with the answer that we would have gotten anyway. So again, no changes in the input-output behavior. We just push the button and Framacy is happy. So that's great. Another issue that has arisen is that somebody realized that this function could be called in some circumstances that are different than the ones that was initially anticipated. So here the condition that is being under consideration is that actually this load balancing can happen as part of handling an interrupt, and in parallel we can be doing other things on the machine. In particular, we can be hot plugging CPUs, and so it will not be desirable to load balance work onto a CPU that is about to disappear. So this is handled in the code very simply by just adding an if statement at the top of the function. And it's handled fairly simply in the specification as well, because we have a new behavior. This kind of shows the advantage of breaking these things down into the different behaviors. You can just focus on your particular behavior that you're working on at the moment. We have a new behavior for this situation, but unfortunately it has the property that there's no like if then else in our specification language. So if we add a behavior for a new condition, we have to update all the other behaviors to say that that new condition does not hold. But at least the change is kind of, I mean, it's the same change in most cases. One can kind of get the feel for this is the kind of thing one has to do. So I would say it's a little bit of work, but not too complex. On the other hand, there can be much more intrusive changes that have happened in this function. So at some point somebody thought it would be a good idea to take hyperthreads into account. So hyperthread is like a logical CPU. Basically the scheduler is seeing logical CPUs, but several logical CPUs may be implemented on a single physical CPU to take pipelining into account. It will benefit better from pipelining. But unfortunately that, gives you a bit more performance, but it doesn't scale perfectly. And so if you are going to steal work onto a CPU, it might be advantageous to steal work onto a CPU where all of the hyperthreads are idle. Then it will run as fast as possible and it will not annoy other tasks that are running on hyperthreads. So we would like to do that. One way we could do that is we could search through all the cores to find one that is completely idle in this sense, and then we could search through the CPUs, all the CPUs again if we don't find one, and find one that was idle in the way we were looking at before, just looking at the CPU, logical CPU itself. But having two iterations over all the CPUs might seem to be a bit expensive, so they had the idea, you have just one iteration, and you keep this variable which is called idle SMT, and that's going to be our fallback. That's a CPU that it's idle, but some of its hyperthreads are not idle. And if we never find a fully idle CPU, then we will fall back to this idle SMT one. So the logic has gotten a bit more complicated. And so this actually also has an impact inside of a loop. Whenever you work on verification, anything inside of a loop is much more frightening than things outside of loops because you have to update these loop invariants. So that's what we had to do here. So previously I emphasized that there was just like one line that's interesting in the loop invariant. This one here, which is saying among the CPUs that we've looked at so far, they are all not idle. Now inside of our loop we have this if, it's like a little state machine. We have to see, has idle SMT been initialized already? Has it not been initialized? What is the properties of the idle SMT thing if it has been initialized? So there's a lot more information that we have to keep track of. So here we have a sort of slightly complicated change, and maybe kind of a big complexity. It's kind of a curve like the exponential curve like this in the complexity of the changes that are needed to the specifications. And then in a quite recent version, people decided to be even more efficient. So these hyperthreads have the property that they are all sort of like an equivalence class. So if 3 and 5 if 5 is a hyperthread of 3, then 3 is a hyperthread of 5. And so once we have checked one CPU, then we have actually checked all of its hyperthreads for idleness. There's no point to check them for idleness again, and so we can remove them from the list of things that we are iterating over. So in general, this idea of we're doing our nice iteration over some things, but now we're going to remove some future things. I don't know, maybe you can appreciate that this is a bit of a complex thing to think about. And so unfortunately, for the thing that I am trying to put forward, this took us like 3 months of effort to figure out how to make it work. So it really kind of undermines my talk, but I hope that maybe we can improve things and get experience and learn about good methodologies for dealing with these kinds of issues, and maybe thus reduce the working time. On the other hand, on the upside, there is a bug in this version. This optimization was not done completely correctly, and we have actually go back to the case where there's not exactly one unique CPU that is going to be allowed to do a load balancing. Now there can be 2 CPUs that are allowed to be doing load balancing in some cases. We can actually see the bug in these invariants that we are able to prove. Okay, so I don't really expect you to study all up on these invariants here, but in the old version, you can see here in the red part there is a here we have an if and only if, so we give a true result if and only if our CPU of interest is the one that we have elected. And if you look at the bottom, there is no more if and only if. It works one way, but it doesn't work the other way, because sometimes there's 2 CPUs, as I mentioned. And if we study up on the code, again, this is a bit complex. There's a single if condition that's not testing the right thing in the fall-through case, and it's allowing, on a failure to match the election, allows you to just try another case as well. So basically, we have our assessment here. Here we have our list of our changes as we saw before. So basically, changes 1 through 7 were quite easy to verify. So some of them a few minutes of work, some maybe 20 minutes, not maybe a couple days of work to do actually all of them, and with not that much experience with the tools either. And then on the other hand, the last 2 changes were much more complex. Just taking into account hyperthreads took about 1 day of work, and then, as I mentioned, doing this excessive optimization based on the hyperthreads took months of work. Kind of an issue is that these SMT solvers are basically SMT solving is like you have some knowledge and then you infer things from that knowledge, and so you just expand and expand and expand your knowledge base, and then you try to see if the thing that you're trying to prove is actually somewhere in the knowledge base. So it's a huge search space, and you're just trying to search in that space. If it can't find the thing that it's trying to prove, it's very rare that it will actually tell you this thing is wrong. Most of the time it will just say, I don't know. It will just work and work and work, however much time you allow it to work, and then it says, I don't know in the end. So it's hard to get really good feedback. If you write a specification that's incorrect, it will often just run for a long amount of time, and then you'll have no information whatsoever. So that's really a bottleneck in getting these things to actually find the right thing. So going forward, obviously we would like to work on some more functions. At this point we have worked on one other function, which is select idle core, which is also part of the scheduler and also has a similar behavior where we're searching through cores to find a suitable one. Our key observation so far is that simple changes in the code lead to simple changes in the specifications, but slightly complex changes in the code lead to very complicated changes in the specifications. So maybe expectations have to be adjusted accordingly. We have also been thinking about some tools that can help in this sort of work. One of them is just like the question of what do we want to verify. If you want to focus on one particular function, you probably don't want to take the entire file, the entire Linux kernel, anything like that. So we have already made a tool that will just take that function, find all of its dependencies, and give you one little file that compiles and is a complete specification for that function. So that aids a lot in doing experiments. Another thing is tool that would be potentially useful is to aid in writing these specifications. So there's sort of two parts of that. One of them is getting all these declarations associated with your pointers to be in the right shape, and one of them is figuring out what your function actually is doing and trying to express that. Often figuring out what your function is doing and trying to express that is not that hard, and doing all of this alias analysis to figure out which pointers might be sharing with which other ones is much more complicated. But it's something that's quite easy for tools to do, so maybe some kind of tool based on LLVM, which is already doing alias analysis, could be helpful in that direction. And also another issue is the loops in the Linux kernel. The Linux kernel has various iteration operators that are defined as various complicated macros. In this talk we saw CPU for each CPU and that just starts from 0 and goes to the end. That's fairly simple as an iterator. But there's in the select idle core that we looked at, it uses for each CPU wrap. And wrap starts in the middle of the set of CPUs and goes to the end and goes around. And describing this goes to the end and goes around adds a lot more complexity. So it could be possible to make some kind of templates for different kind of loop iterators, and then you could just insert the actual behavior of the loop and it would figure out all of the rest about the iteration process. Another issue is how can we help to react to code changes? Ideally we would have a tool that would just update the specifications. That might be a bit much to ask for, but it could be interesting to have a tool that provides some hints just to help identify, is this a change that's easy to deal with? Is this a change that's hard to deal with? Might actually help the user in terms of expectations. And another issue is if you're not able to prove the thing you expected to prove, maybe you need to update it in some way, then maybe that indicates a bug in your source code. How can you identify what kind of bug it is and actually make the connection between the update in the specification and the source code? And so everything that I've presented in this talk is available online if you want to see the actual proofs. So thank you very much. Yes. Luis, but does someone have the microphone for him?
That's a great talk.
Thank you.
How do you handle compound logic statements? Is Wentao here? He pointed out. He's online, yeah. Okay, so we're working on MCDC coverage with LLVM code. CPU ID, for example, has like 47 compound logic statements. So that's 2 to the 47th to actually test that. Do you have to do invariants for that too? I mean, how do you prove something like that?
So I'm not sure to understand, what do you mean by compound logic? You mean just lots of ifs?
A, B, or C, just a very long compound logic string.
Yeah, I don't do that. The SMT solver does that.
Great answer.
No, the SMT solver does that. So if it has difficulty, like if you all have difficulty, I can imagine you have some kind of complexity issues. So the SMT solver will get very slow if it has some complexity issues, but I don't touch that. I just wait. I get some coffee or I do some other work. This is something you have to learn to, parallel process.
Okay.
Luis has behind you actually. There's a question. Yeah.
Does the language under analysis change things? I'm implying basically, would things be easier if you do an analysis on Rust code?
Yeah. So that's an excellent question. So when we were doing this thing that took 3 months. Yes, we got very, very enthusiastic about Rust. We thought Rust was a great language and everything. So yeah, I think it could definitely help guide you. I mean, you have the mutability annotation, so that guides you. I think it can guide you in writing some of these specifications, which are really very about the pointers, which are very hard. And it can also guide you in knowing that you don't have to write those specifications because there's no mutability that's possible in some cases. Basically, we have, you might have two data structures. They might have the same type. One of them is modified, one of them is not. And so here we have A, which is modified, B that's not modified. And basically, you have to say separated. So you have to declare to the tool that these things are not pointers to each other. Otherwise, you will lose any information. You will lose all your information about this one when you have any changes to the other one.
Is there a target that you think that might be good, to try to test to see improve if this would actually be much easier in mind? And if not, I guess we can think of something.
So your question is, have I found some Rust function that I should be working on? So yeah, no, I haven't done that.
Okay, got it.
There are definitely people working on verification for Rust. I'm not sure if they're working on this kind of actual behavior of the functions. People are often working on verifying the verifier or verifying some issues related to concurrency, things like that.
I have a question.
Yes.
Do you plan to apply that approach to the Linux kernel in a wide way, to at least the same level of complexity?
Yeah, so my hope or dream or something like that. Actually, I've spent, if you by any chance attended my talk at the tracing microconference last year, there's a thing I don't really understand about the load balancer. So I'm hoping that after many long efforts of tracing and looking at the code and so on, maybe if I try to verify it, maybe then I will maybe everything will become clear. So I would like to do the entire load balancer. And another thing that could be interesting to do is select idle sibling, the code that decides where do you put tasks when you wake them up. That has undergone similar kind of occasional evolutions, and there have been very strange, silly bugs in the past, like a variable that, it's an integer variable and they use the wrong integer variables, things like that. So it seems like verification could have been useful in that case as well. I'm not sure I'm ambitious enough to do the entire Linux kernel. That seems a bit much. There's a question kind of behind the pillar, if you can get it back there.
I am wondering, as someone who's tried to do the occasional formal spec in the past myself, it looks much better than many previous implemented formal spec systems because you don't need your own special keyboard with weird symbols and that sort of thing. But I'm wondering how much of the benefit here comes from simply being forced to write the spec, forcing you to read the code very carefully and think through the consequences of what it does, as opposed to anything the actual SMTs.
Yeah, no, I get your point definitely. And we found a bug using, in doing this work, we found a bug, and we submitted the bug, and it was accepted and all that. But I can't say that we found the bug using the verification. We found the bug trying to think about what are all the pathways we can get through this function and what they do. Are they actually doing what we assume this function is supposed to do? So I can't say that the verification, like as you say, running the SMT solver didn't find the bug for us. It will never find bugs. Basically, SMT solvers only tell you when things work. On the other hand, you did find this one bug, but there could be another bug. And so it does give you the happy feeling that you have actually fully correctly characterized your code. So I think there's some value to going through the whole process and not just pretending you're going to do it and just doing the thought part. Philippe?
Thanks, Julia. Great talk. How should we teach about writing specifications, and how early do you think? Because there's a lot of complexity in what you did.
Yeah.
Right. So how, who can write the specification, and can we expect that everybody should be able to do it?
Yeah, maybe we could hope that in the future. I mean, I don't actually teach this, so I don't have to think about this issue, but I've heard about other people who have some kind of basic functional programming course. So even if you're not familiar with functional programming allows you to express things in quite a high level, and so you end up with quite simple looking functions and that do a little bit complicated things. So it's more than you can do, and like you can do 3 lines of functional language and you might get something a bit more interesting than you might have 3 lines of C. So it's kind of a good situation in which to start doing that. So I know people who have taught functional programming and formal verification at the same time. So second year course, maybe something like that. Yeah, I don't know. You can kind of sell it as good programming practice. You think about documenting your code and making test cases for your code and writing specifications for your code and actually writing your code. All of these things can somehow flow together. Is there a question up here? Sorry.
I also have a question. Sorry. This is maybe more philosophical, but I'm assuming, and pulling together a few ideas that were stated, but I'm assuming there's a correlation between the human has potentially made an error in expressing the logic of the function, and this function is difficult, and the formal verification statements are difficult to express. So if it's difficult to express formally, the chances of the human writing the code, making a bug, is potentially higher. And then you would also mention the idea of having, so that's the first idea. The second sort of piece is you had mentioned the idea of having a tool that says for patches that come in, whether this change would be potentially difficult to express in formally. And then the third piece is the utility of writing the actual specification in terms of making sure the code is correct, and sort of putting all of these things together. I was wondering if even just having that tool that you said, this is tricky to express formally or not, would give you an indication of you should probably look closely at this code. Even if you're not going to formally analyze it, that it's possible that the chances of you making an error in writing this code is very high. That could be an interesting.
Yeah, I think that's really an excellent point, which is that if it's easy to see how to extend the specifications, maybe it's an easy change and no one needs to think about it. But as I showed in the table with this table here, whenever there was a complicated change, then it took us a lot of work to do the verification, but there was also a bug. So I don't know if we can generalize from just the history of one function, but I think there's some promise in what you're suggesting, yeah. There was another question up here.
This is probably the last one now.
Okay, thank you.
So you write the specification for the preconditions of the function. Would that allow to verify that all the callers are respecting the preconditions?
Yeah, so that gives you the information about what should be respected, and then you have to go work on the verification of those callers to ensure that they're calling the function the right way.
So it can be proved automatically if the callers respect my preconditions when calling my function?
Yes, so you have a function A, and you've worked very hard on making your specifications for A, and now function B is going to call function A. Yep. So you may need to write some specifications for B also, and then you can just drop it all in the tool.
So I would feel like I don't need to write any specification for function B to prove that. Yeah, because it may depend on its own preconditions.
Yeah, it depends. So if you have a pointer that comes into B, and then that pointer gets passed off to A, and A wants to be sure that it's a valid pointer, that it can be dereferenced, for example, then on B you are going to have to also write your preconditions to say that it's a valid pointer. It has to be able to know that too. So you have to write some preconditions.
Yeah, right. Thank you.
We're over, but if it's quick, and then
Okay, so
this is the last question.
Okay, one last question. So I really agree that we should encode precondition, postcondition for some really important components, but sometimes our specification could not be complete because developer they just forgot to encode something. So in this case, our verification is not complete either. We don't know the software is correct or not. So can we make some automatic tool to hint developer something is missing? And another question is, so verification can also be wrong. Like we translate the source code to verification condition. What if this is wrong? And what if SMT solvers is wrong? So how can we know the code is really correct even after verification?
Okay, so let me try to answer these quickly. Your first question, how do you know if it's complete or not? So definitely there is a space of precision that you can use in specifying things. But on the other hand, like you have your behaviors, and Pharmacy, I didn't emphasize it, it will check automatically for you if your behaviors are complete and if they're disjoint. So if you put those annotations there, it will actually check that you have considered all possible input conditions. So you get some help in that direction. Another issue is loop invariants. Loop invariants are kind of really forced to be like the loop code because they're like on the way in, and then as you go around, and so somehow that loop that brings you around kind of forces you to really be describing carefully what's going on inside the loop. So there is some help in that direction. But I agree, it's not a perfect thing, definitely. Your second question, I've forgotten already, but say it quickly.
So what if the verification has some bugs?
Yeah, verification has some bugs. Yeah, I don't know. I can't help you. If your SMT solver doesn't work, Pharmacy does have several SMT solvers, so
maybe we
you can hope for
that.
Yeah. Okay, so thank you very much.
Thank you, Juliet.
So we'll be back here in half an hour. We're on break right now.
So top of the hour to be back. Go ahead. Sure.
I'm supposed
Half an hour in, so we're going to be getting started again. And with that, I would like to introduce you to Thomas, and he will take it from here.
Yeah, hello everyone. Thank you for coming here. Hope you enjoyed our coffee break. So my name is Tomáš Glazár. I work for Red Hat, and I'm going to talk about auto-detecting sleeping clock calls in non-preemptible context via static analysis, which the outline of the talk is as such. It has 4 parts. In the first part, I'm going to describe the problem briefly. Then I'm going to present to you a proof of concept tool together with its algorithm design, implementation, and a demo, if that will work here. Then I'm going to talk about reimagining the approach from scratch and trying to improve it. And finally, there will be some time for questions. And depending on the time that the sections will take me, I might ask you for questions also earlier after the second part. So, the problem we are dealing with. The real-time kernel, the preempt RT patch set, changes the semantics of all spin locks into sleeping clocks. The locks, instead of spinning, they will try to sleep if the lock is unavailable. And this is a problem since it means that now suddenly you can't use spin locks with preemption disabled. And this issue affects all subsystems and drivers because locks are very common in the Linux kernel and you use them everywhere. And if the lock actually tries to sleep in a non-preemptible context, this means with preemption disabled, this leads to kernel panic and your entire kernel crashes. So this is a problem we have on real-time kernels, but obviously this issue can also occur on non-real-time kernels if you are not careful enough with mutexes or another kind of sleeping clocks. Yeah, so this is the problem. Here you can see an example. This is actually a real-world stack trace from an issue in BPF maps. You can see this sock map update LMSys function that used to disable preemption for some strange reason, and then it tries to allocate memory with this slab allocator, which on RT can sleep. And in that case, you get on a debug kernel you get a bug sleeping function called from invalid context, but you can also get bug sleeping while atomic and scheduling while atomic, and then you will crash. And there's also a link to the kernel. This was fixed because we encountered this. But the problem can be elsewhere in the kernel. It can be in code paths that are more rare, and you might not be able to see it at the first glance. And it might crash in the worst moment possible. So how to deal with this problem? One variant is that you can just manually fix each case when you encounter it. Like, I saw this case, I saw, okay, there is this preempt disable. I asked on the mailing list, is this preempt disable needed? And I got the response, no one knows why it is there. So I proposed to remove it, we removed it, the problem was fixed, and everyone was happy. But then there were other cases that we didn't know. So we could try to somehow automatically detect this kind of issue. And of course, we have to analyze the entire kernel, so we can't use any kind of complicated formal verifications through SMT formulas, like it was on the talk that was here previously, if you were there, because that wouldn't scale, and it would just run forever, and you wouldn't get anything from it. So, the proof of concept tool. We are looking for a pattern in the code. The pattern in a simple case looks like this. You somewhere call preempt disable. There you call some kind of a sleeping lock. It can be a spin lock. It can be a different kind of lock. But and then you have no preempt enable before the lock. That's the important part. But of course, you don't always find this easy case in your code, because both the preempt disable and the spin lock can be somewhere deep down in the call stack. You might call some function like lock the map that calls preempt disable somewhere. This was the case in the BPF sock map bug I showed you before. And the spin lock can be also a part of another function. So this has to be dealt with somehow. And fortunately, this second case with F1 and then F2 after it, where the functions call preempt disable or spin lock somewhere down in the call stack, this is the general case, because we can prove this easily, because to trigger the bug, there has to be a call of a sleeping clock somewhere in a function. We name it F. If there is no call to a sleeping clock, this bug can't occur. That's obvious. And now, there are two cases. Either there is a preempt disable in function F, or a function that calls preempt disable directly in function F. We call it G before it. And then we just have this F2, which is the spin lock, and then F1, which is this function G. Or we called preempt disable somewhere up in the call stack. The caller of F disabled preemption, and F is being called with preemption disabled now. And in this case, there is a function called H that calls both F and this function G that disables preemption. And this is, again, corresponding to the pattern we saw on the slide before. And here you see those two cases. This first one is that we call in F, we call G, and G disables preemption, and then we call spin lock. And in the second case, we call G somewhere in, not in F, but in H, and H eventually calls F, possibly through some other function that we name F prime here, but that's not that important here. So if we want to detect this pattern in source code, it's enough to look for this pattern. Of course, the problem are control statements. There might be a lot of control statements there, and the functions that are in the code might not exactly correspond to the functions that get called on the real kernel when you run it. But we ignore this for the time being. We now know that we can determine whether there is this kind of bug in a function if we know how its callees behave, and then we look whether a callee that calls schedule somewhere is present at the correct place in the function. This means in a place where preemption is disabled, which is a place where preempt disable was called and preempt enable wasn't called in between. And I propose a simple algorithm where we do this by a recursion on a function called graph. For each function in the kernel, we first compute this so-called semantics, preemption and scheduling semantics. This means whether it calls preempt disable and ends up with preemption disabled, and whether it calls schedule. And then we look at the function, and because we already know the behavior of its callees, we can determine its own behavior from it. So it's basically a simple recursive algorithm. The only thing that is required is that we have to have a set of functions whose semantics we know. We say, okay, we know this lock sleeps, and then based on that, we know some other function also sleeps, or this function calls preempt, this function disables preemption. Yeah, and I will show you a simple example on how this algorithm can work. Here, this is modeled after the BPF sock map bug. It's not exactly the same, but it's similar to the problem. So we have some primitive map log that just calls preempt disable, and a map unlog that calls preempt enable. And then we have a function called access map that takes the preempt disable map log, then takes another spin log, somehow it accesses the map, and then it unlocks both logs. And this is fine on a non-real-time kernel, because on a non-real-time kernel, the spin log spins, it doesn't sleep, but it will fail on a real-time kernel. And now we will see how this algorithm will detect this issue. We know the semantics of the functions preempt disable, that it disables preemption, preempt enable, enables preemption, and the spin lock sleeps. And we run this algorithm on this function access map. And so far, we don't know anything about this function. So we go through its colleagues. First, we encounter the maplog. We don't know what maplog does. So we go in recursion one level deeper, and we start looking into this maplog function. And we encounter preempt disable. So now we know that maplog disables preemption. Now we know that access map also disables preemption, at least at that point where we are in the function right now. And we go to the spin log. Now we know that spin log sleeps, so we know this access map function also sleeps. But now we have encountered a sleep at a place where there is preemption disabled. And that is a problem, and we detected this bug. And actually, this can be detected by the proof of concept tool I'm going to introduce on the next slide that is called RT-log scope. If we input this artificial case and this knowledge base, which was the initial state of the algorithm that you see on the right side, then it will detect a violation and it will say, okay, you call a sleeping clock through access map here, and you have disabled preemption at this place here. Yeah, so more to the implementation of this tool. I call this tool RT-log scope because it checks for the scope where logs are taken on the RT kernel, but it can be used on a non-RT kernel as well. And it's a prototype tool for auto-detecting scheduling with preemption disabled. The tool accepts two arguments. First argument is the source code tree, which in this case it was this artificial example, but you can pass the entire Linux kernel to it. And it takes also this knowledge base. And it uses this graph algorithm I described before. There are some more technical details of the algorithm, but basically what I described is it. And the tool is quite simple. We abuse ctext and cscope to look up the callees of the functions, and we just assume that the callees are called in the order they are specified in the source code. This is a very crude approximation, and obviously the question is whether it works or not. Yeah, here there is a slide where you can see the knowledge base. We annotate functions. We say, okay, preempt disable, disables preemption, preempt enable, enables preemption, and some functions like spin log and schedule are sleeping. Yeah, and now the important question is, does this very crude and bad algorithm give any reasonable results on the Linux kernel? Or is this just nonsense that I came up with here and has no practical use? Yeah, the answer is kind of complicated. It kind of works, but not quite. To explain this more, I will show you two examples. This is something where you are going to get a false positive, because this is code that calls preempt disable, schedule, and then preempt enable. And what RT-log scope sees is, okay, you disable preemption and then you sleep. This is a violation. But it's not, because there is this A variable. And if A is true, then you disable preemption, but then you don't sleep. Or if A is false, then you sleep, but you don't enable preemption. Oh, sorry, you don't disable preemption. So this is not a real violation, but this will get reported as a violation by this simple algorithm. But it's much worse than that. You can also get false negatives. For example, here, there is a while loop where we first sleep, and then we disable preemption at the end of the while loop, and then we go back to the beginning of the while loop, and we have disabled preemption. But because we are checking by the order the functions appear in the code, this is not going to get detected. And this is a real problem that was encountered while testing this tool. Yeah, so the current limitation is that RT-log scope completely ignores the control flow of the program. And as I already said, the sequence of the function calls that is written in the code is not exactly the same as that occurs at runtime. For example, loops, conditional statements, and also recursion is something that completely breaks this. I think that the implementation I have right now, I just assume the function does nothing if I encounter it in the graph algorithm recursively. And I just assume I won't hit this. And usually this is not a problem, because when we are detecting this bug, the logic around the preempt disable and the sleeping logs is really simple. You have just preempt disable something, then the log, and preempt enable. And in 99% of the cases, there is not any complicated logic around this. But the problem is that if you assign semantics wrong, just to one function, let's say there is a common function in the Linux kernel, and we, by mistake, say this function disables preemption, then we are going to get a lot of violations, maybe hundreds of thousands of outputs, and the tool becomes completely unusable. How to work around this? We simply annotate any functions that are assigned wrong manually. If there is a function that RT-log scope cannot handle, we annotate it manually and say, okay, this function doesn't actually disable preemption. And if you annotate enough functions, it will work, and you are going to get sensible results. And this should be theoretically sound, since in worst case you can just label all functions, but then you are not doing any automatic analysis anymore. So it relies on the heuristic to be smart, and on the code to be reasonable enough for this to work. Yeah, now I'm going to show you a bit of a demo. I hope I can. Oh, I can't actually click on links here. Yeah, I carefully prepared the links to the presentation. I thought I'm going to click on them, but it seems it's not possible here.
If you've got your laptop hooked up to BBB, you can basically change to project from there.
Yeah, I could set up that, but that would take some time. I might skip that.
Okay, let's skip it.
Yeah, so basically you run this tool. It takes about 20 minutes to analyze the entire Linux kernel with this, and you get a log with results where you have violations, and you can check whether those are real violations or not. And if you have the annotations set up correctly, you can get only hundreds of violations, which you can sort out manually and see what are real bugs and what are not real bugs. So this was the first part of the talk, where I presented this proof of concept tool. And I have about a minute time left in my schedule, so if there are some questions right away, I can take them. Okay.
Actually, you've got time. Yeah, you've got another 25 minutes.
Yeah, I'm going to present the other part, which
okay.
Then this is not the end, but is the microphone somewhere?
Here.
Okay, Peter. So I'm curious how you generate the call graph, because obviously the call graph depends on config options, and that can also mean that with some config options there is a violation, and with different config options there is no violation. And I assume you can't simply try out all combinations.
Yeah, this is a very good question, and basically we rely on the knowledge base for this, and when generating the call graph, we use cscope to get a list of functions that are called in the source code. So we get basically all calls that are present in the code, even those that are actually removed by some macros. And this is sometimes a problem because we have to annotate logs manually, because we would get both the RT code and the non-RT code, and those would be in conflict. And it would say, for example, that spin log is a violation, since there is a preempt disable in spin log for non-RT, and then there is an RT variant that doesn't do preempt disable. So we bypass this problem by annotating those functions manually.
Okay, so then I have a second question, and that is, how do you maintain the knowledge base? Because obviously, if you change the code, the data may no longer be valid, which means you would have to pretty much revalidate the knowledge base with each new version of the kernel.
Yeah, that's a very good point. And actually, my demo was originally with the 6.10 kernel, and it all worked perfectly. But then some locking semantics changed in 6.11, and it suddenly completely broke and required another update of the knowledge base. So this is a real problem, and you just have to update the knowledge base until you get reasonable results.
Okay, thank you.
And that was a very good question, thank you. Maybe we can get one more question.
Could you talk about why log dep is not solution here? Like, can we have, instead of like static analysis, annotate, like make log dep complain about spin lock under preemption on non-preemptive kernel, on non-RT kernel, so we would have this wider exposure and catch these bugs this way.
Yeah, that is a valid way to approach this problem, and we do this currently on an RT kernel. When you have a debug kernel, you get this bug sleeping function called in non-preemptible context message. But it's a good suggestion, actually. I haven't thought about this. If we can get the upstream kernel to get such a warning to people on the non-real-time kernel, then this would work.
So a lot of people don't have debug atomic sleep enabled. If you have debug atomic
Otherwise, it won't pick up for a
Yeah, I can repeat the questions if you can't pass the microphone quick enough.
Debug atomic sleep enabled, then it will generate a runtime warning. People seem not to know about that option.
Yeah, we would just have to force people to use that even on non-real-time kernels, which I can't imagine people doing.
Another interesting note, there was some work performed by the late Daniel Bristow, and he had some automata that looked for this case, right? But again, runtime verification. So your work is the other way, right? You are doing static analysis.
Yeah, that's a very good point, and I'm going to mention this exact thing in the next part of the presentation.
Sorry for the spoilers.
Yeah, so your question is completely on point. Okay, so now I would like to proceed to the next part of my presentation, which is trying to improve this very broken approach that I have introduced in the first part. So, how to improve the RT-log scope further? One way is to keep refining the knowledge base, to patch everything that goes wrong in the algorithm by manually annotating it. Another way is to try to improve the algorithm itself, because there has to be a more clever way to do this. Surely science is advanced enough to do that. And one idea I had, and which I developed for this presentation because I was really lazy about this project, but it's an interesting idea, is to check for possible sequences of events. Instead of viewing the problem as assigning semantic summaries to functions, like saying, okay, this function disables preemption, this function sleeps, this function enables preemption, we are going to look at all possible sequences of interesting events that might happen in the Linux kernel, and then we are going to determine if those sequences are correct or not. And this turns out to be a useful way of viewing the problem. So we have a set of events which we are interested in, which in this case is preempt enable, preempt disable, and schedule, and we named those P, E, P, D, and S. And now we have two sets. One is the set of all possible sequences of events that can happen on a system. We call it A. And another set, V, is the set of all violations. So this is the set of all sequences where schedule is called under non-preemptible context. And now we want to verify whether there is an intersection between those sets. And if there is one, then we know there is a problem. It sounds simple when stated like this, but the sets are not that trivial. To be more specific, V is going to be either a regular language or a context-free language. That depends on while we if we allow nesting of preempt enable and preempt disable. If we don't allow nesting, it's a regular language. If we allow nesting, it will be a context-free language. But still, this is quite a simple set, which is representable with a finite state automaton or a push-down automaton. And this automaton representation is used, for example, in the kernel RV subsystem, which does runtime verification. This means in runtime verification, this set A is samples from the set A are collected from runtime, and they are checked in real time against the automaton for the set B. And if there is a violation, then it reports the violation, or it can trigger a kernel panic or something to catch the problem. But here we don't have this luxury of having a running system that supplies these sequences for us. And this A set is obviously more complicated since it derives from the program itself, and the program unfortunately is the Linux kernel, which is very big. So we have to account for all such possible sequences, which is the hardness of the problem. We just have to know which possible sequences of events the kernel can generate. But still, this is an easier question than the complete semantics of the kernel, since we are only focusing on a few events that can be easily traced. We say, for example, this event happens in this function, and that's basically what we do with the annotations in RT-log scope. So this is the RT-log scope problem as an automaton. This is for the V set. We have two states. We have one state where we are in preemptible context, another state where we are in non-preemptible context, or non-preemptive, non-preemptive. If we switch between those, we preempt disable and preempt enable, and if we call schedule in the second state, then it is a violation. This example was stolen from an example in the Linux kernel that verifies something a bit different, but RV has an example that is very similar to this, that is checking for a similar violation. So we have this automaton, and now we can view RT-log scope as an event sequence generator. Instead of determining semantics, we attach a set of event sequences to each function in the kernel. For example, we say that the function maplog, which we had in the example, generates a sequence PD. It disables preemption, and that's the only semantics it can have. And then we check each such sequence for violations, and if we find violations, then we report them. And you can notice that this is very similar to the original graph algorithm. The semantics we assign in the original graph algorithm is just a function between the states of the automaton given by the corresponding sequences. We say, okay, this function does this thing when we are in this state. We are not interested in the exact sequences. We are interested only about the transitions of the automaton that represents the problem. But this point of view, while it looks more complicated and it's not, you can't imagine quickly an algorithm that would work on this, but it gives us an intermediate representation that can be processed further. And this intermediate representation are those sets of sequences. To show this on a practical example, here we have again our program with maplog, map unlock, and access map. And here we have assigned sequences to the functions instead of assigning those semantic summaries. So the knowledge base is that preempt disable has just one sequence PD, preempt enable has also one sequence PE, and spinlock has S sleeps. And now the semantics of the other functions, the sequence sets are composed of the sequence sets of the other functions. Maplog is the same as preempt disable because it calls preempt disable. Map unlock is the same as preempt enable because it calls preempt enable. And now access map is again composed of these functions, and we get this nice sequence PEDS PE, where we see we violate the property at the very beginning on the automaton. So the advantages of these sequence representations. We can use regular expressions to represent the sequence set. There doesn't have to be only one sequence that a function can produce because it depends on the state of the machine when the function runs. And another advantage, this is a bit of a trick, is that we can include C statements into the sequences. This At first glance, it makes no sense. Why would we throw into this formalism C code? But this extended representation can be seen and manipulated as a superset of C, and we can apply some transformations to common patterns in code. This is kind of similar to a project that does static analysis also on the whole Linux kernel and checks for semantic equivalence. This project is called DivCamp, and it also applies patterns. I'm going to give this reference at the end of the talk. But now I'm going to show you an example of this transformation, because this is probably completely confusing and you have no idea what this means. Okay, here we have this kind of problematic code I have already showed you before, where we have if some expression preempt disable, if some other expression schedule, if again this expression preempt enable. And we can see that this we can do a pattern and say, whenever we see this code in the Linux kernel, we are going to assign it this regular expression, either preempt disable or preempt enable or sleep. And this isn't going to give us any violation, since we are going to just check the first sequence, we see it doesn't violate anything, and then we check the other sequence and we also see it doesn't violate anything. So there are obviously a lot of challenges to this approach. We have to implement those patterns efficiently enough so it doesn't blow up. We don't have an exponential amount of the event sequences we have to check. That is one problem. And another problem is that we have to create this database of patterns to cover enough of the code in the Linux kernel for it to work properly. And some of those problems can be solved by doing some kind of representation of the Linux kernel with automata too, and then just do an intersection of the automata and run some already known algorithm on that. And that is something I'm currently looking into. Yeah, so the conclusion of the talk is that you can use static analysis to detect at least some scheduling while atomic issues in the Linux kernel. And although that static analysis is theoretically hard, you have a limited degree of complexity in real-world code. You are not going to have any kind of crazy code from the theoretical point of view, and you might be able to resolve this with specialized algorithms that will apply patterns to code that is commonly written by us humans. And we also see that this approach is connected to the RV subsystem and the formalism under it, detecting sequences of events based on trace points in the Linux kernel, as well as the approach of the DivCamp tool of applying patterns in order to solve difficult questions about semantics. And this can be also possibly generalized to other verification problems once it gets developed enough. Okay, so this is the end of the talk part of the talk, and now is proper time for your questions after the entire talk.
Okay. Sorry.
Hi.
One for two.
So could you go back to the slide with the expression matching?
Yeah, this one? This one?
Yeah. So what happens if the expression is, the opposite, the negated one, but relies on some variables whose values changed meanwhile? So
yeah, in that case, you cannot apply this pattern, or you have to develop a more involved pattern to catch this. This is just an abstract description. I haven't gone into this that much. But obviously, if the expression is simple, which quite frequently it is, this example usually is when this is a real-time kernel, then you don't preempt disable, and if it is a real-time kernel, then you sleep.
Yeah, and another question. For the related tools, doesn't sparse or smudge do these kind of checks also, and maybe could be extended if it's missing this particular scenario, or is it more?
Yeah, it's possible. I'm not familiar with static analysis tools. I was thrown into this randomly. I was basically bored and I started working on this. And I'm not a specialist in either formal verification or static analysis. And it's possible that some of this has been already implemented in some kind of way. So thank you for that.
I'm not sure myself, maybe something to check.
Yeah, I was actually thinking maybe doing it as like an LLVM plugin or something where you can take advantage of its ability to do, control flow analysis and things like that. It's good.
Yeah, that was one of my original ideas, but I got a suggestion from a colleague that it might be better to do this in C. It could be also done on LLVM level, but it would be a bit different.
So allergy to C++ is the issue?
Yeah, but we don't allow C++ in the kernel.
But this wouldn't be in the kernel, it would be in the tool.
Yeah, you mean like using C++ for LLVM in the tool?
Right.
Yeah, that's not a problem. It doesn't matter which language this is implemented in. My current implementation, which is just a prototype, is in Python and it's real slow. And I would probably re-implement it in something else if I did this properly.
Smatch does have a check similar to this. Although, on Smatch, right now, it assumes that spinlock disables preemption instead of sleeping. So there would need to be some changes to that to make it work correctly for real time.
Okay.
Any more questions? Well, let's thank the speaker and thank you very much.
Yeah, I will show you the references.
Okay. I'll leave the references up until we put up the next speaker. Is the next speaker in the room? Thank you. Oh, no, that's not it. I don't know what to do when we start. Switch over to your slides now, and then you can start at, what is it right now? In 6 minutes.
Yeah, that's perfect.
Okay. We're good then.
Do you have any water?
No, but I can go out and get some in the water. Yeah. Hi.
This is the first track, right?
Yes.
I'm planning to speak on Friday.
Okay.
But I couldn't join the speaker training session before, so.
It was recorded.
Recorded. Yeah, he said he might record.
He did.
He did.
Yeah, but so what you're going to need to do is you're going to need to go and upload your slides onto where your abstract is.
Yeah.
Have you done that?
I did. I updated it. But can you double check for me?
Yeah. As soon as I move this one over, we'll go sit there by my laptop and I'll double check everything's good. Okay. And so oops. There.
When the next presentation starts, time?
So let's go over there, and then if you can start in a few minutes.
Yep, so this is just,
It's a bit sticky, so you've got your water.
I got it.
Yeah, nice to meet you. Yeah.
Sorry about that.
I mean, the first guys already have it. Exactly, but it's going to be forever.
So, boom, boom, guys. So, I guess I'll get started. So, my name is Javier. I'm with Samsung. And we are going to be talking about something that we call data placement. And for those that are in storage, this is kind of an old topic, and then you might be saying why you're still talking about it. For those that are not in storage, and you see some of the things that we're doing constantly on block layer and file systems and in drivers, you might think that we're insane because we've been trying to solve the same issue for about 10 years and we don't seem to agree on how to do that. So the goal of this talk is to go a little bit through the history of why this is important on storage devices. I think it's especially important for devices that use NAND, but I think it applies also for rotational media. What are the different approaches that have reached the Linux kernel? What are the approaches that are still alive? And what are the use cases for some of these approaches? And hopefully we find some alignment. And then I believe I talked to Hans. We are in the micro conference that is Sound Devices on this afternoon. We are going to talk about not only Sound Devices, but also a little bit about some of the other technologies that might have some overlap. So why data placement is important? And in the beginning, when we had block devices, everything worked. It's like in the 70s, everything was very easy. Everybody did the same thing. You could write random, you could write sequential, and things were pretty good. Especially since we introduced NAND-based storage devices, this has not been true for all things, right? So we maintain the block device interface, but in the in the back end of the device, we need to do a lot of stuff to maintain that interface. And I don't want to get into nitty-gritty details. I think SSDs are pretty well known today, but the core of the problem is that the write granularity, which is a few kilobytes, and the erase granularity of the NAND has different granularities. That is a few gigabytes for the erase. And you need to erase because in NAND you cannot rewrite. You need to write, you need to erase, and then you need to write again. And this creates a garbage collection issue. And this garbage collection creates something that we call write amplification. And I'm going to get deep into the next slide because there's a lot of confusion. Different people understand write amplification differently. And I'm going to try to draw a line on what that means. But the core of this is that, especially in the past 10, 12 years, primarily since we had Fusion I/O being very successful at putting NAND on PCIe, we've been trying to make the host side and the device side talk a little bit better with each other, so that the host, which supposedly knows better where data needs to go, because whether it is a file system or a log structure application or anything, can send hints to the device to say, this data belongs together. So please do not move it on your garbage collection process, because I know I'm going to invalidate all of it at some point, and then I'm going to save some work for you. And there have been different approaches on whether you go all the way and you give full control to the host, or you go all the way on the other side, and then you just hint the device in different parts. So I hope that's clear. Please interrupt me at any time if you have questions. The result of all of this is that we've had a lot of different competing technologies in different standards, but in Linux we care about, especially if we think a block layer, we think about everybody being common, but we need to do with SCSI, we need to do with NVMe, with UFS, and everything in the middle. So that has been a little bit of a nightmare. Wow. So this is a little bit of the history. A very high overview. I'm missing a few things, like at Samsung would be the key value SSD that had no success at all. So I'm omitting those things that were failures from the beginning. But these are kind of the technologies that have somehow had an impact on the industry. So block devices, block interface, they've been there forever. I think they're pretty successful. These are not chronologically ordered. They are from less communication to the host to more communication to the host. So I'm going to start on the left hand, your right hand side, on the open channel SSD. So when we started this effort, very much inspired by the success of Fusion I/O, at that time, NAND was simpler. We were in something called MLC, that is only 2 bits per cell, and most NAND look similar. So the assumption was we can give full control to the host. The host knows the physical characteristics of the NAND, channels, dies, blocks, pages, planes, sectors, and then the host will do a good job at replacing data. And then you can manage one of the big trade-offs that we have on SSDs, which is your bandwidth versus your isolation. Because, for those who don't know, when you have an SSD, you basically have, you can think of it like a dies that you can think of stripe. We typically call that the super block, and then you stripe across all of them to get bandwidth, but then you have collisions on each of them. So if you do a write and a read, the read needs to wait for the write, and the assumption was, well, you can manage this trade-off by giving the host the enough information to maybe do writes in a part, but then reads in a different part. And the reality is that has turned to be very, very complicated, especially as NAND has become more complex. I think that assumption was not true. The open channel effort, at least from a general industry perspective, died, never got standardized in NVMe. We had a subsystem in Linux called LineNVM, which was there for I think 3 or 4 years and then got removed. You might still find reminiscence of it in some Chinese data centers that are building their own spec and doing something similar to this. But from a Linux perspective, at least, we don't care about that anymore. Building on top of Open Channel and some standardization efforts that didn't succeed, we have some from NAND perspective, we reused a lot of the work that hard drives had been making and succeeding at on the zone devices. And maybe you've heard about SMR hard drives due to how at the end of the day, it's all about how you make these devices cheaper. And then a lot of making it cheaper is to increase the density. So in hard drives, when you put the platters like kind of on top of each other, you end up having some physical limitation that forces you to write sequential in some places, and that triggered this concept of zones. So you divide the drive in how the platters are being made, and then you call that a zone, and then you need to write sequential within that zone, and that abstraction also works pretty well with NAND. So CNS devices on NVMe and SMR devices on the hard drive T10 and T13 is SAC and CBC. Especially in the hard drive, have been very successful. That has triggered a big effort. Some of the guys doing the work on Western Digital are here, and I think you can find Damien, who's dedicated the last 10 years of his life on making this work. That has been very successful. So that has been pretty good. And then the arrow there is, this is selected as one of the technologies that is alive and that we should care about. However, for NAND, some of the limitations, hard drives and SSDs are different. So some of the assumptions that were made on hard drives have not held true on SSDs. And CNS, I am aware there are some people still looking into that, but I believe as a general industry, it has not gotten the adoption that we were hoping to. So we get to something they call a flexible data placement. That is kind of the next part on NVMe. And that builds on something that we had working on in the past, almost at the same time than Open Channel, that was called streams. And I'll mention streams and then build on top of that to motivate FTP. The approach of streams was the opposite of Open Channel. It was, you have a block device, you respect the block device interface, you are backwards compatible to the block device interface, but you can send hints to the device. You can tell the device, hey, here is like a stream ID, and then the device would do a best effort on how to place that. Samsung was very involved in that, but it was not very successful. So a few customers got that adopted, but at least at the time, and there was not that much focus on making support in Linux. And as we all know, when you don't have like a general customer base, things fragment, and that meant the end of streams. So with this flexible data placement, we're trying to find a kind of a middle ground between what was streams and what is zone namespaces. So it's also a hint-based interface. It is backwards compatible, but it adds a little bit more of the control inspired on CNS and on SMR, SAC CBC, that is trying to control the erase block. What I mentioned before, that you need to erase the data before you can rewrite it again. There are parts of FTP that would allow you to make your invalidations, your discards, basically, transform them into a DSM command that would be I don't want to use guaranteed, but taken into strong consideration by the device so that you have some of these guarantees. So I believe today the two technologies that are relevant for the Linux community are zone devices and FTP. So the rest of the conversation is going to be around those. But if you have questions about any of the other technologies, you're very happy to bring that up too. So I promised to talk about write amplification, because this is something that this is, even for people that understand storage, is very confusing, because write amplification, at least for me, I see it as a proxy metric. It's a metric that is being used to talk about many different things. So some people talk about right amplification as the lifetime of the device, because you're going to wear out the drive and then you're not going to meet the 5-year guarantee. Some people look at it as a proxy metric of how much garbage collection the device is actually doing. How much data you're moving unnecessarily. So this basically, when they look at this, they say if I write 1 terabyte to the device, how much data is being actually written to the media. So it can be 1.2 terabytes, or it can be 3 terabytes if you're doing a very bad job. Some people look at this from a latency perspective. I personally like that because when they look at latency, it's a combination of all the above. It's because if you're doing a lot of internal work on the SSD, you can be smart about how you do things, but if you move a lot of data on your garbage collection, you're at the end of the day affecting your user rights. And that's something that affects the user on their daily use. I put an emphasis on this because, we vendors, we need to give you a guarantee. So if we tell you 1 device write per day, 5 years, we normally respect that. Otherwise, we're in trouble. But in terms of latency, we have maybe less control depending on how you're using the device. So this graph here is trying to show you some of the real use cases when people talk about at scale from a hyperscaler perspective, what they mean about right amplification. This is at least the best explanation I myself have gotten on how to understand that and communicate that why customers should care about this. So here you have, imagine that this is real data from one hyperscaler. Some people say, I can only tolerate a certain number of latency, and I can pinpoint, because we have log pages that can tell you the right amplification of the device, how much data is written to the interface versus how much data is written to the NAND. And they can correlate the latency they want to the right amplification that the device is creating. So that correlation gives them a data point when they say, I need to over-provision my device by X% so that I can meet that SLA, my latency, at this right amplification point. In this particular example, I think I can barely see here, I think it's at 50%. This is an extreme example, but it's a real one. So some people say, we can only tolerate 1.3 right amplification for this particular workload. That means that I need to use only half of the device. Why capacity means? Because if you're using less of the device, then the firmware, the flash translation layer, has more space to do their own work. So you're not putting as much pressure, and then the latencies are good. And then these people say, hey, how can we improve right amplification so that I can, instead of using only 50% of the device, I can use 70% of the device? So this is the core. So it's not, I want to emphasize, it's not about the retention, how many years the drive is going to last. You have the guarantee for that. It's about how you're using the device for your particular use case and what right amplification you can tolerate, because it is a proxy of the thing that you really care about. In this particular case, for this particular hyperscaler, this is a comparison of actually, you can see that there are some points there on a sound device that guarantees a right amplification of 1. And then you have an example of a FDP, the other technology I mentioned, where the customer was, well, I want to use, if I use this technology, how much more drive I can use until I hit that right amplification. And in this case, it was at a 70%. So you're effectively getting 50% more of your device using FDP. If you use another technology, maybe you get more. But it's all about, at the end of the day, what these people care about is what's your engineering effort versus what's the benefit you get, so that you find a middle ground. I hope this is clear. Do you have any questions on this? Okay, so with this in mind, and taking these two technologies, from the outside, it might look like these two technologies are competing. You have two things that do the same thing, and I think in reality they're not. I think they are two technologies that target two different use cases, even though sometimes they happen to be on the same protocol, like for example, in NVMe. And I think we can separate it in three categories. What's your write model, depending on the application that you want to use? What are the run amplification guarantees that you might expect? And then also, what is the suitability for the use case that you're trying to put, right? So when people look at sound storage, typically they look at applications that are very much sequential. This is a pinpoint because, many applications believe to be sequential, but I call them like they're mostly sequential. But it is that small percentage that really messes with your algorithms, right? In T10 and T13 for SMR hard drives, they did a very good thing of standardizing random zones so that if you want to put parts of your metadata on that device, you can do that. In NVMe, we did not do that. So that creates a problem because you either have a fully sequential workload or you need a separate device for your metadata, but that creates some failure domain issues, like, what if you lose your metadata or you lose only your data? Most people don't want to get into those discussions. This also applies for people saying, you can create two namespaces, one that is a normal dock device namespace and the other one is a zone namespace. And then the question is what the ratio for that? You're basically theme provisioning your device and saying, is it 1%, is it 10%, how you're going to use it? That's a very complex question. When people are fighting for 1-2% of the device, saying that you're going to strand 10% of your device for metadata, that sounds kind of crazy and people is not going to that direction, right? On the opposite, you have the right hints. That follows, okay, you can have, if you do sequential workloads, it is already very good for the SSD. Even though if you use a block device, sequential workloads, we like them very much. We have obviously heuristics to say, hey, this is a sequential workload. Yes. So you can leverage that, but it's not enforced. You do a random write. Remember that this is about placement. It's not about how you write. It's where you place the data. So if you have like a database object, and then you decide to write a sequential, from a placement perspective, is the same as if you write it completely randomly. You just care about that you invalidate it all at the same time. So in this case, hints are maybe more suitable for people that either cannot guarantee that they're fully sequential workloads, or people that decidedly have a random workload. So some legacy applications, you don't even have the code for that, so you don't know what's going on, and you might do a best effort. From the write amplification guarantee perspective, obviously some devices are best in class because the garbage collection is not happening on the device. So at the interface level, the device is guaranteeing you a write amplification of 1. The caveat for this is, if you do not have a fully sequential workload, or if your application, somehow it cannot invalidate all the objects at the same time, and we see that in key value stores all the time, the host will trigger some garbage collection that probably would not have happened if you were not using CNS, and you need to take that into consideration. So, the guarantee is 1 at the interface, but it's not guaranteed. And this, in our experience, have been an issue when people deployed it in reality and they measure their end-to-end write amplification all the way from the customer's application. So it's not 1. And then the question, what's your software doing? And then we end up in this weird conversation, well, we're not responsible for your software. And even though we might have written parts of it in Linux, we cannot give you a guarantee on the software. So that creates a very difficult conversation. That conversation simplifies when you talk about write hints for people that do not have maybe a system level workload. Because again, I'm talking from the vendor perspective, but if you are like a vendor at a different level, you're at an OEM, you might have to give those guarantees. But they also have, the workload of the customer, they don't know. So, it's a very blaming, their fault, my fault, their fault. Write hints is more it's easier to understand for customers because since it is backwards compatible, you know what the worst case is, and the worst case is what you always experience. But you have an upper hand if you're doing a good job, right? If you're a good boy, you get some of the benefits, and then you can measure those. So at the end of the day, from the suitability, how we see that is, if you're designing an application or even a file system, and that's a lot of work. From the beginning, you might want, and I think Slava has been doing some good job on that, right? You decide that from the beginning, you can work around some of these issues and deal with fully sequential stuff. But what we see is that a lot of people that want to deploy this at scale do not have the capability or the time to wait 10 years for a piece of software to be stable. They want to do a minimal amount of work to get some of the benefit. And this might be complex. Yeah. Do you guys have? Oh. Yeah. Hoping for the best.
All right, so I've been working a lot with this end-to-end integration. I know how hard it is to turn all workloads into sequential write patterns. But one way we can sort of share the pain of adopting some storage is to work on the file system support for it. So if you put a file system on top, the user doesn't have to even know that there's some storage underneath them. We can reap the benefits if we do the file systems right. So F2FS has been there for quite a long time, and now the Android guys are now being able to use some UFS when that comes around. Butterfs is stabilized, and we're also working on zone storage support for XFS, which sort of mitigates all of this, but it doesn't mean that we're done. We still need to make sure that the end customers' use cases do not. Just because it works doesn't mean it gets any benefit, right? And something that would be great to discuss in the BOF later on in the Zone MC, how we sort of have a good interface for the user to make sure that they can specify the things both for zone storage and for the FTP use case, so they can utilize both. So yeah, there are things we can do to make zone storage easier, and we'll see what would be the easier way to either provide hints or just do some nice heuristics in the file system.
Yeah, I agree. I mean, file is great. The caveat to that is that, people that are extremists in saying, I really want to get the best out of my write amplification, they try to shorten the stack. So they say, I'd rather work at a block device level, and I don't want to have a file system, because then I'm doing log writes on my application, then log writes on my file system, then log writes on my SSD. For those people, we still have an open problem. And from a file system, I think you can do a lot of work, but I always have, and I think that's a good topic to discuss later. How many semantics are we able to send from the application to the file system for the file system to do a good job? Let's say that I have like an object database. How much can I tell the file system this object really belongs together, or this object is loosely coupled with this other thing? I'm not entirely sure that we have a good answer for that.
That's a common problem with FTP, right? You need to be able to specify that you should separate or co-locate data in some way, and I think that's a really interesting research area. We have more time.
Yeah, sure. But thanks for the comment. Slava, go ahead.
Yes, I would like to add, you have done good point, but don't forget about NILFS 2. It's from 2006. It's pretty completely log structure. We need to update on the super block at the beginning, super block at the end of the volume. So but at the rest of the volume, it's completely copy and write policy. So yes, file system can guarantee sequential writes. So maybe, of course, some guys would like not to use file system at all.
So, but I want to emphasize the difference between writing, the fact that, in my opinion, the fact that you write sequential to it is a consequence of the technology, not a benefit of the technology. You care about placing data in a way that you can invalidate at the same time so that you can help the device. Writing sequential is not the objective, it's a painful consequence of having to do this, if that makes sense. So from a placement perspective, I know that we prefer to have sequential data, but from a pure placement perspective, the only thing you care about is that if I'm writing, 100 megabytes worth of LBAs within the same range, and I can invalidate them all at the same time, that's what I want. I don't care whether those writes are going sequential to the device or are going random to the device. I'm aware that there are some benefits, but I see that people that go with some devices, especially on NAND, struggle on guaranteeing the sequentiality, and that has been a burden more than a help. The file system can help, but it's about the placement, not about the sequentiality. I hope that makes sense.
Yeah, don't get me wrong. I'm not against flexible data placement.
It's not. It's not about one versus the other. I personally spend a fair amount of my life working on CNS, and a lot of people have. So it's about being realistic about what people want, not what I want to sell them, if that makes sense.
Yeah, we will have time to.
Yeah, we can talk more about that later. Yeah.
So as has been, like you have already mentioned, there have been streams and so on. So there have been some kind of attempts for this hinting in the past, and the problem with these hints tended to be like, I guess it can work reasonably well for these hyperscalers which control tightly the whole software stack, but like the story doesn't really work for like a lot of other use cases where simply if you don't have the control over all your software stack, then like there are difficult questions how different users of these features are going to interact with each other, or how even like you kind of discoverability of these features and all this stuff for user space.
Fully agree, and
which like by the previous attempts actually didn't succeed because these questions remained open. Nobody actually figured out a good solution, and in the end the traction wasn't like strong enough to get it to completion.
I fully agree, and it is clear that this is a hyperscale enterprise feature. I don't see, even when we talk about, I guess you can buy today some SMR devices. The technology has evolved enough that you can get it in client somehow. You can buy it at Amazon. But, maybe we get there, but today the use case is primarily enterprise, hyperscale. And I fully agree with you. People that claim you can hide the hint on the file system and then hope for the best, I don't think that's going to work. I mean, the file system doesn't know anything about it. This is all about giving to your application the hints if you're either working on block or file or pass-through. I'm going to mention that later. But it's very targeted applications, very specific. We've done some work on CASLib, Meta's CASLib. This is a very good example of something that can leverage this. But I'm fully aware that if you're running on other use cases, this is completely useless for you. Okay, so I'll try to move ahead. So this is basically what I've mentioned before, at least how we see the traction on the industry is that Zone Storage is very strong on SMR hard drives. It's coming very strong also on UFS devices. And you might say, why in UFS works when it is NAND and in NVMe is not getting the same traction? And the way I see it is that UFS is a very contained environment. It's Android. It's a single file system, F2FS. Even though you have many applications, it's very controlled what you can put into that. So they've been very successful at using the F2FS hints for temperatures to be able to leverage this. And I think that, Bart and Yegiuk are doing a good job in that direction. On NVMe, I see more the hints getting ahead because of the use case. I mean, I'm very aware that there are some people doing other stuff, but at least from the Linux perspective, if you look at the past 3 years, that's basically where things are going. But happy to be proven wrong, and then we can talk more about it on the path. I don't want to spend, I want to show you an example of the work that is happening now on FDP, but also to motivate what happens if you want to do other stuff that is out of FDP. Long story short, it's hints, same as we had before, but you have some guarantees in terms of when you send a discard, that the discard is going to be respected by the device. And then you have some more information in terms of what's the number of hints that you have, what are the sizes of the we don't call it zones, it's called reclaimed units, but basically the LBA range in which you're placing the data, how big that is, so that you can map that to your objects. And there is feedback loop in terms of log pages. So you can go and query the device and tell, hey, how am I doing? Am I aligning to the reclaim unit, yes or no? And based on that, you can tweak your application to make better decisions. I want to make a kind of a pit stop on, because today we do not have a block layer of file system support for FTP, and then you say how you have all this data and how people is deploying that. For those that are not very familiar or don't follow NVMe too much, in the past years we've created a new interface that is called IO pass-through, and that you can think of it as an ioctal that is asynchronous. So it's connected to the IOU ring, and it speaks directly to the NVMe driver. So you can write asynchronously to the NVMe driver, and then you bypass the block layer. So you can speak NVMe. I like to think of this as, people that might be familiar with a SPDK, that is a file system NVMe driver, not very popular in this forum, but you can think of a SPDK taking the good part of SPDK that I think everybody agrees that is having a domain-specific block layer that people can deploy on their applications, but using the in-kernel NVMe driver. We've actually gone and done the work to connect SPDK to pass-through, so today if you have an SPDK application, you do not need to use the user space NVMe driver, you can use pass-through, and then you would be using kernel infrastructure on a domain-specific block layer. Did I pass? Oh, yeah. So in terms of implementation, I mentioned it's a new ioctal, but it's connected to the IOU ring command. And it follows all the checks and capabilities. We're constantly finding new, every time that there's optimizations for the block layer, we kind of try to bring them back to pass-through because there are some very good things happening there. One consequence, if you want to be aware of this, of putting pass-through, is that there's a few commands on NVMe specifically for CNS. One thing called a append command that is a nameless write. You write and then you don't specify the LBA. The device places the data and gives you the LBA back. We didn't have enough space, so we ended up creating something that is like a big submission queue and big completion queue, which now has proven to be useful for other commands like copy too. So that's there, and it's I think it's pretty well supported nowadays. We have a file support, NVMe CLI, you can use it. As I mentioned, SPDK has support for that. liburing also uses it. So if you have any issues, just scream in the mailing list and we'll fix it. So coming back to FTP, this is one of the use cases why we created the pass-through interface. So if you have a new idea like FTP, or if you have a new idea like, I don't know, the key value that we did, key value system that we did in the past, you can use this interface without having to make changes to the kernel. So you can put this actually in production, you can validate it and test it, and then hopefully save some cycles for reviews and maintainers to spend time on whatever patches you're sending. Today, for FTP particularly, this is deployed on CacheLib, and Meta has been very open about talking about this. And now we are in the process of, we believe that the technology is pretty mature. I think every single SSD vendor today is building FTP support, so this is not like one vendor or the other. So I think now we're ready to bring it to the block layer. And this is ongoing stuff. We tried two approaches. I'm going to get a little bit specific here. So if anybody's interested or wants to review, like this is happening right now, being answered. We've been having a conversation this morning. So if you're aware of SCSI, on SCSI devices, we've had for some time what we call the temperatures of the hints. That's how it was implemented like 8 years ago or something. It works also for UFS. So it was standardized in T13, I believe, and then UFS picked it up. Support for this was removed from the block layer around 2 years ago. So you still have the right hints at the protocol layer, and the file system can use them, but they were not mapped all the way up to user space. Now, Bart did a good job in the context of UFS of bringing those hints back and motivating them on why UFS uses them. So today UFS has that infrastructure. So the first attempt that we had that was very simple is, okay, let's use what we already have in the kernel. It's kind of a lie, because the NVMe protocol does not think of temperature. You know, SCSI specifies this hint is cold, this hint is warm, and then actually, you know, the device could make better decisions where they place them. Don't do that really, but, you know, could. And in NVMe, we say, okay, we can map those 5 hints, and then, you know, off you go. Some people don't like that because it's not generic, and that's true. It's simple but not generic. So from version 4, actually, I modified the slides, but I couldn't upload them yesterday. From version 4, we are changing approaches, and instead of reusing the temperature hints, we're using the same space in the inode, but we are overloading to say either you use the temperature hints or you use the whole 128 bits to be able to specify 128 different hints, and that's you know, that's what's moving forward. It removes the semantics of it, which I think is probably a good idea, but it complicates because it goes out of the NVMe layer, and we start messing with how we present things to user space, which you know, is always a little bit scary because we don't know what this is going to go into the future. You know, what if we add right now? I think everybody is in like the few tens of hints, but what happens if we get to thousands of hints? Then suddenly, you know, Christian was saying, giving you a little bit more space, like another byte on the inode. That I just spent I don't know how much time removing one. So you know, that's very expensive real estate. So we need to think about that, but. We do hope to get this merged. I think 6.12 is not. 6.13. Send the new version. So if you're interested in FTP or you're interested on you know, consequences of it, you know, please go and review the patches. And it's 38 minutes, and that's all I have. So basically, you know, takeaways is, I think data placement is still unsolved, but I think we're converging. I think you know, I look forward to the conversation this afternoon on how we can reuse a lot of the stuff that folks have been working on the zone devices to enable FTP and whatever comes next, you know, extensions. Hopefully, we don't need to spend another year standardizing another thing. Providing an end-to-end solution is very key. And for that's homework for vendors. You know, we tend to make the mistake to believe that just because we support it on hardware, then things are magically work and people will like them, and that's not true. So we need to think about what are the consequences in this particular case in Linux. But you know, there are other places that we need to consider. So you know, people should be aware of that. And I think, you know, we can live with 2 different models. They target different use cases, and hopefully one day they converge, and then we can all go and celebrate. So that's all I have. Do you have any questions?
Any more questions?
Yeah, I think there's one there, right behind you. Go up.
Right. So I saw the patches on the block list regarding the usage of the inodes with the 128 values.
Yeah.
So what does that? I was wondering what does this hint mean? Is this like take 2 inodes? One inode, like both inodes have the same hint, does that then mean in FTP that they belong together? And then you have a different inode, and then you have a different hint on other inodes, and then they belong to some other...
Yeah. So hints are at the end of the day, In theory, best effort in FDP is respected. So when you are, what you're saying is absolutely correct. So the way you communicate to the application is, if you use a different hint, whether you're putting it on the inode or your application is using the hint specifically, the SSD would place it in a different superblock. So they are meant to be things that belong together. So hot call data is typically something that people like because it's easy to understand. But for example, we've had good experiences in big, small. So if you have big objects and then you put them together, and then small objects, you put them together, that also works very well.
But right, the value in the inode, kind of the meaning of the value kind of changes a bit depending on whether you use like SCSI or NVMe, right?
That is correct.
It has a different meaning, right, at that point.
That is fully correct. And we've talked a lot about this, how much we should spend, because your point is completely valid. So we spend time in communicating to user space, oh, this device supports this and this device supports the other thing. But the reality, if you look at the model today, there's no check. You can take a device that does not support a SCSI device, not supporting temperatures, and then you can populate that if you want to. The write will not fail, but it will just be ignored. Do I agree with that? No. But at least at this moment in time, we have customers that are using auth3 patches for this, and that's awful. It's painful for everybody. We would like to get it upstream, and then from there have a conversation. What should we do to make this better? Because it's also a mess for SCSI.
Yeah, sure. I mean, don't know whether any SCSI device even implements them right now.
Yeah, they do. So SCSI devices, some temperature, for example, UFS is one example that uses write hints heavily.
Okay, all right, thanks.
Hi. So he just mentioned that the temperature or the hint or the stream is stored in the inode.
Yep.
So will user space be able to set the hint on a per request basis?
Yeah. So that's we have patches for that, but we don't want to mix them with this. It's going to be IO uring. So IO uring, we already have the code. You're going to have per IO hint through IO uring, and actually through that, you don't even need to go through a file system. You can submit it directly to the block layer. Okay. But we see this as two separate patches. So try not to mix two different things. But yes.
Okay.
Very good point.
Because I want to emphasize that for many cases, I think having it per file is fine.
Yeah.
But in other cases, for example, I think about virtualization. We have one big difference.
100. Actually, I don't know if I'm speaking too much, but a lot of the use cases we see from people that deploy this, they don't care about the file system. It's all about giving it to user space for virtual machines. So 100%.
Okay, thank you.
We have a... Oh, yeah. So
we might end up having two ways of setting hints then. One is like this relative write lifetime hints, and this like just separate this data.
Exactly.
So I think this might be very confusing for user space.
100%, but it's already.
Like we should do the research and see what's good and what's not, and also provide documentation when to say either and or, and so everyone sort of has a common picture.
Yeah, I agree.
What do you expect when you do this, so you don't get a completely different behavior when switching disk?
I agree.
So I think there's value in both. Like having this just separation IDs, but I think most of the time you're gonna have to end up co-locating stuff anyway because you have a limited number of buckets to place them.
Yes.
So but it's a very complex problem, so it's something that will probably continue.
Yeah, so some people, I remember some arguments in the beginning. I think Martin was very vocal about, I have thousands of files on my machine. I should have thousands of streams. I don't think that's realistic. I mean, everybody that has been an SSD, 1,000 super blocks, good luck. But if you think more of grouping, the virtualization example is a very good one. So if you have like X number of virtual functions, typically you have like in the small tens. Yeah. And then you can, you can put like a VFIO device on an LBA range or whatever, and then you have like a very poor man's isolation solution, adding a tag for each of those VFIO devices. That works surprisingly well, and the effort is close to zero because you can automatically tag that.
Yeah, one interface might not fit all, right? Like, so it's just be clear to see, use this for that use case and like recommendations and see if we can continue
100%
figuring out how the users should use this.
I would like to say about temperature. Temperature is really confusing.
Yeah.
You cannot measure temperature of data. You can try, but it's hard. So maybe it's mostly about isolation. You would like to isolate different
Agree.
from each other. So maybe you don't, because maybe we can say it's hot, it's cold, maybe warm, but what is warm? Who knows? And it's temperature is really confusing.
Yeah.
But again, it's about isolation of data and gathering similar data. So maybe it needs to think in such a way, but not like temperature.
I agree. I mean, we had some feedback when we were standardizing NVMe. Oh, we should follow this custom model of temperature. It's like that's horrible, because people can think of other things, and then actually people that are using these on UFS overload the temperatures because they're doing something else, and that's horrible. You should have like these handles, and then you give them meaning you want to. If you transmit the semantics, can the SSD do a better job or the storage device do a better job? Of course, but I think we need to be very much into the future with very clearly defined things of what's hot and what's cold before we can do that. Because you can say, hey, super hot stuff I can put on SSD memory, but to me that's a research project, not a product problem for now. I mean, we have a question there.
Last one, then, I think.
If I understand correctly, you were saying that you are starting to hint into the inodes, and depending on the amount of hints you have, you can actually start running out of space into the inode to store those hints.
Yeah, so the point is right now, it's always what we implement an upstream today versus what's the ideal generic interface we need for tomorrow. So for a single device, in the small tens of hints is enough, but if you think of a storage box, let's say that I build a JBOF and then I put a bunch of SSDs with different hints, I might end up with a virtual block device that has hundreds, if not thousands, of hints, and I want to support that. That is true, but I think today the use cases are not there. If we get there, we would have an argument to come to file system folks and argue for those inodes. But today, I don't think we have the arguments.
That was exactly maybe my point. Like, what prevents you to store those hints as extended attributes?
Yeah. You could do that, yeah. But I think the approach and this is plumbing, is not so conceptually, yes. And the plumbing approach has been, we already have all the work on a FNCTL done for the right hints. Why add more plumbing unnecessary for this? Let's reuse that. Somebody has a problem with that. I think as long as we don't change the interface, we can always do stuff on the kernel and then, move it from one place to another. That should not be an issue. Okay, hey, thank you very much.
Thank you.
This is fun.
We are starting the second half of Luxury Talk here for today. Huge thanks to our sponsors. Is it better? Okay, thank you. Huge thanks to our sponsors without whom this event wouldn't be possible. We do have a anti-harassment policy, so essentially be nice to each other. And now I'm giving this to presenter. It's all yours.
Thank you. So, hi everyone, I'm Pratyush. I'm working for AWS, and today I want to talk about persisting user space memory over KXSec. So in this talk, I'll talk about why we want to do this, why it's important, which exact problem I'm trying to solve. Then we're going to talk about how, and in that I'm going to present maybe 2 design approaches. And the goal of this section would be to get feedback from the community and from the people attending on which design they see to be more viable. And then I'm going to talk about the current state of the patches that I have and what I plan to do with those in the future. So let's start with the most important thing, why. So the kernel gets bugs, it gets security vulnerabilities, and we constantly fix them. To apply those fixes, to apply those patches, we need to reboot the kernel. And reboots are always a problem, but if your service is stateless, and that means if you're running a workload where you may be doing some networking or maybe doing some CPU-bound workloads where it's easy to replace the host, you can just spin up another machine, you can transfer your workload onto that machine, and you can just take the load of the machine that needs to reboot, and you can go on. And that's easy, that's people what they should already be doing. But if you have a lot of state on your machine, and that means, let's say you're running a storage node where you have a multiple terabyte disk attached to it, then it's not so easy to just spin up another machine and to just transfer all of the workload to that machine. Part of the problem is if you try to do that, you're going to have to somehow transfer all of the data on disk. That takes time, and that takes a lot of network bandwidth, and you don't want to spend that time doing it. Another problem is if you do a reboot on the host and you just take it offline, that means you're losing that host for a bit of time, and that means you're losing money. But also, usually with database or storage node workloads or use cases, you have availability concerns. So you'd have maybe 2 or 3 replicas, and if one of your replicas is down for a long time, that's a problem. And if another replica happens to fail, then it's a real problem for you, and you might risk losing the data on those hosts. So for that reason, we want to make reboots as fast as possible. And one of the ways to do this is to hand over the state. Because when you reboot, you're spending time shutting down the service, you're spending time bringing it back up, and then you're probably spending time warming up the caches again if it's getting a lot of state in memory to serve requests. And that's the time you want to save. And that's why we want to be able to take the state of your service, and we want to be able to hand it across to the next kernel after reboot, so you get security patches and you get as little downtime as possible. And while I was working on this, I realized with some folks I was talking, and they also came up with a use case where, let's say you're running containers, and those are long-running workloads that you don't control. This can be useful to have a fast reboot. You can use something like checkpoint restore in user space, and you can quickly bring those hosts down, bring it back up, and resume the workloads. And with this handing over memory, instead of flushing all that state to disk, you can do it faster with less downtime for those hosts. So let's, so let's see, something. Yeah, so the idea would be we would hand over memory as explained over KXSec, and if you don't want to modify your application to use this new feature that we're going to add, then you can use CREO, checkpoint restore in user space. And I actually have some patches that prove, that as a proof of concept, that it works with CREO, and instead of modifying your complex application to do this, you can just send it to CREO, and it'll do all of the things for you. That obviously comes with drawbacks of using CREO, but that is to be expected. So general high-level overview of how such a process would look. So you're running on an old kernel, you have a process that's serving customer workloads. At some point you get the notification that it's time for a reboot. So this process, it shuts itself down, takes some time to clean things up. It calls this system call called KMHO, which stands for K-exec memory handover, or we can name it something else if you want. And what's doing is the area of memory it's serialized, it hands it over to the kernel for safekeeping, and then it's going to shut itself down. And then the old kernel takes ownership of that memory, it makes sure it's reserved, it makes sure nobody else touches that memory. And then the old kernel does a K-exec, and it hands off all of that memory to the new kernel, along with other metadata that the new kernel would need to restore this. Currently, how I do it is via KHO, which is the set of patches that Alex sent out a few months ago. And the idea with KHO is before you K-exec, you call into the KHO system, you tell it to freeze the state. At that point, it calls into the hooks of the drivers and or whatever whoever else has registered hooks, and it tells them to give it whatever state. It takes that state, puts it in a binary blob. The blob is flat on device tree, but it doesn't matter. It's just some format, and that format is sort of ABI, so both kernels agree on what that looks like. It's a contract between them. And once you do that, then when you K-exec, KHO takes care of making sure none of the pages that you are handing over get trampled by the new kernel. It does that by marking them as reserved early in boot via memlock, but also make sure that before we are able to parse that information, it makes sure we are running in a reserved, known, good space. Once the handover happens, the new kernel is up and running. Now it's going to start initializing user space. It's going to start initializing the service or your process. Your process comes back up. Your process now has to discover whether it has some state that it can recover. And then it's going to call this system call again, with this time asking to get the pages back. And when it gets the pages back, what we did was we transferred the pages from the old kernel to the new kernel without ever copying them anywhere, so they're in place. It's only the metadata that gets copied around. It's the metadata that gets handed over. And the pages in place are just left untouched. So you can remap it wherever it wants and go on with its life and go on serving whatever workload it was serving. So then how can we implement something like that in the kernel? There's two ways that at least I can think of, the two obvious ones. One of them would be to do a system call. So we would create this system call that I gave an example of called KMHO. The other way could be a file system that survives K-exec. Such an idea has been proposed in the past. We have had examples like dmemfs, we have guestmemfs, pkram, pkernfs, and a bunch of those, and even I see in this conference there's already a couple of talks regarding this. There's trade-offs on both sides. There's some things that a system call can do better, there's some things the file system can do better, and maybe let's go through with some examples of how this would look like. And yeah, just to mention, a little bit of a difference between the goals of these file systems I mentioned, like guestmemfs or pkram, is they're largely meant to be used by virtual machines, so by a hypervisor to live update while keeping virtual machine state. But they don't serve as well the goal of handing over user space memory, and maybe we can combine all of that into a single file system that does it all. So system call. Let's see how that would look like. So we would create this system call named KMHO. It can have two modes of operation. So the first one would be before you K-exec, you want to hand over the memory to the kernel. And then after you K-exec, you want to take the memory back and resume your workflow. So this is just an example, just to paint a picture of how such thing can be used by a user space application. So let's say you're going to have an operation called handover. And with this handover operation, you're going to give it obviously the ranges of memory that you wanted to carry across, and you would also want to give it a key. And this key is important because if you have, let's say, 5 processes that want to hand over memory, they each need to know, or the kernel needs to know which one is which and who's asking for what memory. So it's just a simple idea. Obviously, there are problems with this, as in you don't know what key you want to use and key discovery, but we'll get to that in a bit. And then, for example, you would just do this thing. You would create a range. You would give it the ranges of memory you want to save. Here, the process just uses a hard-coded key because maybe when you write the program or the service, you know already which process gets which key, and it sets the ranges. It does the system call. When the system call happens, when it succeeds, these pages are transferred from the user memory, from the user space to the kernel space. They are unmapped from the user process, so it can no longer access them. They are marked as reserved, or they're not going to be handed over to another allocator or anything. They're just kept safe, untouched. And after that, the process can do any other cleanup it wants and exit. Then, once the kexec happens and all of this kho handover happens, you're gonna take the process comes back up. It's gonna wanna get its pages back. To do that, it's gonna call this takeover operation, and in this operation, it's gonna again give the key that it originally provided to the kernel to identify which pages the kernel should hand over, and then the ranges of memory. The interesting difference with takeover compared to handover is in handover there is only base and length, but with takeover there's something called remap address, and this isn't really set in stone, but the idea is you might not want to get back the original memory at the original location. So for example, if you have a page at 0x10,000, right now you might have something else at 0x10,000, or you may want to have it in a different place. For example, with CREW, a lot of the times if it's preloading pages, then it can't just put them anywhere because it has its own memory areas. So you can ask the kernel to take the original base, and whatever the pages were at the original address, just remap them to somewhere else. And the rest of the operation is an handover, so the kernel maps the pages into user space, address space. It moves its ownership over and it adds them to whatever LRU lists and everything. And then it goes on. From there, the process can reserialize whatever state it needs and move on. So an example call would look like you would just set the base, the length, and the new address that you want. It can be the same as base, it can be something else. And the original key, so the key has to be the same, because if it's a different key, then it won't be able to find those pages. And then you provide the range of memory, you do the system call, and from there on you have the memory mapped in your space, and it should have all of the same contents as before.
Question now or after?
You can have it now.
That means that the new process must know what the original address was.
Yes.
That's very cumbersome. You probably want a way to name the ranges instead.
Yeah. That we'll get to. So this API doesn't do that right now. And with a file system, that becomes easier. And that makes it a good case for doing it.
I was kind of about to say the same thing, that you're kind of missing a discovery mechanism here that a file system naturally gives you, you know?
Yeah. So right now, because so essentially this evolved organically by me trying to implement this in CREW. And with CREW, you already have images that store the addresses everywhere. So at least for the proof of concept that I wrote, it's not a big problem, but yeah, you're right. Both naming is a problem with this, wherein how do you discover you're not using someone else's key, and discovery of what ranges you have.
Yeah, and if you've got multiple processes, you know, like multiple instances of the same process, then you can't hard code the keys anymore. You need some kind of key distribution thing where you could have rather directories in a file system. Also, what's the permissions model? How do you prevent one process? With file system, you get POSIX permissions on your files. So I'm really, I'm obviously biased because I'm the author of one of those file system approaches, but I really think that you get a lot more with the file system, and I'm keen to understand what the system call gives you over that. What are the benefits?
Yeah, I have that later on. So I'll talk about the comparison between using a file system and this system call.
So I'm assuming that you currently only focus on anonymous memory, right?
Yes, yes.
Like your applications, how would they actually know which kind of memory they can punch in there? And does it apply to all applications, or are you just focusing on one example of a database? Because I mean, as soon as you involve shared memory or something like that, that approach would not work anymore.
Yeah, so for now, I'm only focusing on anonymous memory. I haven't really looked at how we can do shared memory. I'm not sure. I don't have an answer on how we can do shared memory because I didn't really think into that.
Probably you should look into using a file system.
Mm-hmm. Yeah. So then, let's get to the next slide, which talks about exactly that. Sorry, there's another question.
I just wanted to ask, so what's the contract with processes for the syscall that have multiple threads, so like multiple tasks with access to the same memory? Do you synchronize that within the kernel when you do KMHO, or is that responsibility offloaded to the process? Because it might be problematic for like languages like Golang, where their concurrency model doesn't map nicely to the kernel threading model.
So the idea is, yes, the kernel will do the synchronization and it'll make sure there are no races.
Okay.
So the synchronization will be in the kernel. All right. The question?
How do you ensure that the virtual space is still available after the reboot because of the address space randomization? So if the memory that you're preserving was mapped at a particular address, and after the reboot, if you want to remap it at the same address, like you preserve the address like as a hint, but what happens if you can't?
Sorry, I think if you can't map it to the original address.
Yeah.
So then you would set a new address in remap address, and you can just
reboot again. Or what?
So let me understand the question. So you're saying, let's say I have something mapped at 0x1000, and then
then you reboot. You start your application. You try to attach to the previous address, and that VA is taken. You cannot.
So then what you would give in base is 0x1000, which is the original address that you saved it at. And then in remap address, you can give it a new address. So what you're saying is, give me the memory that was at 0x1000 and put it at some other address. Does that make sense?
So basically, the memory that you preserve can be mapped at a different address after the reboot.
Yes.
And everything should just work, like all the internal pointers, everything should just work?
That should be the responsibility of the application, to make sure. So if you remap, let's say you have a big chunk of memory that you use for cache, then it's the responsibility of the application if you want to do that. If you don't want to do that, then just map it at the original place. There's nothing stopping you from doing that.
Address space randomization might stop you.
Sorry?
Address space randomization might stop you mapping at the early.
Aha, okay.
And also new kernel may have something different.
It will be restored with the same address. Always.
So you mean randomization in the user space, user address space?
Yes.
Can you repeat the question, please?
So the question was, what if we can't? What if we map it to a different address? How would we update the pointers? And there's no real answer from the kernel side. I think it would then have to be the user space.
Yeah, my main question is like, how do we guarantee that that address is still available to be mapped, like start and end, like.
You mean you have access to your memory mappings? You can.
So the EA20 map cannot change because you're not really going through the BIOS again.
It's not about EA20. It's about the user process VA space.
Sure. Well, I think what he's saying is that the old kernel knows what was in use by user space. It can relay that to the new kernel and attempt to keep it all the same, but that doesn't address your concern about the randomization. I think that's
so with
what does Priya do today?
Doesn't, as far as I know.
So Crew will restore the exactly the same address layout
in the restored process.
Yeah.
With Creo, we don't have this problem.
No, with Creo, if you want to do pre-mapping before you go into the parasite, then you would have to map at a different stress.
So when we pre-map mappings, we just do this to restore the memory content and to restore VMAs. But before resuming process, we move these mappings to the old addresses.
Yeah, yeah. And so, which is why this remap address exists, because you want to take the memory that was originally at some address and have it at some address. Yeah. But so to get back to the question about address-based randomization, you can't have it. Or you would have to have some mechanism to then move all your pointers around, which I don't know if you can. So, file systems seem to be the popular option. So I'll talk about the other side of things. You can have a file system, maybe something like what James is proposing with guest memfs. Obviously, it's meant more for virtual machines, but maybe we can have it meet both goals. Let's say we have an imaginary file system called care2fs. We mount it to a directory, and then what your application would just need to do is the same old stuff it does when mapping files. It would open a file descriptor, it would do an mmap, it would do whatever it needs to do, it will munmap, and when you kexec that file, all of the pages are still in the same place. You can remap the file after a kexec, and you can do your thing again, and you can just move on with it. And the nice thing with file systems, as was discussed a few moments ago, was you get naming, you get permissions for free, basically, because they're already implemented, they're well understood, solve problems. So you don't have to do any kind of discovery of what your key should be. You can give permissions to different users to access different things. And you are using the same APIs in your application that you always use. There's nothing new, there's nothing fancy. The downside is, for one, you don't get anonymous memory, because then any other process with the same permissions as you can access your memory, which should be anonymous. Normally it would have to ptrace you at least, so it would have to have permissions to ptrace you, but if you're with a file system, there's no stopping anybody else from mapping the same file and doing anything with it. There can be some hacky stuff that you can do with splicing. So you have anonymous memory, then you do maybe some sort of zero copy splice into the file, and then you do a kexec, then you come back, then you do a splice again and unlink the file, which makes the argument with syscall being just a little bit simpler to use. So, do you have a question?
I was just about to ask about the splicing, so thanks.
I mean, we do have to some degree like memfds, which are like anonymous file descriptors, where you could allocate an anonymous file descriptor using some ID or I don't know what, and then just keep working on that. And I mean, I'm not buying the security concern that anonymous means that somebody can do stuff with your things. I mean, you have permissions and things like that. I don't buy it. I don't understand what the problem is with not having anonymous memory.
But then with normally anybody else in your process,
you can also access all of your guest memory using proc self mem.
No, but self you can. No, any other process can't, right?
Right, but isn't that a problem that can be fixed by permissions?
Yeah, probably. I think so. So if you maybe separate your processes like into different users and things like that, yeah, I think it can be solved.
I have a slightly different question, and that is, as soon as you transfer that memory essentially into this saved world, let's put it like that, is it still movable? How is it managed? What about memory compaction, all of that? How can it be abused?
So the patches right now don't support, so the K2 patches right now don't support any kind of moving, but I don't see why we can't implement that if you want. The cost would obviously be you would spend time doing this, so it has to be up to be tuned, because if you do compaction, if you do move memory around, you're going to spend time. Maybe you don't want to spend that much time, but I don't see why we can't do that.
So there's a function of time here, right? So first you're running as normal anonymous memory. You have your process that just runs out of its memory. Then you have that splice call that turns that process memory into a file. At that point, it's just a file in the file system at the end of it. It may be an in-memory file system, but it is just a file in the file system. At which point it can still be movable. You don't actually care as much, right? Because as long as the reference just stays the same to that memory, you're good. As long as the internal file system can track that. And then eventually you have the KHO serialization phase, at which point KHO needs to serialize where exactly in physical memory all of its downstream data resides. And after that point, you can no longer move. But KHO itself only gives you the tools to take care of that. You wouldn't need to go and actually limit that movement after that yourself, but you can. You can literally, as part of KHO creation, you can just say, as of now, no longer movable. Up to that point, you can. So all of that serialization phase of user space, you can make movable. After that, once you create the KHO DT, you can't.
Mm-hmm. And I suppose there may be a case for doing it after KHO, so right before your k-execing, or you might have more free memory that you might want to use to compact stuff, but I don't see why even that we can't implement, right?
I just want to say about the security concerns with ptrace and stuff. I don't know how much you would want to use this for like nested workloads with containers and everything else, but like the ptrace restrictions are more strict than file system related restrictions. I mean, for one case, I mean, with user namespace and stuff like that, like there are protections such that you can't attack things from outside the user namespace and all the rest of it. You would, if you were to just trade it for regular POSIX file permissions, I think you would lose that. I don't know how much of an issue that is in practice for what you would use it for, but there is a difference.
Yeah. Right, don't see any other questions, so. Alright, so currently I have a proof of concept and it works. For me, it started out as using Creo, so I basically have more or less this KMHO system call that I showed. But as I said again, if there's more strong or good arguments for file systems, I don't see a problem with doing that either. Again, for Creo, we might have to do some splicing magic to make sure there's zero copy transfer from anonymous memory to a file descriptor or to a file, but I don't see why that also can't happen. I have some patches for Creo, really hacky, that make this work, and I plan to send out an RFC, and the idea is get the feedback, see what implementation people like to see, and then we can I can send out some patches. I wanted to do a demo, but unfortunately screen share doesn't work. Let me give it another try. Let's see if it works this time. Otherwise, maybe someone can just... I mean, the demo on its own doesn't make that much sense, so people might not be able to understand just by looking at the video. But let me see if I get lucky this time. Yeah, doesn't work. Alright, let's move on without that. If somebody's interested, you can go look at this thing. What it roughly does is it runs a simple process that if you press a button, it's going to verify the memory contents it knows beforehand. And then you call Creo, Creo saves that memory using KMHO, does a kexec, restores it, and makes sure the contents are again the same after restore. So, now I want to talk about going deeper into this madness of handing stuff over kexec. And so one of the things is, let's say you're running a memory constrained system, you have a bunch of stuff in swap. You don't want to, obviously, since you're memory constrained, you can't bring it all back. And you still want to do a kexec, you still want to leave that stuff in swap. So once we have this thing dialed down, then we can start looking at using KHO to move swap contents across. And in the same vein, a lot of databases like I think MariaDB rely on the page cache for performance. they don't maintain their own disk cache or cache of their data. So we would also want to serialize the page cache state and then hand it over to the next kernel, so it already comes with a warmed up page cache. And you'll have fragmentation everywhere, but at least you'll be fast, so that's the upside. And yeah, that's about all I had. I think I'm a bit early, so if there are questions, happy to take them.
Just one thing I want to mention. So, I mean, it looks like you're going to go with the file system approach, but I just want to say, if you do end up going with the syscall, there are just two things I want to mention, which is that one, in general, I would say you probably want to avoid going with a multiplexer design. You probably should have just separate syscalls for each operation. And also the other thing is that if you want to have the structures, I'm a little bit biased, but I would recommend trying to use extensible structs, because if you plan to add extensions later, it's a pain in the ass if you don't do it from the outset.
Yeah, I wanted to make them simpler for the talk, but yeah, we'd have to add a bunch of stuff. But I have a question, sorry. Why do you think multiplexing is a problem?
Long story short. Without pointing at examples, I mean, it's sort of so I can't give you a concrete exact problem that it is, but it sort of it boils down to, like, there are certain things that it makes more complicated. I mean, like, if you have to do second filtering of it, or if you have to do like user space when they have to trace it and so on, it makes those things more complicated. And like from an API perspective, it's one of those things where, like, we have multiplexers in the kernel, but like I would say that there needs to be a strong reason why it needs to be a multiplexer. If there's like two operations that are like related but distinct, like there's nothing wrong with just burning two numbers for it. Like,
yeah, fair enough. Yeah. Is there someone in the back with a question?
Hello.
I just wanted to quickly add to that, like having two system calls for things retains your type safety to some degree, right? Like because if you multiplex, all your type safety always goes down the drain. But actually I wanted to say something different. I also wanted to emphasize that going for file systems, in my opinion, is the way to go, simply because, you know, thinking about the kind of resources that we want to pass over, there's a lot of stuff that isn't like conceptually memory so much, but a file, like for example DHCP leases or TPM measurement logs, right? Like they are literally files typically anyway, right? And from my experience with systemd background, this is kind of also the data that people want to hand over to KX again through KX again currently can't do. So I really like a file system, in particular because, like in systemd, we nowadays split up the system like into this hierarchy of slices and services and then containers and things and so on. This is really nicely mapped into a file system. I mean, this is what cgroupfs, for example, exactly does. So from my perspective, it would be wonderful if we had a proper file system with directories and nesting and things like that. I mean, it doesn't have to be like a fully POSIX one with, I don't know, device nodes and shit, but if it has directories and files that we can name properly, then this would be really, really nice for us to map, because we can delegate things with permissions and match them exactly, the hierarchy of the services and containers and what else we have. The problem that I always see with like these things that use identifiers, like linear identifiers, is always that this kind of hierarchy that a system is these days for many use cases cannot really map through this. And again, I also think like if you have files that you want to pass over, and these tools that currently write those files, they generally have no like they have very much an understanding of a file system, but they do not have understanding of calling some special system call doing special memory management. Right, so please, to keep the big picture in view, really consider the file system way to go. And from my perspective, I would love to support this in systemd, but I don't see how we could ever do this nicely if it's not a file system.
Yeah, thanks for the comments.
I must be missing something, why we can't leverage what we do for Hibernate.
Because you don't upgrade the kernel in Hibernate, so you just dump all of the core of the kernel and you just bring up the same thing. So
right, but can you not dump not the kernel, but like how they handle the process dumping? Stored in the same sort of way.
To some extent, that's how GHO does. Is it serializes the state it needs to hand over, and then the new kernel gets it. But we don't want to dump it to disk, of course, because just wastes time.
Okay.
But did I understand your question, or?
Yeah. No. Yeah.
Okay. Thank you.
That's what I was asking.
So I attend the session in the morning, and also see there are some arguments about the handover, about the MMU, the persistent memory, and the next the ACPI. Do you guys will have a committee to convince each other to unify the method? Finally, there is only one method to hand over all these things to the
Talk to these guys.
That's what they chose.
Yeah, I think all you should discuss this.
So Alex and James.
And second
should be
That's above tomorrow.
Yeah, I plan to attend that. So there's a BOF tomorrow where we talk about exactly these problems.
Yeah, that's great. Maybe you can have an internal offline memory mail to discuss this. And the second is, I'm from Red Hat, and since Red 10, we will stop supporting KZ reboot formally because of some fatal drawbacks. So I think firstly, we should solve those problems, and then we talk about these things in upstream.
I'm not sure what the problems you mentioned, but maybe
For example,
we can take...
the first one is the shutdown method of the driver.
Yes.
You know, there's some on-flight shutdown of the DMA. So, and those drivers, we very hardly to discover. You can see Red Hat, we have found, debugged and found many problems and have added those shutdown methods, but still there are some missing. Second is about the NVIDIA GPU and AMD GPU. They cannot shut down and restart in the kernel because of the potential issue. We have talked to the developer of GPU. They don't have a better way. So if this only used on the guest machine, I think all this handover is good.
Yeah.
But if it want to be used in the host, that will be a huge problem. All the hosts having the server want to use the GPU, rely on GPU.
Yeah, I think, but I agree that those are problems, but I don't think they have to be solved at the same time because they're largely independent problems. But yeah, I think if you can figure out how to fix those, really good.
Yeah, possible at the same time. And I think I'm the upstream Kidam kernel maintainer, and I think this should be decided by the KZ maintainer Eric Badman, but I also help him to review those trivial patches of KZ. So I hope this matter should be unified into one and can take all those things over KZ to the second kernel.
Yeah.
Right. Okay, thank you.
Thank you.
I was wondering whether if you had a process that was waiting on a child processor, it forked, how you'd restore that kind of information, like PIDs and FDs and so on?
That would be on you to restore. So the
is it kind of quite manual, this using the KHO call, and you have to kind of figure out how to take the state you've been handed back and reconstruct? And
so the responsibility of state discovery would be on the process.
Okay.
I mean, you can just use Creo then.
Yeah, but it doesn't upgrade your process itself, so that's the drawback.
Yeah, I just wanted to sort of also touch on that topic of updating, right? One of the risks or the problems of trying to directly serialize kernel state like we do for Hibernate, let's say you wanted to just save VMAs or save MM structs, is you then, if you try and do a big kernel upgrade, that binary blob is going to break. And one thing that KHO does is it doesn't just save binary blobs, but it has this explicit serialize and deserialize phase. So that's really useful for doing big kernel upgrades, and also if you do something like allow the process to restore things, then you can change your process version, which is also really important. So I think using this as a mechanism to do big kernel upgrades and big process upgrades and change the layout of memory, change binary structures is something that we should be careful to continue to allow. Yeah.
There is a few other things behind that on KHO, such as, for example, imaging, you have storage system with large amount of spinning rust, which we still have a lot of in data centers. Those things takes minutes to probe with the SCSI stack. We could serialize a lot of that information and deserialize it on the other kernel. To go back to what the Red Hat person over there was saying, I've been arguing that the shutdown callback for KExec is the wrong thing to do for about a decade. I didn't fight that battle hard enough, but when Eric wrote KExec, I probably should have. Shutdown will actively go parse things down, turn some device into D3 states, things like this, where the new kernel just can't get them back out of. The right thing to do probably would have been to unbind drivers instead, because this is typically what we do when you RM mod a driver, and mod probe maybe a new version of it or something like this, or unbind VFIO and bind the driver and vice versa. So unbind type of operation would have made more sense in a KExec context. Now, of course, we have workaround for shutdown all over the place, and so if we were to change it, we'll probably break something. But there's definitely a cold hard look that we need to have at the current community on to how we do KExec, because there is a lot of demand for KExec to become a bit more common as a fast reboot mechanism, and it is not reliable. And it is not reliable in large part because of how drivers are handled and because drivers are done the wrong way. So food for thoughts, but definitely an ongoing issue.
Yeah, thanks. So let me start a poll. I wanted to do that, so let me figure that out. Okay, I have started a poll on this. File system is Cisco. I guess people here can raise hands. So people who think file system is the way to go, and then people who think Cisco is the way to go. I guess I have my answer. Thank you. I guess I'll let people online vote as well. Oh wait, sorry, I didn't publish. That's stupid. Oh.
And just one more thing, it doesn't have to be like guest MFS, which is quite tailored for virtual machines, and it also doesn't have to be a new file system. One of the ideas that we floated is making huge TLBFS persistent across KExec, or making devtempfs persistent. You know, you could take an existing file system and kind of add persistence to it. Yeah.
Yeah. All right then, thank you for attending the talk. Thanks for all the feedback and the discussion. And you'll see patches soon with the file system then. Thank you.
I'll come back in a moment.
Please, some quiet, please. We'd like to start the next talk. They're all yours.
Okay, let's maybe start in 20 seconds. And the kickback continues. Okay, hello everyone. Welcome to this presentation. My name is Ben. I'm from ByteDance. I'm a software engineer in the System Technologies and Engineering team. So today I'm going to talk about ACPI fast handover, also through KExec live update. So this is by no means a complete work. It's just maybe a start and also a continuation of what we have maybe looked at since a couple of years ago, including like in the scenario of virtualization host, how we can live update our KVM host kernel. So yeah, let's start. Learning how to click the next slide. Okay, so here is the agenda. So I'll go for some introduction to the main problem here. Oops, too quick. I think it takes time to really reflect my clicking. Okay, so agenda. First is the introduction. And also I'll give a quick overview of ACPI kernel code that's happening during the boot. And then it's mainly the proof of concept or the proposed solution to how we can preserve ACPI state across KExec. And then it's some looking at the conclusion and the future plan. Okay, so I will not repeat on why we want to KExec. So briefly, it's a way to allow you to quickly flip from one kernel to another. And usually timing or how long it takes is what matters here. So as I said, we looked at different aspects of that whole process and what is taking time in the previous work. And ACPI is just another one. So previously we looked at how SMP parallel boot can save the time, how you can manage your memory wisely, like using the huge pages, HVO, work, etc., and how we can maybe allow list the PCI probing so that you can save time scanning the PCI bus, etc. And with all those previous work, we managed to trim down quite a little bit from the new kernel booting process. It was maybe from tens of seconds or maybe 1 minute, and then now it's almost down to well below 1 second. So here I draw a graph based on one of the physical machines I took and KExec, and so the bar here, the width of each block represents maybe just one line in the kernel demessage line, and I set the width by their difference in their timestamp. So the wider it is, the more time it's taken, and the overall horizontally time here is around 600, 700 milliseconds for a physical machine with 128 cores, 512 gigs memory, and a bunch of platform devices and also PCI devices. So we have almost excluded all those very expensive parts, and now the outstanding one is this one thing that's marked in the square here is the ACPI part. So ACPI init, that is the entry point for this whole work in the new kernel, and it does all the ACPI-related initialization and relates to enumerating the devices of the device tree, and finally bring up all the necessary drivers. So the time of this thing, we'll see later, it's around 300 milliseconds. So it's quite obvious that we should think about maybe can we do something about it to speed this up. And that's the topic of today. Okay. So yeah, here is another overview. It's a call chain in the new kernel. So you first start from the entry point of the kernel, which is kernel init, and then eventually it will land to this almost later part of the thing called init calls. So this is just a list of callbacks that the kernel will do one by one, and one of them is called ACPI init. It's registered as one of the init call. And this thing is what we were talking about, that's taking hundreds of milliseconds. Okay, the other question is what is exactly happening here, and is there anything we can speed up? So I'll just go one level below this function, which is kind of meat of this ACPI init call. So first step is ACPI load tables, and it's following the spec to load and parse all the AML byte code and all the format that's following the standard. And after loading the table, next step is initialize all the objects that kind of more of the kernel logic handling. The parser, the device driver, the ACPI driver, etc. And then there's a step that's specific for processors. It's called the early processor control setup. It's part of the standard that you need to invoke one of the function, one of the method in the table, interpret it and execute all the opcodes so that your processor is properly set up for operation. So it's mainly about several feature bits that need to be agreed upon by the kernel and the platform and the CPU. And finally, it's this ACPI scan init that's mainly how the whole device tree is worked, and drivers will pick up what they recognize and continue from there. Okay, so with that in mind, we can actually check more of the details. So first thing, I'll just show you what we talked about. So adding this nice debug capability to the kernel command line, init call debug equal 1, and then boot or kexec, we can show some nice output about each init call functions. So here it's easy to grab out all the relative timestamps and cost, and then just sort them by how long each subsystem takes. And the ACPI init is a very, by far the most outstanding one, which is, in this case, 280 milliseconds. So it proves why we care. Okay, then from there, we are utilizing another nice tool in the kernel in the ftrace features. This is called function graph tracer. So if you enable that, conveniently available from the command line, so just add a few more kernel boot parameters, you can see the process of the booting. So I listed the specific arguments I added here. First one is selecting the tracer using ftrace equals, and then I defined what function to trace and how many levels to go into that function, just to trace the cost of entry and exit of each function call. So out of the long body of that function, we can easily notice which maybe sub-functions are more expensive here. So yeah, just quickly, it repeats what we explained. First one that's expensive is ACPI load tables. It's over about 200 milliseconds. And the second one is the processor stuff. It's almost 900. And the third one is the scan init. This is over 400. These numbers don't add up to the previous tracing because we are introducing more overhead to it. But proportionally, we can have a feel of what's expensive here. Yeah, okay, so trying to further break down this, so let's focus on the first one. It's the ACPI load tables. We can easily add, maybe change the parameter to trace specifically this part, and then show its callees. So it's not hard to notice which few operations are more expensive. So first one is the installation of some region handlers as the beginning of the load tables operation. This one is just the kernel a static logic there that is required before the ACPI parsing starts. So we will just keep this as is and continue to the next one, which is the table loading. So table loading is it's kind of the main focus of this talk, and what it does is mostly just passes all the data structure from the firmware. So it's all the ACPI byte or blobs that need to be handled using a parser. And I think that is one thing we could do in order to optimize. Okay, and then the third one, the namespace initialization, it doesn't seem to be very expensive. So we will just keep it as it is too. Okay, that's the first main part. The second one, briefly talk about this, is the processor control setup. So as per the standard, we need to call one of the two methods defined in the ACPI table. And it's used to report the supported capability bits to the platform. So I think in most cases, we don't introduce big changes in that regard from the software. So the question here is rather to have maybe decide how we can check or test if it's safe or possible to bypass this. So this is more of an open question for now. Okay, and then there's a third part that's ACPI scanning. There is some non-trivial changes here, but just for speeding up, I think there's just only one possibility, which is about if the definition of device init can be skipped. So it's similar to the previous question. And it does show some cost here, but we don't have an answer yet. I think the rationale is, on the one hand, the kernel driver could be exactly the same, so there's maybe no behavior change from the driver side. And for the device, I think there are two cases. One is if the device is probably not relevant to the operation, but maybe it's just not actually used, then maybe there's an option for the system to decide if certain devices are needed. Maybe we have a similar whitelist mechanism so that expensive initialization can be skipped. Or maybe the device driver can, or the device can advise that it's maybe safe to pass, and then we can optionally also omit this. Okay, so yeah, now let's talk about the central bit we want to think about. It's about saving and restoring the state. So the top of the idea is to add a new mode to the ACPI loading table. So we are imagining an ACPI mode here called restore, and that will be explicitly used if it's been key-exec into the new kernel, so that the new kernel has a chance of picking up some state from the previous one, and then maybe avoid certain expensive loads. So if this mode is enabled, we will take a different code path in the ACPI load tables function to restore from somewhere, which will be a memory reservation mechanism, like we talked a lot about. So in order to do this, we can tell it hinges on one is a way to very predictably preserve memory across save and restore. And it is a fairly strong requirement if we look at the details depending on how you implement this. But in my case, it's kind of pretty rigid operating. And then it should be simple and fast. Because if you need to do any complex setup or scatter-gather operations or huge data structure traversing, it may still cost you some time in the process, even before. Yeah.
Thank you. Two questions. The first one is you're proposing to save and restore an in-kernel binary representation of the ACPI objects, which will break as soon as the next time you update the ACPI ICA dependency or anything else, which makes this very difficult to keep compatible ABI, right? It's just vast.
Yes.
It's lots of binary data inside the kernel. Not sure also that serialization or that preservation is going to be significantly faster than a serialization, deserialization path from AML should actually be. Like, I don't understand why we're spending so much time saving and restoring, or creating objects out of that AML code, when our in-kernel representation should actually look kind of the same as that data that's already there. So it's just copying effectively, right? Which gets me to the other question I'm actually asking. What I've seen is that the effect that you saw, where we just take forever to load ACPI tables, where we have these insanely dumb callbacks that just go into SMM calls right in the boot up code, right? That takes seconds. All of these things typically only, at least for us, only affect x86 systems. I never see any of this show up in our ARM-based ACPI physical machines, which means how much of this is actually a homemade problem in having completely dumb ACPI tables compared to what they should be. And well, you have EL3. Sorry, Michael's saying you have SMM. You have EL3 on ARM the same. You can also build just as broken interfaces. We just don't. Like people on ARM usually have much more sense of, I don't know, ethics. I don't know what it is. So have you looked at what actually is the hotspot in, like, why do you have that much time that you're spending in loading these tables, and what type of objects are we actually talking about? What do we spend all this time on?
Yes, we have some idea. We will see in next slides.
Okay.
Yeah. Okay. Yeah, just to echo your comments, I fully agree with the first one point. Before we move forward with anything with this, we need to think carefully about the ABI, because anything we preserve, that will be form a contract between two kernels, and that has to be very, very carefully designed. Yeah.
And on that topic, not just going forward, but you actually need to be able to go back as well, right? If you deploy out a kernel and there's a problem, to be able to roll back. So it has to be not just forward ABI compatible, but backwards as well.
In this case, not necessarily. If there's any abnormal happening, or even if the ABI changes, maybe the binary format changes, we can still go back to the old way, which can discard all the...
Then you've got the bimodal system, right? In one direction it's nice and fast, and then in the other direction it's terrible. And I don't think that's a behavior that we necessarily want.
Yeah, I think the rollback will be more complex considering the compatibility, because if you define a certain protocol, and it has to go both ways if it's a complete solution.
I think it's honestly the hardest part of this problem, actually, is the format and the handover and the binary compatibility. Yeah, I think that is the hardest part. And that's why Alex ended up with device tree, because you get these nice compatibility flags, it's more structured, you know. Yeah.
Okay. Shall we continue? Cool. Okay, now I think that's what we need to look at, what to save and restore, which effectively forms an ABI between two kernels. So here, just for the sake of prototyping, I'm listing what are the effective bits here that we have to do the minimal work to save and restore in order for two kernels to boot at least. So this is not a proposal of an API or some sort of ABI, but rather to see what are the status is about. So there are two kinds of data structures mainly defined in this header in the kernel, and which is also taken from the SAPI CA library. So one is the tables, which are kind of just the original data, and the second is the namespace, which is after parsing created by the kernel to represent all the data structure, all the models of what ACPI is defining. So we need to basically save and restore both types. There are some other smaller ones, but these are the main one and also mainly the reason why it takes long time. So just to illustrate a little bit, for first one, the table is basically a list of entries. Each one is describing a table. So the middle column is ACPI table disk structure, pointing to a table header, which then in turn points to the actual AML table. So this is just can be seen as an array or a list of things. Next one is bigger. It's a ACPI namespace. So the node here is represented by what is specified in the AM table. So as we parse this table, we need to create nodes depending how the AML bytecode expresses. And a node forms a tree. So there's a root node, and it can have its subsequent nodes and so on and so forth. And also each node will have associated objects. Here it's called operand objects, which represents a certain state that is attached by the kernel code. It can be some callbacks, can be some data assigned to it. So each operand object can have a different type, and one type will have a function pointer, the other type may have some scalar data, etc., etc. And they are organized as a linked list assigned to one of the nodes. So in the server I tested, we have in total created over 20 key nodes, and each node have multiple objects following it. So there are more than 300 key objects. So this is a scale of the objects we need to go through if we are to use the old path. Then that's basically the reason why this takes time. So each object is currently managed by the Euro kernel memory allocation allocators, the keymalloc and keyfree. So yeah, then we are to think about how we want to preserve this across KUSAC.
Can I ask, do you have a breakdown of what those objects are? What are those 300K objects? What's the majority object type there?
I don't have a chart to see it. I think it's a lot of different. So it's I don't have maybe the ranking of it, but it's of over 20 types of things.
Okay. Well, that's the types, right? But the 20K that you had is the first level, right? So it's basically the DSDT objects.
Yes.
And I'm surprised that you have 20,000 DSDT objects in your DSDT. That's like some megabytes of AML, right?
Yes.
What are all those objects?
We have two huge OEM tables. These are, I think, half of it. And then the main ones, I think, are also the other half. So I don't have the type statistics here.
So I think that would be one of the first things to try and analyze a bit deeper. I remember we spent quite a bunch of time, and have patches on the list too if you want to take a look, in effectively removing a lot of the overhead of just having duplicate CPU entries. So one thing that is very typical in x86 ACPI tables is that your BIOS developers will literally just copy and paste their CPU description and their CPU slot description for every single possible slot in the system, which could be thousands, right? And then just completely that just explodes your complexity of the DSDT with no purpose. Like all of these nodes are doing the exact same thing, right?
Yep.
So, and if you can reduce that complexity of the underlying data structure, I think you're solving your problem without introducing any new ABI compatibility problems, and you're also accelerating the cold boot.
Yes, sounds great. I think that will be a nicer solution, makes us life easier. Cool. So okay, so I'll just continue to show you some more of the current status. So as a simple naive implementation, I just put all these objects in a preserved memory area. And that's basically the core idea of this talk, of this POC. So most of things stay as is, except that there are physical pages where they are, and their virtual addresses, which is how they're mapped by the kernel, they don't change. So we rely on this way of, being able to map it exactly the same. And then the slight complexity here is because some of the operand objects are referring to kernel addresses, which will go away if we have a new kernel. So we need to handle that as well. So first step, if we change the allocation, make sure it is in this area, and then we have most of the data preserved, the state preserved. So thankfully, it's defined by a macro in this subsystem, and we can have a different implementation to call into our preserving allocator. So that is the thing we did here. So we have new macro, and then on the path we had to patch all the unmatched key free, which is unexpected because it's supposed to use the ACPI free macro. But that's about 160 occurrences in the current kernel, and once that's fixed, our allocator would take over that memory management and allow the ACPI to do its work.
Sorry, I didn't quite follow. Where is this allocation coming from? Is it some big fixed chunk of reserved memory?
Yes. Yes. So this.
How do you guarantee that your new kernel doesn't scribble over that?
This green area is from our specifically carved out E820. So we have continuous pages that we can use and create a small allocator. I don't want to go into details about this because this is definitely not a flexible, not a good solution. But I'm hoping if we were to really do this, there can be some mechanism that can do that.
Yeah, I mean, we've spoken about KHO quite a lot.
Right.
I think it's probably another good use case for this, right? Where you can hand over your memory pages.
Yes, yes. Yeah, I wanted to mention that in the end, yes. Okay, now we have looked at. Yeah.
Did you send a patch to fix up these mismatches in ACPI ICA?
Not yet.
Will you?
Yeah.
Awesome.
Okay. Yeah, with the table loading down, before we can safely do the ACPI bus scan, which is actually traversing the node tree, we need to have some fix-up here. That is because of a problem I point out. Some objects in that preserved area have references to the addresses of the old kernel. So this step can happen either before KZAC or after. So this is a kind of a fix-up that has to be done in order for this to work. It's not clean, but I think for certain types, it's clearly what to do. And as a POC, what I did was to check each operand object's type, and then depending on what it is, we will try to clean up the state. And that's what happened before we actually use the namespace. So I gave two examples here. One is mainly the handler, which is a callback to the kernel code, how to handle this object. And the other is about memory management, memory mapping, which if I mark it as not mapped yet, the new code will try to map it properly before really accessing this region.
So Fem, how much of this is in Linux kernel code, and how much of this is in ACP-ICA upstream code?
You mean the change?
The code path you're trying to optimize, are those binary structures, is all of that defined in upstream ACP-ICA, and are you leveraging that, or is that actually Linux code?
The actual bits can be Linux specific. I did have added a function call as part of the ACP-ICA, but that's kind of independent from the rest of ACP-ICA code.
The reason I'm asking is maybe one way to tackle this problem, just trying to think out of the box on how we could potentially do this without being too hacky, right? If we can teach ACP-ICA to go into either like a version binary structure mode or even into a serialization, deserialization mode that is a lot faster than deconstructing everything from AML, even though I still don't understand why that takes long. We may actually be able to create a proper ABI out of these structures, which is required to make this really compatible.
Yeah.
During the first kernel boot, we already have.
Do you want the mic? I won't go that far.
During the first kernel boot, we've probably parsed it all, and we have that parsed data already, so we don't have to go through it all again. And I think that is what he's doing, just save restore. So he's not reparsing it, which saves a bunch of time.
Wow, yes, nice. No, my concern is that the only way to actually make this properly, like a final fixed binary structure that you can go and consume from arbitrary versions left and right, is by making it basically go through a serialization, deserialization phase, or by creating a very fixed binary representation of how things work and operate, which means you basically have to get rid of pointers, you have to get rid of a couple of other things, right? One of those two. And either of them would have to live in ACP-ICA. We're actually not even talking anymore about Linux upstream, we're talking about ACP-ICA upstream. And that was the whole point, right? Like I don't think it's about that reuse. We can't just literally reuse the existing old data that's there.
Yeah, the internal structures can become our binary.
What I don't understand is why does it take ACP-ICA so long to establish this, and would a deserialization phase be faster even? Because realistically, all that ACP-ICA does is it takes templates, serialized templates of how objects look, and then creates internal representations of those. And a serialized data format would do the exact same. There shouldn't actually be a difference. It should take as long.
I think we'll only know by profiling what's happening, actually. To be honest, I think you're finding a solution for something that we don't know where the problem is. I mean, the only thing we need to understand is what the CPI tables contains, probably for x86. I don't know if for ARM the problem is the same. It's likely to be the same, depending on how many devices are populated, and then profile it and check. Maybe there are some optimizations out there, even for not necessarily KSEC, but also for bootstrapping first-time CPI configured kernel. So I think it's better to profile it before thinking about saving and restoring things that complicates things further. That's my opinion, at least.
So question, are you actually serializing and deserializing? I mean, maybe you can...
Yeah.
Just move over. That seems to be the concentration.
So Amit's question is whether I'm actually serializing and deserializing, and no, I just use it in place.
Exactly, that's what I thought. So he's just using the in-kernel pre-parsed data from the first boot as the serialized format, as it's just the kernel data structures. He's just keeping, there's no...
Can we agree on the fact that that's a bad idea? Okay.
Because of the rollback.
Once we do
just the
this,
rollback,
any roll, just basically this is going to break. Whatever you do, this will break. It always does break. The whole reason why we have the slide is because it breaks, right? But that's the whole reason why this slide even exists. This slide exists because that data is not meant to be preserved across AKXEC. What we need is data that is meant to be preserved across per-exec, and that's either binary data that removes anything that's dynamic,
okay, so
or it's serialized state, and AML is already serialized state.
So I think what's happening is, in his use case, maybe there's ACPI tables are not changing underneath, and in your use case they are.
No, they're not. ACPI tables are not changing. The kernel changes. The kernel that implements the logic to construct these objects changes. And once it does, God knows what happens. Maybe we just introduce a new flag and suddenly, or we change the semantic of a flag, or we introduce a new field and suddenly there's padding and we just interpret random ACPI internal data as something completely different. This is hazardous, and that's why it's on RFC, and that's why FAM also put a lot of caveats on this, which is correct, right? But the final solution to this won't actually have the same performance benefits that you're showing now, right? Which is fine. I'm just still puzzled on why we even see the effects that you're seeing, and that's, I think, where we need to drill a bit deeper.
I agree. Let's first find out why it's so slow. Then we'll take it from there.
Yep, fair enough. Okay, just to add to that comment, whether we do serialization, deserialization versus using data structures in place like this, which kind of feels very hacky, I hope we can find a middle ground, which if we see it's expensive, if there's really a lot of objects, it may be better to define a well-defined data structure that can be just used as a pointer, and we can use it in place. And for anything that's reasonably fast to serialize or deserialize, we can, of course, make it more robust in design like that way. So the bottom line is, if the new kernel can have a way to see it doesn't recognize the previous data, it should discard that and maybe do it a safe way, a fallback. It may not be the normal case, but I think for the extreme low latency of KExec, some mechanism that can be more cleverer and avoid the memory copy is worthwhile.
Not happy. But one thing I'd like to make sure we caution a bit on this is this gives a false sense of performance at the end of the day then, right? So even if you have that fallback mechanism, you will only exercise that fallback mechanism once a year, once every 2 years, sometimes, right? Or ideally, hopefully. Now, the problem is when you do that, when you do exercise that fallback mechanism, you trained your customers against the good SLA. So your customers now, your downstreams, right, the ones that do the AKXEC, they will see, oh, by default, I'm only getting 200 milliseconds downtime. Amazing, I love it. And now suddenly you're saying, oh, you know what, I'm doing a kernel update. Meh, it's going to be 600 for you now, which is going to completely explode any of the constraints they were operating under. And then you're suddenly having a much bigger problem than before. If you train them to always assume 600, you live in a world where they won't configure their timeouts to be anything below, right? Whereas if they are by default typically getting 200, and now you suddenly spike from time to time, that's going to be much bigger escalations than being predictably bad.
Yeah. I completely agree. It can even be worse. Like there might be timeouts which will just declare the node dead and just remove it from the cluster. And the other clusters will do exactly the same, so it will end up in an endless reboot loop. Okay, got it. Yeah. So it seems like the only middle ground is if you can find out that the ACPI tables are not really optimized. The first boot may optimize them and then just pass down the optimized version of the tables. But yeah, we don't know what these 300,000 objects actually are. So maybe we should start from that.
Yeah, sure. I hear you.
Is it worth bringing core boot into the mix somewhere so the kernel passes the tables it receives from BIOS into core boot and core boot does the magic, whatever? Because it's not the kernel's job. Just wondering.
How many slides do you still have? Because I think we are running.
Yeah, we are running a little short on time, 2 minutes maybe.
It's 2 minutes.
2 minutes. So yeah, I can quickly finish this, and we can discuss later. Okay, so yeah, here is the conclusion slide. Then that's the timing. So we showed the original time is around 300, and then with the loading speed up, we have 100 or something. Okay, so yeah, and thankfully there's not a ton of code there required to do this, although I know there are a lot of design decisions to be made even before thinking about how to move forward. So we'll definitely need more discussion, maybe more drilling down of what exactly is taking time in my platform, and if it's a common problem for different servers, etc. And maybe there are some first-time boot optimizations can be done for the parser. Okay, and finally, I want to comment that debugging is a little bit tricky if you have very early kernel code. So I relied on serial output, but it's not great. So if any suggestion, it's all welcome. And just to finalize this, I listed a few things we can talk, but I think we already talked enough about what the next step can be. Okay, so with all the references and the acknowledgements, thank you guys for working together on this. And then we have the last slide. Thank you.
Just thinking more about this idea of getting the ACPI tables optimized, like this actually seems like the best way to do it, to be honest, is let your cold boot be slow, optimize it, and I even wonder if you could make that a user space, some user space functionality, that on your cold boot, some user space process comes, reads your ACPI tables, there's all sorts of optimization, and pushes some optimized ACPI tables back into the kernel that then get used, or something like that.
That's where I was going to go.
Did you say cold boot or core boot? Okay. Yeah. But there's no reason not to do this in user space even, right? This optimization. Yeah. Cool. Anyone else?
What was the core boot comment?
I think similar to what James just said, the kernel shouldn't be in the business of optimizing ACPI tables, and core boot already has some code that deals with stuff like that. So pass on the tables that we got from BIOS into core boot and add that magic into core boot.
But we need to understand how much we can actually save by optimizing these tables, right? Eventually, if you end up, yeah. So I think.
Okay, thank you. Break time.
So we are going to be on a break for half an hour.
I'm working on the memory and so like having our virtual machine memory and my own memory state. It's still the same stuff, but the approach has changed since last year. It's monolithic design for everything. This year, it's moving into this multi-level framework. Different models using frameworks to pass over criminal states. What are you up to now? Why did you leave?
I think that's not intermittent.
Yes, exactly. A whole bunch of laser struck page visualization and doing all those things.
Okay.
And how long? Yeah, you should get my latest selection. It's a coffee. It's a coffee. Nice to touch you more later. What's up?
This is the right one. This is the beginning, right?
So people will see like this, not the full screen slides, just a small one.
We can make it bigger.
Can you make them full screen because we have some details and it's going to be like this?
We need to ask them to make the adjustments.
But there's nobody here. Or not if there's somebody.
I'll go there after we. You can start with this and then we go to fuller screen.
We can remove, like, we can go full screen for the slides and then go back. So if there is any discussion in the chat or anything. Yes, like it's too small, I think.
Of course, if we
Especially at the back.
all the three like DLF,
All right. So we'd like to start with the next talk. The stage is yours.
Yes.
Can we have the slides a little bigger? Like full screen? Okay. So that's all we can get? Okay, guys, you have to squint. Okay, hi everyone. There's three of us. We are here to talk about GitLab use in the kernel community and around it, and how it's actually working for people and not hurting anybody. So, Helen.
Hello, my name is Ellen Koike. I am a senior software engineer at Collabora. I was a former Mesa CI contributor. I'm currently maintainer of the RMCI as well. And I'm also part of the kernel CI team, trying to improve tests for the kernel. And I'm working from Brazil.
Oh, that's me. I'm Nikolai Kondrashov. I work at Red Hat in the CKI project, which also does CI. I'm also doing KCIDB development and design and everything at kernel CI, and I help manage technical steering committee, and I do electronics and embedded as a hobby.
And I'm Thales. I'm a senior engineer in Red Hat, working also in CKI, and I'm tagging along for them in the kernel CI. I'm also working from Brazil.
Thank you. So I guess a lot of you know this story, if not all. 2023 Maintainer Summit, there was a discussion about maintainer burnout and the overloaded maintainers. And in particular, Linus jumped in and said that reviewing is boring and that's no wonder people don't want to do it. And he keeps seeing huge patches go into the mail list and nothing happening to them. And finally, he said that perhaps what we need is to move away from the email workflow. Yeah, it has been an interesting statement, which we've been waiting for a while, honestly. But yeah, you all know email workflow, right? It's conceptually, it's quite simple. Just review and then merge, blah, blah, blah. But in fact, a lot of burden goes onto maintainers, has been discussed on that discussion at the Maintainers Summit. and maintainers have to test stuff, have to merge, have to manage, and lots of patches, so it's difficult. The email workflow is made a little better by patchwork, which helps you manage and track everything that's happening in there. It tracks all the threads and the status of the patches, like if they're approved or reviewed or whatever, and it also can track the testing status, so it accepts testing data, testing results there, and it can show the summary, like somewhat structured, explaining what worked and what didn't, which is good. The problem is that it's based on the email workflow, which is not so amenable to automation and integration. So what's the next best thing? There's like, where do we go from the email workflow? There's a lot of discussion, a lot of options, and ultimately people will choose whatever they want, and that's what we'll end up with, like some people using this, some people using that. These are just a few options that people were discussing, that just random quotes. And there are, of course, also people who will forever be with the mail workflow, and they consider people who cannot manage it or don't want to manage it wimps. And this happens. So we think that GitForge is a good option. GitForge is a good option. And it's quite a popular one, and as you all know, most developers these days use GitForges like GitHub or GitLab. And I think that they help a lot because they allow you to integrate your process and automate a lot of your work and make a lot of things simpler and faster. They are not without their drawbacks, of course. So again, there's plenty of choice, and ultimately people will choose what they like. And you can do various metrics and whatever you prefer, like for example, like this metric that SourceHot is advertising is the performance of the web UI. So it's important for people, of course, to have a snappy UI, which is not always possible with the web UI. But ultimately, we are here to talk about just one option, which we're familiar with. We spend a lot of time working with it at CKI and other places. So, and it's being used already. So some just keep a mirror there, right? Yeah, like Tegra, for example. Some also track issues like the, it's hard to see. Yeah, like the Novo driver and the XE driver and yeah, other Intel drivers. And some still use the CI in GitLab. Yeah, like MediaCI here, MediaFox. And some use even MRs, like the MSM driver, use MRs for the full development cycle. And some use MRs a lot. We'll get into those details a little later. But we are going to focus right now specifically on CI because we think it's the least disruptive but the most impactful thing that can happen to your workflow in the kernel. I know it's difficult to move from workflow or change things, but you don't have to take all of GitLab at once or ever. You can pick and choose what you want to use, as we just briefly explained, but we'll show in detail later. So, over to Dallas now.
So, if you never played with GitLab CI before and want a small guide to it, be you a developer or a maintainer, it basically consists of two parts, the kernel tree and a CI configuration. We are talking about GitLab, so the first step there would be to create a account there. It's very simple. You just need to input your name, your emails, or username, and you're done. I would highly recommend using two-factor authentication and putting your SSH key there. And then all you have to do is create a new folder, initialize a Git repository, commit anything there, and add your remote for whatever name you want under your namespace, which usually is your username. And finally, push. And you already have a CI repository on GitLab. It will create a private repository. If you want to, you can make it public later. Now, about the actual CI configuration. you can write a simple CI possible. They have plenty of documentation there about the YAML syntax. But all you need to do is select an image, a container image that can compile the kernel. And here I'm using builder how hide from CKI. Then make any configuration you want. And finally, compile the kernel. That's all you need to do to compile the kernel in the CI in GitLab. But wait, there is something missing here. Where does the tree enter there? So there are two ways to connect your tree to a CI configuration. First one, you can clone it within the CI configuration. So just add a step there, clone your tree, wherever it lives, wherever it's planted, and then go to your CI repo, configurations, and add, well, since I use a custom name here, add the name of your file, your CI configuration file that you just created. And in the next push for your CI repo, or manually triggering the pipeline, you have a CI running a compilation for the kernel. And the job will look a little bit like this. You can see you're making the configuration and compile the kernel, and success. So the second option there, if you are willing to move your tree or mirror your tree to GitLab, you can start for a fork to save some resources. Like they have a limited 10 gigabytes for repositories there, and Linux is already 5 gigabytes, so it's nice to start from a fork. It doesn't take much as well. Just click on the fork button, add a name there under your namespace, wait a couple of minutes, and you have a fork. Now, to configure the CI, same step as before, go to the CI configuration page and point to the CI configuration file. Notice that the CI configuration file needs to be pointed at in your CI repo, right? So the name of the file, add namespace, name of the CI repository, and the branch you want there. And finally, in your next push for the tree repository, or manually triggering the pipeline, you have your pipeline running for your kernel tree. And that's it. You already have a pipeline for compiling your kernel in GitLab. So now, we have a compiling kernel, a pipeline to compile the kernel. How about test? How can we add some tests there? Well, we can add a basic boot test using QEMU. It's facilitated by VirtMe and Next Generation, written by Andrea Higge, which is based itself on VirtMe by Andy Lutomirsky. And to run a boot test using VirtMe, we need some new dependencies there, which is QEMU, VirtMe, and some other things to run case-of tests. I will like my boot test to be just an echo, just successful boot, catching the kernel version, which I'm compiling, and run the small subset of case-of tests. So again, just create your configuration here compatible with VirtMe. They have some tools there to do that in one single command. Compile the kernel, and some more dependencies for running case-of tests. And finally, boot the kernel with a single command again. So now, our pipeline, if you commit that, push that, you already have a pipeline with a job that is look like that results in green, which means it actually built it. You can see here the success message with the kernel version that I just compiled like this week, and the case-of test running there. If you look into the end of the message, the case-of test ran to the end, and well, it was a success. So that's all you need to have the most basic CI pipeline running for the kernel inside GitLab. Now for some real examples of CI people are running GitLab right now.
Thank you, Talis. So let's go through how things are done in the community these days in a bit greater detail. So let's start with the simplest cases and go up to the more complex. So XE driver is a graphics driver from Intel. And they do development on a mail list. And they normally use Intel Graphics CI, which is a sophisticated system developed at Intel, which posts results to Patchwork, and then Patchwork posts those results to the mail list, so the loop is closed this way. But they also have a repo on GitLab, which has CI enabled. And CI is implemented in a separate repo, just like Thales was demonstrated right now. And it's quite simple. They only do we ran to the end of the first part of the slides. Okay, just a moment. Hope it works. Yes. Yeah. So they have a simple pipeline there, just running some check patch, and then building kernel docs to make sure they work, and then running a build, basically to make sure that building still works. So that was very simple, and I hope it's gonna catch up soon. So this is the whole of the RCI YAML completely, and well, it's quite simple. Multimedia and television support subsystem take care about the radio, TV, and all other similar stuff. And they develop on the mail list for now. Track the status of the submissions on Patchwork as well. They are using Jenkins for some testing, but lately they've been working on their own implementation of CI in GitLab, and they also have it in a separate repo, which is quite sophisticated and well documented. So here's what's happening in their pipeline. So first they do some ABI compliance check, yes. Then they do static analyzers. Then they do builds with Clang, GCC, and an older GCC tool chains. And there's some more. They do basic bisection tests. They check that every patch builds and runs some basic tests. And then they run compliance test suite in a virtual machine. And then they check the signatures on all the commits. And finally, they publish a summary as an HTML file. So, and they also submit the results of testing to Patchwork, including a link to that HTML file, which becomes like an entry point to CI where you can see like a long overview of everything that's been happening and all the results. They don't use merge requests. They trigger on pushes and also on patches to the public mail list. For that case, they run only a minimal subset of tests which are more or less safe for anonymous contributors. And that's it for the media CI for now. Next, we have Mesa3D, which is not kernel, obviously, but they are sufficiently close. You all know Mesa, of course, and they developed fully on GitLab as well, and quite intensely. There is over 25,000 merge requests merged by now. And here's one example of those that was opened 3 years ago and took a while to merge, so the conversation was quite long. There's a lot of comments. And these merge requests are kind of tended to by so-called MarchBot, and some other projects also use it. The point of MarchBot is that when maintainer is happy with the contribution, did the reviews and everything, it assigns the merge request to the MarchBot, so MarchBot is now responsible. The MarchBot tries to rebase the merge request, then triggers the pipelines on it, and if everything went well and pipelines were successful, then it merges the merge request. And actually, the MarchBot is the only user who can merge merge requests, and that helps with avoiding conflicts and all that. So if it fails at any moment, yeah, if it fails at any moment, then it calls for a human, assigns it back to the author, and then they have to intervene and fix and rebase manually. But it manages to do a lot of work. So finally, merging the stuff. And it looks like this. So here's one of their pipelines, actually from that merge request. There were 81 pipelines run through that time, but this one was successful. So what they do is, well, they check if pipeline can run, if they have all the prerequisites. Then they prepare the builder containers with the tool chains, I guess, and everything. Then build the test suites, and then run tests in a whole bunch of devices. And then they publish the results. So there's more about this at a recent talk by David. He explains how this works and all the various details. It was happening at DevConf CZ. And that's basically it about the Mesa 3D. So next one comes DRM from Helen.
Yes, so regarding DRM, so I think you already know what DRM is, subsystem for graphics inside the kernel. And but we are talking about CI, so let's talk about the DRM CI. So what it is a pipeline defined to run on GitLab to test DRM. And it was released with Linux kernel 6.7, so a bit different from the other solutions that was shown is that this solution is in kernel 3, not in an outside repository. And well, I have another talk with more details about it, but let's go through a few bits of it. So the original patch was from Tomeo. And it's currently most used by maintainers to validate patches before sending it to Linux, right? And it derives from the Mesa project. So Mesa already knows how to do several tasks, for instance, how to submit the task to the real hardware and build the containers with all the configuration that is needed. So we kind of inherit all the configuration from Mesa. So let's compare both pipelines a bit. We do almost the same thing, so we prepare all the containers, then we build the kernel and the test suites, then we run all these test suites on the top of the kernel that we just compile on several different hardware across labs. So they are pretty much the same structure. So if you want to try it out, you can look at it and check the documentation. So you can find instructions how to run it on the documentation. So basically, so it's written 5 steps there, but the last 2 is just, now check the results. So it's basically 3 steps. So let's go through them. So first you need to plant a tree in gitlab.freedesktop.org. So we can have it 2 ways. So you can push your tree there, or you can just fork one inside the GitLab of FreeDesktop. Then once you have your tree there, we need to do the configuration that Thales mentioned, go into the settings, go to the CI/CD there, and in the configuration file, we need to point to this specific GitLab-CI YAML file that is inside the DRM folder, so it's inside the kernel tree. So once you have that, you also need permission. So you need to request access permission. You need to request to be added to this group that we call DRM/CI-OK group. So to do that, you basically you can check. You need to be part of this group, and you need to request to be part of it by sending an email to the community, or you can bother one of the members listed there. But of course, you need the community needs to trust you. It might require some time. You need to send a few patches there. After you have this, it's all set. So next time you do a push in your repository, and you check your repository again, you can go to the pipeline configuration. You should see a new pipeline with your last commit there. And you can check the result if it failed or if it passed. And you can also click to see more details, so you can see the full pipeline. But there is an overview there about the result. And but DRM-CI has a few limitations, so it is very specific to the DRM subsystem. And it only works on the free desktop GitLab instance, especially to access, because of the access to the labs. So all the credentials are inside infrastructure, so it's required to execute tests on the devices that the DRM subsystem is interested in. Also, the runners are shared across all projects on the free desktop. And the Mesa that Nikolai presented uses the same devices, and there is more time critical because it actually blocks patches from getting merged. So we have the MCI running with lower priority. To address all these limitations, we are proposing a new solution. We call it KCI GitLab. It's already? Didn't we have 45 minutes?
Sorry, it's 15.
Okay. Right. So there is a proposal solution called KCI GitLab. The name is, well, we were discussing about the name during lunch, but I'll talk about this in a second. So the idea is to have a common solution that everyone in the community could profit from it. So the KCI GitLab was a patch set submitted in February this year, and it has the KCI part on its name because it was developed together with the kernel CI community, but we were discussing that, well, it's a single community, maybe doesn't need to have this prefix, but anyway, we can discuss that later. The idea is to have a more generic solution, so a common base, so CI for everyone, basically, and KCI GitLab allows customization, so the structure is a bit like the device tree, where you can have includes, and then you can override the properties and define other more specific nodes. So which is very interesting for subsystem and for driver maintainers who want to define their own kind of testing. It is well documented. You can check there how you can run it. You can execute this on any GitLab instance that you have. We got a lot of feedback from the community, and the interesting thing is that Linus didn't block it. So the next version is, his proposal was to move to the folder tools/CI. So this is for version 2 of this patch. So this is how the pipeline looks like. So we started very simple. The structure is that we can add things on top. So we have the part where we build containers. We do some static checks. For now, we are just doing check, patch, and smash. We have a stage for building. So we build the documentation. We build the kernel with different configurations and two different architectures. We also have the last stage there for optimizing the runs. Oops, I pressed some button.
Oh, that's actually better. Leave it.
Okay. And yeah, that's it from my side.
Okay, thank you. Thank you, Helen. So, at Red Hat, we are developing fully on GitLab. The whole workflow is on GitLab for the kernel. Merge requests and all. So, we integrate this workflow with our traditional Red Hat workflow and other pieces of Red Hat, and tracking all the states of syncing with all the different parts of the company and the subsystems. So, and we use in particular tags a lot to signify like which parts are complying with all the requirements, which parts still need to be done. And we use bots a lot. So we have this CKI KWF kernel workflow bot, which does a lot of things. It checks if the status of the linked bug reports is correct, like if they are in the right state, both in Bugzilla and in Jira. Then it checks if the signatures are all right on the commits and all the signed off and everything is there. It also checks if the pipelines that are required have completed and displays the status of the optional pipelines, non-blocking pipelines. And then it also looks at what is being changed and then maps that to subsystems and then calls the people responsible for the subsystems and calls for required approvals and for optional approvals. And this way, like, we can involve people quickly in the reviews and they know what they need to review. So there is a lot of bot screenshots to make, so I didn't do them all, but you can go to that pipeline and see more. But the point is that no humans needed to be involved in all of this, and all the dirty and mechanical work of making sure that everything is in order was done automatically and not by humans. The humans only need to take a look at the summary and say like, oh yeah, it's all green, so on we go. So the testing summary is usually like just this little panel in the merge request, but if you go inside, you will see this, which is actually 5 pipelines in one. And this is just one pipeline flavor. We are picking and choosing different parts of the pipelines and the amount of pipelines based on what we're testing, what we're testing for, etc. We have lots of options there, but I would not recommend to look into our YAML. So the main part of the pipeline is testing, because we have our labs across the world and we test on real hardware and different servers, etc., and on VMs as well, and 4 architectures, including mainframes. And then when we're done, we put it into a database and in a special UI called Data Warehouse, which kind of aggregates everything and shows you the summary. So, for example, these numbers like 47, 1, and 16, those are number of results, but these are results not for tests, but for test suites, of which like many contain a lot of tests. So there's been quite a lot of tests executed there, and it's all working quite well. We transitioned about a year ago, I think. So. And well, it's working. Our development is fully on GitLab, which shows that it's in principle possible. The developers also have command line tools and the UIs to help with talking to GitLab for those who don't like web UI. But there it is. So why do you think GitLab is a good idea? As a potential option is, well, it's Git. It has code reviews which are quite functional, well, except the commit messages. There is quite well-versed, just a second, we're finishing. So it's quite well-versed in the integration and automation. You can do all those things with the bots and change states of things and merge things, etc. It has very good CI, which is considered one of the best, if not the best, in the industry right now. You can do gating and pre-merge testing and the post-merge testing, whatever you want. You can go to commits and see like what the results of testing in the past, like some old commit, and you can reach the tests that run on that commit and see them. You can have your own runners which do building and and testing or whatever you want. And you can have your own installation, your own instance of GitLab, because it's open core. And the company behind the GitLab is quite open source friendly. So we heard a lot of arguments against GitLab, and we hear you and we understand these. So one of them is being the centralization. It's been a single point of failure in your workflow. It's controlled by a corporation, even if it's open source friendly. It's not fully open. It's only open core. There are some features which are premium, you have to pay for them, and Red Hat pays for them, for example, but you don't really have to use them. And there's quite a lot of features which are not premium, basic. You need to sign in into each separate instance individually, and it kind of tries to de-anonymize you a little bit by prohibiting anonymous email services, but it's quite easy to sign up anyway. I mean, it doesn't ask you for your blood or signature or something. And web UI is slow compared to some console UI and sometimes hard to navigate. And you, of course, need to be online to review the code, which people mention sometimes. On the other hand, email workflow is, yes, flexible and democratic, but it's also fussy because you have to manage all the little bits. All the bits like signatures and making sure that everything's tested and everything is tracked, the right status, did it get the review, did it get the testing and everything, which can be done automatically, as you've seen, not only by GitLab, but all other tools. And in the end, people will make their choice what they like. But GitLab, yes, GitLab comes with the cost of learning. You have to learn it. You have to work around this limitation, which you are not used to. But exactly these limitations help GitLab save you time and effort by automating and integrating everything that's possible into a good workflow. And finally, which is not mentioned on the slides, is that you as a maintainer or as a developer free to build your own CI relatively easily and decide yourself what you're going to run, when you're going to run it, and what results you want, and how it's going to work exactly, without implementing all the things that GitLab already implemented and integrated in your workflow. So it could be your specific CI. If you'd like to try any of that or give it a try to, try to run yourself CI or see some of the things, or like even try merge requests or issues or whatever, if you have any problems, we'll be happy to help you at the kernel CI channel on LiberaChat or kernel CI email list with the address specified below. Thank you. Yes, we had a question first from that woman over there.
I think there.
You shortly mentioned it. How do you work around this non-possible review of commit message? So because it's not possible to comment on the commit message, but for example, it's very important that the commit messages are in good shape. Yeah. For example, to use git blame in 10 years or 5 years.
Yeah. Yeah, it's not very convenient, but you can always leave a comment in the merge request. It's not exactly inside the commit message, but you can copy the commit message, put it in a comment, highlight the parts you don't need, the same as you do with email, actually. So it's on the same.
But if you have a merge request with 20 patches or 50 patches,
yeah, well,
so a huge merge request, then this review starts to get really hard because you have comments on every commit message, and is there something going on so that this will be changed in the future on GitLab?
There is an issue open about this for several years now.
Yes, I know.
Yes, you can go there and tell your thing, and if you're a corporate customer like Red Hat is, you have some more leverage. If your company is signed there, go there and tell them to finally fix it. And if they do that, they will be way ahead of GitHub.
And just on that topic, cover letters as well. I think super important part of our workflow that generally don't get handled. Cover letters.
Cover letters. Yeah. That's your merge request message, basically. So you push the commits and you also...
Can that be commented on in the same format?
Well, yeah, it's like you answer with the comments. That's basic workflow.
It's the same problem.
Yes.
Yeah, so I think what the previous questions basically highlighted for me is that one big issue I see in this move is that basically the whole kernel community would move onto a product. So basically currently we have the mails, so nobody is owning the mail list system, so we have a lot more flexibility with that. And I think this whole commit message issue shows that it's incredibly difficult to make this tool behave the way how we want it to behave, because we have to open an issue and then we have to cross fingers and hope that they actually do something. And so I think, especially thinking about, for example, if the goal with this whole endeavor would obviously be that the whole kernel community moves to that at some point, because if everyone moves to that, it is a lot more convenient to use for everyone.
Of course.
Like, for example, one thing that we previously talked about was the issue of like, when you send a patch which applies to multiple different subsystems, if only 2 of the 3 subsystems have actually GitLab and one is still using mailing list, it's a bit awkward to send that whole thing. And so I think the general issue that I see is, if we move to GitLab, we are dependent on GitLab. So if the company GitLab is going away at some point, so they can just go bankrupt, and the whole kernel community is based on that with all their workflows, which is basically in a bad situation. So is there maybe a fully open source alternative that the kernel community could use, which is maybe not as fully featured, but which gives us the flexibility to work with that in the future, and which can't just go under the under us away?
Thank you. There were a lot of points made and good points as well. So let's get it from back to front. So there are other Git forges. We listed some of them there in one of the slides. You can use them. And I'm not saying everybody should use GitLab. I'm saying that it's one of the tools that could be good for you. Depends on what you what you like. And then GitLab itself is open source, the open core. So the core of GitLab with a lot of features is open source. And that's why Free Desktop runs it. That's why a lot of universities actually have a GitLab instance. So if GitLab company goes bankrupt, you would still have that, right? And there maybe someday there could be a GitLab instance on kernel.org. Who knows, right? Finally, regarding the commit message, technically you're free to go and implement that review yourself. I would not envy you, but but it's possible. It's open source. The only problem is convincing the GitLab team that they would take it into their tree and take care of it later and not keep in your fork. Regarding the commit messages and the cover pages, yes, it's important, I agree, and it's substandard that they don't have it. That's unfortunate. On the other hand, you don't have to use all of GitLab right now. As we've demonstrated, different subsystems, different people use different pieces, whatever works for you. We think that that CI part of GitLab is very good, and you can do a lot with it. And if you find it useful, maybe you can drop in a few merge requests here and there and see how it works. And see, maybe you can manage with the comments. Maybe it's worth it. You wanted to add something? Yes?
U-Boot uses GitLab for CI, and it works really well. The thing I really don't like about GitHub is I think their code review is just awful. It sort of disappears on you when someone force pushes. It's hard to see the difference between multiple revisions, and I've never used the GitLab one. So is that any good? Is it better?
No, okay. It's different. It's a bit different. It's still having a problem because they refuse to accept that, it's preview needs to be as detailed as we are used to in the kernel community. I think that the only system that gets the reviews perhaps is Gerrit.
Yeah, I like Gerrit. That's a good system.
It has reviews there are great.
So I have a second question. Is it possible to integrate email into these things? Because if there were some sort of bridge so that you could still use email, I actually find email really fast.
Yes. Yes. So, in fact, we went through this at Red Hat. We had to convince a whole bunch of kernel developers to move and sometimes nudge them, and in the end there was management decision to push on with the transition, but we had to accommodate for that. We had a tool built which bridged between GitLab and the mail list and everything. And to this day, people building and working on this console UI, as I said, which people use. It's quite effective and fast. You can do that. But in the end, that bridge, for better or worse, served only for a short while, and now nobody uses it. So Yes, it's possible.
It served the purpose then, right? It helped bridge people from the one
absolutely.
platform to the other. And I think that that is something that you would totally need to get the kernel community to move in a certain direction. And I could totally see a product where when you post comments on the web UI, it generates emails. When you reply to an email, it posts comments on the web UI.
It's already working like that.
Okay.
So GitLab allows you to, you get the notifications from GitLab, and you can respond to those, and your response will be in the comments.
Perfect.
Yeah.
Like one final question, you showed that you currently at Red Hat do your kernel development completely on GitLab.
Yes.
So does it mean when you do upstream submissions that you develop these upstream submissions basically on your GitLab instance first, and then you create patches out of that, or how do you create upstream?
No, the other way around. The Red Hat works upstream first.
Okay,
right?
so you send the patches,
yes.
They are upstream,
Then,
you put them back into your...
We can use the GitLab CI and everything to test them, I suppose. I'm not a kernel developer myself right now at Red Hat. I cannot tell you what exactly, but that's how I see it. And people here, there's plenty of people here who can who can correct me. Upstream first. But you can use GitLab CI for testing before upstreaming, no problem.
Okay, yeah, it just sounded interesting to me because I thought that you actually would have then basically a testing platform for the whole thing, because you could do basically upstream development on your GitLab instance, and as soon as you're fine with that, you send just the patches upstream.
Maybe that's how it works, I don't know. I suspect that people use that.
Okay, thanks a lot.
Thank you. Yeah, I think we are out of time. Thank you very much. Catch us in the corridor. Thank you. Okay. Well, we don't have to discuss speech. Thank you very much.
Hi. Nice to meet you. Yeah.
I heard news.
So should give a minute to settle, I think.
Yeah.
But have you heard what he says?
Absolutely. I will not try to work together with
Oh. Okay. We'd like to continue with our next topic, please. Okay. Go ahead.
All right. Thank you, everyone. Today I'm going to talk about Hazard Pointer. This is collaborate with Paul McKinney and Neeraj, with myself, of course. And yeah, let's get to it. Does this work? Okay. So we all know that atomic ref count has a scalability issue. This is the result from ref scale, and it's basically when the number of the readers increase, the critical section of the reader side, the actually acquire of the atomic will have a lot of contention there, and therefore the performance is bad. So we all know that as I said, we all know that the atomic reference has a scalability issue. And luckily, we already have solution in kernel. We can resolve this, which mostly per CPU ref count. You can distribute your ref count into different CPU, and so you don't have this contention. Or you can use RCU, which similarly. So this is how it looks like when you use RCU or use per CPU ref count when you try to do this compared to atomic ref count. All right. So this is like a very high level comparison between atomic ref count, per CPU ref count, and RCU. So indeed that per CPU ref count and RCU are fast and scalable. I need to point out that the scalability issue of ref count may not be the real issue in your workload, because it's only an issue when you have multiple readers want to acquire the reference at the same time. But it may not be the same case, may not be the case in your workload. So, but I'm here just try to, if this is an issue, I'm just trying to introduce the technology that can help on this. And for the memory overhead, the per CPU ref count does not do very well, because to have a per CPU ref count for each object, you need to have the number of CPUs ref count to ideally distribute all the ref count to different CPU, so that the scale of the memory overhead will be number of objects multiplies number of CPU. And for RCU, it's the memory overhead would be number of objects, because this is assumed that you use RCU head in the object, and there are small costs as well in the reader side, but assuming that you have a lot of objects, then the reader side of the memory cost could be like very minimal. And the other thing that RCU does differently compared to normal ref count or per CPU ref count is RCU has a bounded protect duration. This is because that you cannot hold RCU read log for very long. And if you hold the RCU read log for very long, what do you get? You will get an RCU store warning. And the RCU maintainer will receive email complaining about that, although it's not RCU maintainer's fault. All right? So for normal ref count and the per CPU ref count, what they can do is you can acquire the ref count in one context and pass that ref count to another context, and then so forth, and then eventually drop it somewhere, so that protect duration can be very long. And what if I told you that there is a secret technology that can still do fast and scalable, and still have a reasonable memory overhead, but the protection duration can be long? What if there is a technology that can do that? And you will guess what that is. All right. Thank you. Yeah. Thank you. So it's hazard pointer. So it's introduced in 2004, and it has been used. I think it's already made into C++ standard library, and it also has other user space library implementation, which means the technology is quite mature in the user space usage. And so I'm just going to talk about hazard pointer. So the key idea around hazard pointer is something called hazard pointer, or I call it hazard pointer slot, which basically hazard pointer give reader slot, and the slot you can store a pointer into it. And also the other thing is that the reader need to allocate the slot themselves, so that the reader can use the slot to protect what it want to reference. And magically, the updater can. This is similar to RCU. There is a reader and there is an updater, and the updater can basically access all the possible slots to determine that whether the reader still exists. So this is kind of the property around the hazard pointer slot. And this is a symbol code algorithm for hazard pointer when the reader tries to acquire the reference count. It will first read the global pointer, and it will store the value to a hazard pointer slot, and it will issue a full memory barrier, and then it will read again of the global pointer value, and if the value doesn't change, it will return, and assuming that the reference is already protected. Otherwise, it will reset this hazard pointer slot and try to fetch the value again. All right, and this is the release part, like basically you release the reference. It's very simple. Just set the slot to empty, and this is the opposite side. So the opposite side do things in the opposite ordering. So it will first know that what object it's going to release free, and then it will unpublish that object. It will unpublish the object so that nobody can reference the object in the future. And then it will issue a full memory barrier, and then it will check for each slot that whether there is a reader still on this object. And if there is still reader, it will go to recheck for the slot. Otherwise, it can check for other slot. That's the algorithm on the updater side. Okay. So let's get into some scenarios that how to understand how the synchronization algorithm between the reader and the updater works. So this is the case number 1. There is some diagram here. So initially that the global pointer point to the object, and the header pointer slot point to nothing. And after the reader install that header pointer slot to the object, it will change the status to here. And right after that, the updater actually change the global pointer to null, to unpublish the global unpublish the object. So it will change to this state. You can see that the global pointer doesn't point to the object. And this is before the reader do the second check. So right now that the reader can do the reader's second check, actually figure out the object is gone. So it will go to the else branch, which eventually will unset the header pointer slot, which gets into this final state where neither the header pointer slot or the global pointer point to the object, so the object can be free. This is a simple case. And this is the actually interesting part of the synchronization. So again, the reader first read the global pointer and slot that into a header pointer. So the header pointer now point to the object. And let's assume that the updater are going to change the object of the global pointer. But before that, the reader already do the second read. And the reader will assume that it gets the protect of the object. And so it's up to the updater that it cannot free the object until the reader is gone. So after the so this is the status when the reader does the second read. And after that, so there is a synchronization here. So since this step 4 on the reader side does not observe the write of the updater, so it means that this does not happen after this. The second read of the reader does not happen after the write of the updater. So there is kind of ordering here, and since we have full memory barrier here and here, so the memory barrier can kind of extend from here to here. So that means the step 2 of the reader actually must happen before the step 4 of the updater. Means that the updater will guarantee to observe the value stored by the reader. So that means this the read of this slot so the updater can observe this slot being the object. All right? So anybody have any confusion about this? I can explain. Okay, so we use this ordering to guarantee that when the header pointer reader acquire the reference, the updater must be able to observe that. This is the synchronization, the most important synchronization between the updater and the reader. So after this, the reader will eventually release the ref count, and the updater will eventually observe that. So this is give us the case of synchronized case number 3. So this is quite simple. The updater, the reader do change the slot into null. And since the global pointer is already not point to the object, and then once the updater observe the change of the slot, it can move forward. And basically, after the updater check all the slot, go ahead.
Back to the previous slide.
Okay.
Just if it can help people in the room, that would be the Decker case from Paul McKinney's LWN articles about memory ordering in RCU. So it's a classical case where you have store to A, store to B, cross loads with the barriers, and there are some guarantees that are inherent to that.
Yeah. It's a classic store buffer synchronization. Yes. Thank you. All right. So this is basically summaries of all the what we just have previously. So basically, you can see that the hard pointer is a synchronization between the reader and the updater, and you can also see that the reader can actually use the hard pointer slot to protect different objects. This is better than principal ref count, which the slot will be the ref count will be dedicated to one object. So this is why a hard pointer can be space efficiency because of this. And also that the other benefit is that notice that the updater only need to check for this object, so the object you want to free. So it doesn't have the similar. It doesn't have the, well, it's not the issue, but it doesn't have the property of RCU where you need to wait for a grace period to wait all the reader is gone. It can wait only for the relative reader to gone. So that may potentially have a smaller memory footprint because of that. Okay, so yeah, that's basically the introduction of hard point algorithm. We have a question here.
Yeah, so just between example 2 and example 3, on the data side, you had a read once in example 1 and 2, and on example 3, it changed to an SMP load acquire.
Oh, yes. Yeah, sorry. I should bring that up. So, yeah, this one should always be SMP load acquire because of the potential, this case. I'm just putting this, because in this, in this case, it doesn't need to be acquired to guarantee the correctness of algorithm, but in the follow case, it needs to be acquired. So yeah, you're right. And I want to explain a little bit on why this need to be acquired. So here, the reader can access the object, and it do a store. If this is a normal store and this is a normal load, then there is no guarantee that the access from the reader will be observed right here, basically here. And then if the updater free the object, the access from the reader may still have not been observed by the updater. So that could be a user after free in that case. Although it's quite impossible, but that's maybe the case. So we need this release and acquire here to prevent the readers. This is similar to you need acquire in the case where you do a reference count put. You also need acquire there because you want to avoid the access leftover there. Go ahead.
This is all fairly new to me, of course. So what do you mean by the, sorry? Okay. By slots, you really mean like this is usually per task, I guess. So the task needs a slot to store and it has a pointer.
So it's a little bit flexible. I have some slides about that. So basically, you can allocate a slot from, you can give some memory to the hard point system, and then later on you can allocate a slot So you basically get a slot from the what you gave to the hazard pointer. So it's flexible in that way.
So we briefly talked a bit about this, and I think I annoyed Paul at LSFMN briefly with this. An interesting case just to explore for me would be files or the FD table, because currently we use a mechanism that is eerily reminiscent in some ways of what hazard pointers do. So we have this use an FD, dereference the slot in the FD table, take the pointer, use an atomic int not zero. If it's positive, then refetch the pointer and compare the two to make sure that, you know, because of slab type safe by RCU, that it's not been recycled by something else. So hazard pointers might be interesting. That the only thing is that, so say you have a task that has like 100,000 file descriptors, which is not that uncommon with, I don't know, IO Uring or what workloads you have, then the interesting question to me is like, how would you handle this with hazard pointers? Or would you make the FD table itself use hazard pointers? It's very interesting for that case.
Paul, do you want to answer that?
There's a lot of ways you could do it. So one way you could do it, so the question is, do you need to hold a hazard pointer just because you have the file open? And I think the answer is no. You hold the hazard pointer when you're actually doing something like reading from it or writing to it. Okay. So at that point, how many operations can you do all at once? The answer might be one, but IO Uring might throw a few curves in there.
Yeah.
So you only need enough hazard pointers per task to tie down the maximum number of file descriptors that can be used at that time by that task.
Yeah, it depends on the operation. Sometimes you have 2 file descriptors if you do. Sorry. You have 2 or maybe 2 file descriptors if you splice or something when you do an operation from an FD to another FD, but it should all be fairly limited. Depending on, I don't know if you can splice into multiple file descriptors, or anyway, but yeah, it should be fairly limited.
Yeah, you'd only need as many hazard pointers per task as you had file descriptors you needed to use at the same time by the same task. So I think that's good.
Yeah.
Hello. Yeah, I have a terrible proposal, which might be overly complicated, so it might be a terrible idea. But you could have like one slot or a couple slots per CPU, and then when your task gets scheduled out while you're holding a hazard pointer, you turn the hazard pointer into a ref count by using a sched out notifier. But I'm not sure if that's a great idea or a terrible idea.
I would try to avoid it, but sooner or later somebody's going to have to do it. So good on you for helping them out ahead of time.
Yeah, but I mean, this I guess in general for FD table this would be interesting. Also, what performance numbers we would potentially see, how much improvement we would actually get.
Yeah, that's
on a patch set right now to port it to RCU ref as a first step and see if we can bring the atomic int not zero costs down.
Boshun, they posted the patch set this morning, and Lena said, okay, what are the use cases and what's the performance advantage? So please. And yeah, it would be really good to use RCRef as well because, well, maybe that's better. But anyway, it's good to have a full comparison.
I mean, it's simpler, although I would have some questions for you for that later. It seems like it's something we can easily port. I just worry about some what the interactions with slab type safe by RCU are. It's probably
slab type safe by Haspotter. Sorry, Vlastimil. Oh, we had one over there. Yeah.
By the way, I think Linus' email can be a nice introduction for next year's presentation on hazard pointer.
I have a quick question about the updater. I think on the slide it says updater can have access to all the slots.
Mm-hmm. Yeah.
I'm just curious, like how is this done?
So I will cover that in the next part, but basically it's actually required for the updater to read for all the slots because updater need to know that there is no existing reader for a particular object. So that's kind of a requirement of hazard point implementation. And there's an ability guarantee that updater can do that. Otherwise, it's going to be a wrong implementation. Okay. Right.
Here.
How do RCU traversal, let's say, interacts with hazard pointers? So how do you promote some existence guarantee from RCU to hazard pointers?
I think this is a good question. I'm going to ask Paul because this is actually going to be nicer upon. Yeah.
Good segue. So it would be pretty similar to what you do now to promote to a reference count. Okay. I can't think of any difference right offhand. The main difference, of course, is on the update side with a reference count. I'll get to that the next slide. But first I'm going to do the 100,000 foot level of how you compare these things. And the thing is, the laws of physics are really inconvenient here. I mean, you'd really like something that was free on the read side, and on the update side you could immediately reuse the memory, and that you could just go traversing down the data structure without any possibility of retry or anything like that. That'd be wonderful, but if you come up with a way of doing that, you'll have to prove it to me, but it's really cool, okay? But at 100,000 foot level, RCU can be kind of thought of as a fast and scalable replacement for a read-write-a-lock. And you can use it for other things. And it's not exactly read-write-a-lock for one big thing. The readers do not exclude the updaters. But nevertheless, in a lot of places where we used to use read-write-a-lock, we now use RCU. In the similar spirit, hazard pointer can be thought of as a fast and scalable replacement for reference counting. Again, they aren't exactly the same. Like RCU, hazard pointer, when you get rid of something, there's a delay. You know, you can't just get rid of it. In the case of RCU, you have to call RCU or synchronize RCU in something. And there's a call hasputter, or I can't remember if that's exactly the name, but that you have to use on hazard pointer. You have to actually do something, and then there's a delay, and then the thing gets reclaimed. But that's kind of the analogy. On the other hand, there's a lot of overlap. If you have hazard pointers, you can do a lot with it that we would normally use RCU for right now in the Linux kernel. And similarly, because we have RCU, have had it for 22 years now, there's a lot of things that might be more natural for hazard pointers, like FD table, to Christian's point, that we use RCU for. And so one thing is, what the right place to use it is. And let's see if nope. All right. I may have to have Bushun come up here and figure out tell me how to advance the slide.
I think there is a button there. I think you should click. But do you want to go to the previous slide?
I want to go, oh, I'm already there.
Yeah.
Okay. I'm just impatient, that's all. I want it now. So this is Bushun's earlier slide. I'm going to take a little bit different look at it. The thing is, you can ask which one's better. And well, we're engineers here, and the answer is the engineer answer. It depends. Okay. So reference counting, two really cool things about it is you can get a reference count and hang on to it for 5 minutes if you want to, and as long as you aren't tying down too much memory, nobody cares. Or an hour, or a few days. It's okay. And another really cool thing about it is that when the last guy lets go of that reference count, now you can free it. I mean, that reference count is going to 0 and bam, it's ready to be used. You have to pay a price, a couple of prices. One is that it's slow and unscalable. Another thing is that if you have a possibility of object deletion, things get complicated. There's a guy named Valois that tried to do just reference counting and only reference counting for that, and that turned out to be really complicated and buggy. The guy who invented hazard pointers, Megan Michael, corrected some of the bugs in Valois' paper. But, as Bushman said, if you aren't really hitting the thing very often, if you're only acquiring a reference every 5 seconds and you're freeing objects every minute, it'll be fine. We still use the Linux kernel, and we should continue in the places that make sense, which is a lot of places. Per CPU ref count is a cute thing Ken Overstreet came up with. At least his name's on the file. And it's fast and scalable. Its big weak point is that you have to it splits the reference count across the CPUs. And that means a fair amount of storage. Now, for a lot of cases, if you're tying down something 64K or a megabyte, who cares? But if you got an 8-byte object that you're trying to do this to, that may not be the price you want to pay. All right? Also, like the normal reference count thing. When you say the equivalent of RC dereference, when you say RC dereference, give me the next pointer in the list, you always get it. RC doesn't say no in that case. All of the reference count like things can say no. I'd like the next object, sorry, start over, okay? And it's a two-edged sword in both ways. The cool thing about RCU is you can unconditionally go down there, and it's very fast. Nothing can block you, really. Okay, an updater can't do anything to slow down an RC reader other than make it take more cache misses. The price RCU pays for that is that when you say RC read lock, that ties down each and every RCU protected object in all of the kernel, no matter whether the things have anything to do with what you're doing. All right? That's why you get the convenience. RCU doesn't have to know where you're going. It just ties everything down and lets you go. The other things, and then that means its memory footprint could be large. If you've got a long reader, there's going to be a bunch of memory piling up. The thing you get, the benefit you get from this painful try to go down to the next list, no you can't, start over. The benefit you get is that only those pieces of memory currently in use are actually tied down. If you're short of memory, you can go and burn a bunch of CPU and free up everything that's not actively in use right now. Hazard pointers, it's fast and scalable. It has an SMPMB in the reader, as does SRCU. Matthew would point out that in user space you can use membrane, thank you, and we could use IPIs in the kernel. Some of the people who are dealing with real time might not like that much, so if we do that, we'll have to do something, right? It's have the same things as reference counting things. If you want to hold a hazard pointer for a few years, as long as your machine stays up that long, no problem, go for it, right? If you get your RC reset critical section beyond 21 seconds, the kernel will yell at you, or if you're doing expedited with certain Android configurations, you get 20 milliseconds, all right? Yeah, so finally we've got an RC CPU stall warning faster than Dynex PTX back in the 90s. It's really cool. Yeah.
So with ref counting, you can hold those ref counters for years if you want.
You can.
What is the impact of holding a hazard pointer for years?
Same as a reference count. You tie down that object. The guy behind you wants to ask a question. Yeah.
Well, I mean, a bit more than that, right? If you've got a limited number of slots, you start tying up your slots.
That's true.
And that's also a bit of a resource that you'll run out.
You're absolutely right. You have the additional, but Boschun's patch, if I remember correctly, does dynamic allocation or allows you to give new ones in there. So that's a price you can choose to pay.
As I recall, there's a worker thread kind of handling this hazard pointers lookups, right? So you will require more work as long as you are holding a hazard pointer, right?
Yeah, that's another cost. So you can get rid of everything that's not actively being used, but if you want to do that because you're out of memory, you're going to be paying some serious CPU to do it. But, you know, it's a trade-off, right? Anyway, we're getting towards the end of time, and we should let Niraj have some time to tell us about some benchmark results. So why don't we do that? Oh, excuse me. Okay, well, I'm obviously not doing well here.
No problem. So yeah, I have like some simple slides about the implementation. Try to answer like the previous question about how the updater get to access all the slots. So basically, there is a concept we introduced. It's called hard point context, which basically is allocation for all the hard point slots, and the other concept is that we need to scan all the readers, basically scan all the slots from the updater. And so since that the hard point need to allocate by the reader, and the updater can access all the slots, then it's given the question that how we do that, right? So the idea is simple. You just ask the reader if they want to use hard pointer. They just provide some memory to the hard pointer, to the hard pointer, so that the memory will be linked together by some linked list, and the updater then can know that for sure that's about what all the possible slots there. So this is so the linked list and all the synchronization on this hard pointer context is not a problem because it's only mostly accessed by the updater, like go out for all each context. and the reader will just allocate the slot and just write to that slot. And if we arrange the memory correctly, smartly, then we can make the slot in a different cache line so that different hardware pointer contexts doesn't affect each other. So this is the idea why we need a hardware pointer context. And this is like with the hardware pointer context in the picture, that how the hardware pointer API would look like. So basically, the reader needs to initialize the context. It can add as many as contexts as possible. And once the context is initialized, it can allocate the hardware pointer slot from it. And the one is really acquired object, it will do a hardware pointer try protect. And then it can, if that succeeds, then it can access the object here. And eventually it will do the clear, which basically release the hardware pointer slot. And the reader can still reuse this hardware pointer slot until it's either the hardware pointer context is cleaned up or the reader explicitly free this slot. And the updater will, as Paul already mentioned, that spoiler alert about this, it can call hardware pointer function, and it's basically will put this object in a list where eventually wait for the other reader to go and execute this function. So this is like the roughly what will the user of hardware pointer do. And back to the last bit of hardware pointer implementation detail. As I said, the updater need to access all the slots to understand that what any existing reader for an object. So if we have an object and an active slot, the whole scan would be, if we do like a Bruce Bosley, then it will be I'm multiply n, and it will be quite bad if there is like lot of slot and a lot of object. And some user space implementation use B tree or other tree to cache the scan result of the reader, but it's introduced a case where you need to allocate memory to free memory, because the reader scan in the updater is basically try to free all the object. And if you allocate the memory to free those memory, then you may have some situation where you either cannot move forward because you don't have the memory to allocate to free the memory. So we don't want to do that in kernel. At least we don't want to do that in the beginning. So the solution is simple. It's just since we already have the hardware pointer context, we just make the hardware pointer also pay the price of the search structure for its slot. So basically, we put an arbitrary node into it, and with a snapshot of the hardware pointer slot value. And when the updater scans the reader, it can use this arbitrary node to kind of take the snapshot of the slot and build up an arbitrary, and then once the updater finishes the scan, it can use this tree to basically check whether there is a slot it interested. So yeah, this is considering the reader scan, that's how the hardware pointer context will look like. And yeah, with all that, we have the patch, and I have put some test number on it. This is solely on the reader side scalability. You can see it's basically similar to perceivable ref count, and it did a little better job compared to sleepable RCU because it had only one SMPMB there. And the overhead, since we have the callback for the updater, so we have to introduce some RCU head like object. So we have big O number of objects. And also the other overhead is the number of slots, which is really hard to make an estimation. So basically, it's the memory overhead of the slot is basically depends on how many slots you will have at X max value in your system for your workload, right? If you have, like Christian mentioned, that if you want to reference like 100 objects, then you need to have 100 slots. And but usually the case is that you only most of the case I assume that which is good for hard pointer is that you only, for each task, you only have like 1 or 2 or maybe 8 slots that you use to you access, and that would be a sweet spot for hard pointer. So in that case, the memory overhead is relatively low compared to pursue ref count. Okay, so this is all the details about the implementation of hard pointer. Go ahead.
What is the arbitrary ordered by, and why is it ordered?
It's ordered by the pointer value of the object. So, yeah, address. Yeah, so it's ordered because you can do a quick search. You can scan all the readers, and then when you processing the callbacks, you look one by one and try to see whether there is an existing reader for that object in the tree. And if not, then you can free this reader. You can free this object. Yeah. So, yeah.
In this patch series, have you migrated some particular kernel data structures to hazard pointers?
I have not.
Okay, so then what do you think, coming back to Paul's earlier observation, which is what is the right technology? Well, it depends. So what are the right data structures that you think really need hazard pointers? They shouldn't use RCUs, they shouldn't use reference counters, they should be using hazard pointers.
So I think Neeraj have some case, he will show that later. And for myself, I think that one of the things which we usually do is sometimes we need to acquire the ref counts of a task. And because maybe the task is like an owner of something, and the other one can check whether the owner is gone or check the owner status. So owner, check the state of the owner and so in that case, maybe we can use that for task for that particular case without holding the reference count of task. That's maybe one usage.
This might be a good time to.
Yeah. So let's get to. Sorry.
Was a question there.
Oh, I have a question. So typically, if I'm using like ref counting, if I'm the thing that cleans up the object is the task that does the last put, right?
Yeah.
When it goes to 0, we clean it up.
Yeah.
What actually frees the object in this case? If I clear the pointer, is there a kernel thread or something that comes along and scans these things? I don't understand that part.
So this. If you use hard pointer, it will be similar as you use RCU. So you will have some delicate task. So you will have some function which you know that the object you are going to like release this object, and you will call a function called call hard pointer that will kick up a work queue, and eventually that gets freed by that work queue. But this is different than normal hard pointer, normal ref counter usage, where the last one reference that free that. So it's different. So you have to adjust that for sure.
Thank you. Okay, and do I get it correctly that you expect basically like one context per task, or possibly multiple contexts per task?
Yeah. Okay. I mean, hand over this to Neeraj.
Yeah. Good evening, everyone. So I'll be talking about the use case. It's Nginx, which when it is run with AppArmor enabled in kernel, we see scalability issue where you see that atomic contention is there on the ref count. So briefly, before going to that, I will give an overview of Nginx and AppArmor. So Nginx is a web server, and what happens is it has a architecture where you have a master thread which takes all client requests, and then it delegates those requests to worker threads. To optimize throughput, the throughput is the number of concurrent client requests you can service in a given time or a given second. What it does is there is a single worker per CPU, and each worker will handle a particular client request. So you have more throughput when you service more requests. And now going to AppArmor. So AppArmor actually uses or it enforces a mandatory access control where every application has a profile for it. So that profile tells you that what all files it is allowed to read, what all actions it is allowed to do, like changing the owner or binding to a particular socket, which it is allowed. So each application has a profile file, and that profile is loaded into kernel. And when, let's say, you open a file, the syscall actually lands into your security hook for AppArmor, and that hook checks whether that action is actually allowed by the profile. And to do that, it actually acquires a reference on the profile label. So each profile has a reference count associated with it, and that is acquired by that security hook. Now, this is how it looks like. So what happens is, so on the left side, there are Nginx workers, and these workers are trying to open a file. And on the right side, if you see, they land into security hook of AppArmor, and they try to acquire the reference at the same time on the same policy or the profile object for that application. So this leads to the atomic contention on a particular ref count, which we observe. Now, what we have done to try hazard pointer for this application is, so there is a get call which actually acquires the reference count. And what we do is, we do not replace all the reference count usage for a label. We only modify this function where we see most of the contention. And what we do is, we, instead of doing a kref get and put, which are done here, we actually create a hazard pointer context and associate one context with the, so here we associate one context with that particular label. And when that function is done, we clear the context. So the context is, the boundary of the context is within that function, which is the hot path of your AppArmor when the file is accessed.
So why isn't the right thing to do in this case, seeing as it's a small critical section, why don't you protect it with RCU rather?
So to protect it using RCU, you mean? I guess we can do that, but yeah, that is correct. We can use here, but then we have to wait for the entire synchronized RCU grace period for that function to complete. Yeah, maybe that is possible, but we have to try whether it gets more overhead on the updater side. That is one thing.
Just pointing out that we might want to investigate promoting those other pointers to ref counts if the use takes a longer time, right? But future discussions.
Well, we should probably go to the results. Just
sure.
Go ahead with the performance results.
So when we run this on the use case, what we see is on the baseline with kref enabled, when we compare it with the AppArmor disabled, we see 11.6% improvement on the throughput. And with hazard pointer replacing the kref usage within that function, we see a 7.4% improvement on the overall throughput. Yeah. Yeah.
No, I think it's fine.
Yeah, that's all. Thank you.
We are out of time.
Next year, work on time management.